But we cannot change the address on the landing page, can we?
No, we can't change it on the landing page anymore. But we should update.
Sorry.
But we should update. I mean, I can add some comments for the invited speakers. That it's now available here, and I can also post it. So we can't continue the stream on the old one.
Sorry, what?
So we definitely can't continue the stream on the old channel.
Yeah, I don't think so.
So even if we take the video offline, like make it private for now.
No, it's like the address is combined to the old one. So if you collect the older address, then it basically the yesterday's video will come up. So it's like the address is used. I cannot specify the address anymore.
Okay.
I haven't figured out how it works. Yes, when I'm testing this live stream, I did test like stop for one day and start to stream to the same address the next day. Yeah, it works, but.
And what does it say now?
Hmm?
And what's the error message that you get?
Oh, there's no error message. It's like it just shows like the old stream is over, so it becomes a video instead of a line. Oh, I've already started the stream.
Okay, then it just means that we should leave messages. Yes, can you post it to the Slack? We're already streaming.
Just a few seconds.
Sure. And we're streaming to the CVPR Zoom already, right?
Let me check.
Yes. Okay. Welcome everyone to the second day of our workshop on SLAM, visual odometry, geometric and learning-based SLAM systems, and long-term visual localization. My name is Thorsten, and I'm going to be the host together with Wensham and Goyu and all of our other organizers. Let me give you a brief introduction of what will happen in this workshop. That's not what I wanted. Okay, so welcome to the second day of our workshop on long-term visual localization, visual odometry, and geometric and learning-based SLAM systems. I'd like to welcome you from all of our organizers, especially Wensham and Goyu. who have done most of the work. For your information, we are streaming this live. We had a live stream yesterday. We changed the stream link. This is a new one. And the new link is also on the streaming page of yesterday. And you can also join using the Zoom links provided by CVPR. If you want to ask questions, either do this on the chat of the CVPR Zoom, or you can directly do it on YouTube, and we will forward it to the speakers. The detailed schedule of the workshop is available on the workshop website, which is also available on the CVPR website. So this morning, or the first part of the workshop, we will have invited talks by Andreas Geiger, Victor Prisacariu. We will discuss the visual localization challenges. So we will have talks by the winners and runners-up. And then we will have invited talks by Jana, Kosecka, and Jakob. After Jakob's talk, we will do a break and then resume in the early afternoon Pacific time with talks by Raquel Urtasun, Katerina Fragkiadaki, Deva Ramanan, Haibin Ling, Xiaoming Yu, Yasuyuki Matsushita, and Yingyi Ju. And with that, I am actually done with my introduction of the workshop. So it's my pleasure to introduce the first invited speaker, Andreas Geiger, who's currently a full professor at the University of Tübingen and still associated with the Max Planck Institute, where before he became a professor, was a group leader. And I know him quite well from the 1.5 years he spent at ETH, and it was a pleasure working with him. He's always doing very cool stuff. So I'm very much looking forward to his talk. Andreas, the floor is yours.
Oh, thank you very much, Torsten, for the introduction. Let me try to share my screen. Can you see that?
Yes.
Good. Okay. So I'm happy to be here, even for virtually, and I'm going to talk about 3D controllable image synthesis, which is joint work with my postdoc and my PhD students, Katja, Lars, and Michael. Oh, I need to close this window here. Otherwise, I don't see my screen. Okay. So as we all know, SLAM system, there's two dominating paradigms to SLAM systems. There's the indirect approaches that take a set of images, extract key points, and describe these key points, and then match them in order to minimize reprojection errors for either tracking the agent or incrementally building a map for estimating the 3D landmark locations. And there are direct approaches that take the set of images and try to directly minimize some photometric reconstruction loss in order to track the agent or to, for instance, estimate a per pixel depth from these measurements. Now, one work that I particularly like is already now also 7 years old, is SLAM++ from Andrew Davison's group, where they took simultaneous localization mapping to the object level, where we try to find an object level description of the scene, which has the potential to scale to potentially much larger scenes and compress the representation much further. Now, all the current SLAM systems, I would argue, are mostly discriminative. They are relatively large, sophisticated pipelines with many components, such as feature detection, robust matching, loop closure detection, mapping, and so forth. And many of these components are either hand engineered or learned on independent loss functions. So the question I want to raise in this talk, can we also think about a generative model for SLAM? A model that directly learns the observation manifolds, being that images or LiDAR points, where basically no supervision or annotations are required. For instance, in the SLAM++ system that I've shown in the previous slides, all the 3D objects had to be previously scanned using Kinect Fusion, and there's an object detector that has to be trained on a big label data set. So can we build a generative model that can be trained without such supervision? And that captures the uncertainty in the data, which is useful on its own, but also, for instance, for completing missing parts of the scene. But the challenging question here is, well, how can we actually disentangle the underlying 3D factors that give rise to the image generation in a completely unsupervised or self-supervised manner? That's certainly a difficult task, and we are trying to do some baby steps in these directions here in this work. And that's what we refer to as 3D controllable image synthesis. We want to build a generative model of images that is trained based only on images, but in essence is 3D controllable, where we have access to all the 3D quantities that we'd like to manipulate, such as the pose of the camera. So here's a brief overview of the goal and where this could be useful. So such an image synthesis model takes a description of the scene that includes the pose, but also other parameters like the appearance and the object geometry, and generates an image. I mean, this is an image from a real simulator. This is not an image from our simulation. So as you will see, we are far from that, but that's the ultimate goal. And this can be used then for simulation or for training or for verification, which is very important, of course, for any intelligent system. But it can also be used in a Bayesian setting to infer quantities, latent quantities of interest given an image as input, such as the pose, which then becomes useful for pose estimation or localization. So here's a brief overview of how we define this term of 3D controllable image synthesis. We want to learn a generative model where we basically have a latent distribution and we can sample images from that. So it's a generative image model, but where the underlying factors here are 3D controllable, where we have explicit access to the object shape, the object pose parameters, the object appearance parameters, such as the texture or the camera viewpoint. And we want to learn this from 2D observations, which do not require any pose information. So it's just a collection of 2D images. And we don't require any supervision, no poses, no segmentation, no depth maps, nothing. So let's have a look at some generative models. The traditional rendering pipeline maybe serves as the most basic generative model, where we have a 3D designer that invents some 3D models and that get then rendered using a physically based renderer into an image. But the nice thing about this approach is that, of course, the 3D factors, they are designed, so they are by design controllable. However, it's of course not scalable, so it's expensive to create this content. Then we have classical GAN-based models, image GANs, generative adversarial networks that take a random code and in an unsupervised fashion produce a model that can generate images from that random code. So these, in contrast, are unsupervised, so you can learn in an unsupervised fashion from 2D images, but the 3D factors are not fully disentangled, right? So there are some works that look at disentanglement of factors, but they are not fully 3D disentangled. And the reason for this is that this relatively naive 2D convolutional network that's typically used for the image generation process, this naive architecture needs to learn all the aspects of the image formation process. For instance, perspective projection, which is something that we actually know something about. So we should incorporate this into the image generation pipeline. That's our hypothesis here. And this gives rise to our approach, where we have a random sample that's fed into a 3D generator that generates a set of 3D primitives that are then rendered onto the image plane in terms of feature maps. And then we have another 2D generator. So both of these are trainable models that then give rise to individual images that correspond to these objects that can be stitched together into a coherent description of the scene. And then this entire model we want to train end to end. Now, in this model, the 3D factors can be controlled because we have this explicit intermediate representation that is actually 3D. And we can also learn it in an unsupervised way from 2D images, just as 2D generative adversarial networks. Yeah, so the key idea here really is to jointly model in 3D and 2D space. Here's an overview of our model, which is actually a paper that we present here at this conference. So I will walk you through all of these. It looks quite complex. I'll walk you through all of these steps now in succession. So let's start at the left side here. So we have a latent code that's drawn from some standard Gaussian distribution, and that's decoded into different quantities. So we have a certain number of foreground objects that we decode this into. So we have a common backbone and then shallow heads that decode into the parameters of these foreground objects. And then we have one object that's modeling the background. So here you can see the formal notation of these primitives. O1 to ON are the foreground objects, and OBG is the background object. And then each of these primitives is represented by 3D parameters, such as the rotation and translation and scale of that primitive, and appearance parameters that implicitly determine the appearance that will later be rendered onto the image. Then in the second step, we have a differentiable rendering part here, where we render each of these primitives. I'm not going to specify these primitives now. Later in the experiments, I'm going to show which type of primitives we actually use, but let's just assume we have an abstract representation in terms of primitives that gives rise to a differentiable rendering in terms of its feature maps. So we render these onto the image, and we get feature maps. This is the first column. We also get alpha maps, which describe the spatial extent of this primitive, and we get depth maps. And then for the background object, we only get the feature maps. In this case, we use a sphere that we look at from inside out, and this basically is kind of the environment map that we produce. So we don't have any alpha map or depth map here because it's assumed to be at infinity and cover everything that's not covered by the foreground objects. And then we have a 2D generator where now these 2D representations are processed with a set of 2D convolutional networks, basically UNets, that transform these representations into now here in the first column, the actual RGB pixel values. In the second column, refined alpha maps that adhere more closely to the actual shapes. As you can see here, this is more the alpha map of the primitive. Now here we have the alpha map of the actual shape. And then also refines the depth maps. And we also have a 2D convolutional network that, I mean, all of these have shared weights that produces the background image from the feature representation. And then we have a standard alpha composition step, which is also differentiable, that based on the depth ordering produces an image from these alpha maps and these RGB pixel values, as you can see here. In this model, we have multiple loss functions. So the most important loss function, of course, is we're working in an adversarial framework here, also like GANs, is this adversarial loss function. It's a standard adversarial loss with spectral normalization. The only difference to a standard loss is that it has a little switch here, C. So it's also conditioned on C, and C determines if the image is either a pure background image or if it's an image which contains background and foreground objects. In fact, we observed that if we just compare, if we would not have this, if we just compare the full images to the real images in our data set, then it would be easy for the model to integrate the appearance of the objects into the background component. Now, to disentangle this, we generated a data set of real images with foreground objects and background, and a set of only real background images. Now, with this discriminator here that can be controlled using this flag C, we can now learn to disentangle using these two data sets the foreground objects from the background objects. And then we have a second loss function here, which is the compactness loss, which is basically a regularizer on the size or the shape of the object. If we wouldn't have this, then objects could grow very large, which we want to avoid. We want to have the most compact representation that still produces a reasonable image. That's why we penalize basically the L1 norm of this alpha map here, which means that most of the pixels should actually be turned black. And then we have a geometric loss that ensures geometric consistency after the 2D conversion. Because we have this 3D to 2D conversion and then another set of layers that produce from the feature maps actually the RGB pixels, it could be, and that's actually what happens, what we also observed, that these 2D convolutions also contribute to the image formation process itself. So they manipulate slightly perspective, and that's of course not something that is desirable. So what we do here is we basically, because we have the 3D representation, we compare the appearance that we obtain here to the appearance of the same instance that has been randomly rotated and translated. And we can do this because we also have the depth map, so we can do lookups through the depth map into the other viewpoint. We basically create a multi-view scenario, and this loss function then penalizes the error, the multi-view reconstruction error, both in terms of the RGB pixel values and in terms of the depth values, which is a geometric loss. So here are the data sets that we're using for our experiments. We have this simple data set without backgrounds, then we have a data set with simple backgrounds, and we have an indoor data set that's using real images from, or I think it's rendered images, but more realistic images from indoor scenes, and we have these cut models from ScanNet overlaid on top. And then here, from ShapeNet, sorry. And here on the right, we created our own little data set using synthetic fruit. Now here, everything is real. So let's look at the experimental results. We compare to several baselines. The first baseline is layout to IM, a recent work published at CVPR 2019, which shares the idea with us, but does everything in the 2D domain. So the idea here is also that from a layout of bounding boxes, one can produce an actual image. And this is here modeled in such an autoencoder-like fashion. And in contrast to us, not only it is modeling entirely the scene in 2D with 2D bounding boxes, but it also requires the 2D bounding boxes as supervision during training. So we don't require 3D bounding boxes or the segmentations during training. However, what we observe for this model is that if we now generate an image using this layout representation, and then we move this object here in the red rectangle across the screen, the object identity is not disentangled from the pose or from the 2D location, actually, because it's only a 2D model. So as you can see, as we translate the bounding box that should generate that car, the car identity flips completely from yellow to red to black. Right? So it's not consistent. And that is something that happens consistently for this model. It's not something that the model actually penalizes, because all of these images look realistic. It just looks for realistic images. It doesn't look for this consistency. Then we created a baseline from our approach where we remove the 3D layers and just use the 2D layers. So here, this generative part directly generates a set of 2D rectangles, so a 2D primitive representation that's then parsed with these 2D units into similar feature maps as we had before. It's basically a 2D version of our model. And what we observe for this model is that, well, while it preserves the identity, it does not disentangle rotation and translation, which is clear because we have just a pure 2D model here. There's a little bit of noise here outside. Let me quickly close the window. Sorry. So this is results from our model. Here you can see what happens in our full model when we apply a 3D translation or a 3D rotation to the objects. As you can see now, this car here translates through the scene realistically, and in this case, it rotates around its own axis. So we have full controllability over these 3D factors, and also we can rotate the viewpoint or the camera here around the scene, as you see here, or we can lower the viewpoint, as you see here. There's also a little video. I hope this plays well. So this is the first example from the layout to IM baseline, where you can say the identity switches on this simple car data set. And this is the result of our 2D baseline, where you can see that the rotation cannot be controlled. Here's the results of our full model, where we can either translate objects. So these are 4 different instances, as you can see. So we translate in different directions. We can rotate the objects. We can rotate the camera around the scene. Or we can change the elevation of the camera. Here are some results on this flying furniture data set, which is much harder, of course, because the background appearance is much more complex. And here are some results on this fruit data set. I mentioned before that there's multiple options for this 3D primitive representations, and we consider in our experiments several variants. So first of all, we consider a point cloud that's rendered onto the image using these Gaussian spheres that are projected onto the image. Here on the second column, you can see the alpha map color-coded based on the 3 objects that we project, and you can see the final image reconstruction. We also compare a cuboid representation where we directly project the 3D cuboids of the primitives into the image, and then in this feature map encode in the channels the different features. And then we have a sphere-based representation where instead of these cuboids, we model 3D spheres. We found that there's not a big difference in terms of the performance of these 3 different representations. What we can see here is the FID. This is the Frege inception distance. So a lower score means higher image quality. And on top, you'll find the result of the vanilla gun, the 2D gun approach. What we also have is the FIDT and FIDR measures, which are basically computed after random rotation and translation of the objects, which somehow measure the disentanglement capabilities of our model. And here, finally, the FIDI measure is the Frege inception distance for single objects that are generated, which should also look close to rendered images of single objects, where you can see a slight improvement of the sphere-based representation. But in general, we have similar FID scores. So the precise form of the 3D representation seems to be less relevant than the general concept of joint 3D, 2D representation for this task. We also compared to a representation where we represent the entire scene now with a single primitive. We don't have multiple primitives, but try to represent the entire scene as a single primitive. And surprisingly, the FID score goes further down, but of course, we cannot represent individual objects anymore. Furthermore, we can see that now the number of objects is entangled in the representation. So for instance, if we rotate the scene, then at this point here, the red car disappears. And what we also did just as a simple benchmark is to use a textured mesh representation where we don't have the 2D convolutions, but directly project this mesh using standard differentiable rendering techniques into the image domain, and then learn the parameters of this mesh such that it produces realistic textures. And this leads to much worse FID scores, as you can see here, caused by the fact that meshes are just a very difficult representation for deep neural networks to output. I also want to show you some failure cases of this approach. Here you can see failure cases on the 2 most challenging data sets in our evaluation, the fruit and the flying furniture data set, where in the first case, if we move to the right here in 3D space, both these objects here move simultaneously and slightly change their shape. So multiple objects have now been represented by the same primitive. On the bottom, you can see the rotation of the camera, which causes this bench shape to change to a chair shape. So there's a little entanglement of object identities happening here. So what we were also wondering is, well, these results were nice, but they were pretty simplistic still. And what is needed to go to more realistic setups? Is there actually a better 3D representation for 3D controllable image synthesis? Going back to single objects first. And this is actually very new results. So one famous work from last year that also tackles this aspect of 3D controllability is Hologun, in this case for single objects. where the random code is sampled and generates a 3D feature volume that is then rotated and projected, followed by 3D convolutions and 2D convolutions, which I call neural rendering here, in order to render an image. This gives relatively high fidelity images and leads to some disentanglement, but in our experiments, in particular for large viewpoint changes, it doesn't lead to consistent 3D models. And we quantify the consistency that we get by applying CalMap to the reconstructions of the model. So for the same appearance code, we generate multiple viewpoints, and then we apply a standard structure for motion and multi-view stereo pipeline to these results and see how the point cloud looks like. Another baseline that we consider for this work here is Platonican, which is similar to Hologan, except that it doesn't have any learnable rendering part, but it directly tries to predict a colored 3D voxel representation followed by a differentiable rendering that has no learnable parameters. Now, because it doesn't have any learnable parameters in the rendering, it's multi-view consistent by definition. However, because this is just a very hard task, it leads to low image fidelity and has a relatively high memory consumption. Therefore, also the reconstructions from the multi-view stereo algorithm don't look very compelling. And so this is the approach that we are proposing here. It's built on some recent model that has shown that neural radiant fields are actually a good representation for novel view synthesis. So we want to build here a generative model for these radiant fields. This is a continuous representation that's multi-view consistent and is able to, as we found in our experiments, produce high image fidelity with relatively low memory consumption. The general idea is illustrated here. So again, we sample a random latent code, and then we have this radiance field that maps from a 3D location. So it's a neural network that maps from a 3D location and a relative viewpoint direction to a color value and a density value. And then we can use volumetric rendering techniques that don't have any trainable parameters, but they can evaluate basically these continuous density fields at arbitrary resolution to yield images of arbitrary resolution. Now, if we do this and train this model, we can obtain results that are much higher fidelity, but also by definition multi-view consistent, as evidenced here by the CalMap reconstruction. So here is a brief overview of this approach. Because this is a continuous representation, we cannot simply sample all the pixels in the image. That would just be too memory intensive. That's why we have what we call a patch generator and a patch discriminator, similar to a patch gun, but with dilated patch versions. The advantage of this is that the patch discriminator can be a standard 2D convolutional network, which is efficient, while the patch generator can generate these patches with arbitrary dilation factors in order to reach better and better quality. In practice, we use patches of size 32 by 32 pixels, but sample random scales during training. So what goes into this generator here are the camera intrinsics, the extrinsics, as well as the scale parameter for this patch. And then this fully determines the 3D rays that correspond to the pixels that are active in this patch. And then for this ray, so this is this outer box R for rays, we can then sample these rays along the ray in this 3D space. So we get these 3D points that go into the radiance field. That gives us, for all of these 3D points that are lying on that ray, for this particular shape and appearance latent code, a color value and a density value, which we can then render volumetrically onto the intensities or the color values actually of the pixels of the patch. And then we can compare this predicted patch to real patches that are sampled using the same sampling strategy from real images. So here are some results of this model. What you can see here on top is images generated from cars where this model was trained in a fully unsupervised fashion on a car data set with unposed images. We also automatically obtain depth maps, which look quite nice. You can see rotations of the model. You can see interpolations in shape and appearance space. It also works to some extent on faces. So get quite nice depth maps here. But still, you can see these common gun-like artifacts. Okay. So the question is, what's next? Well, one thing we want to definitely do is we want to have this model operate in the real world. Most of the results that you've seen so far were produced using synthetically generated images. Now, how can we lift this to the real world? And one particular project I want to show you here at the end is a new data set that we are creating, where we are also going to apply these ideas now. And this is called the Kitty 360 data set. It's basically the successor of the Kitty data set for self-driving. The difference to the existing Kitty data set is that this data set has now semantic annotations in the form of 3D bounding boxes and per 3D point and pixel semantic information for all the frames. It's actually a data set that we have been working on for quite a while, since 2016. But as you know, the last 10% often takes most of the time. So we are just releasing this data set this summer. We have an overall driving distance of 70 kilometers with 2 frames of a forward-facing camera actually, and 2 frames of a fisheye camera. And then we have also a new laser scanner. So in addition to the Velodyne laser scanner, we have a push-broom laser scanner that gives us a bit better coverage. Furthermore, we have everything geolocalized. So we have the accurate GPS coordinate for all the frames. And then we have semantic labels consistent with the cityscape labels for 19 classes. And we have instance labels for buildings, vehicles, pedestrians, traffic signs, and other classes, which are importantly consistent across all frames of the sequence because we have labeled this in 3D. So here you can see some examples from this data set. You can see a 3D point cloud here on the left, some bounding boxes that we have annotated, the corresponding semantics. So we have an algorithm that derives from these bounding boxes the semantics of the 3D points and the pixels in the image, as well as the instance information. Here you can see how this projects into the image. And we also created a little teaser video, a little cinematic trailer, if you will, that I want to show you now. I hope it plays reasonably well through this Zoom session. And I hope you can hear the sound also. So we'll release this data set this summer, and I hope that this has also it provides also as a valuable resource for research in localization and mapping. So that's all from my side. I want to thank you for your attention. Also want to point out our blog page if you're interested in our research, and I want to thank our sponsors for supporting our research. Looking forward to your questions if you have any.
Thank you very much, Andreas. Yeah, it's a bit weird, right? It's tradition to do this, but it's a bit weird if there's only one person. Yeah, very cool. We will see whether people have questions on YouTube. There's a bit of a time delay, but let me start with questions maybe. I very much like this idea of the radiance fields that you talked about. One question is, how do you scale this up, going from like small controlled scenes to urban scenes, something kitty-like? Do you have any ideas there?
That's, I guess, really the question here. So I don't have a good answer to this.
Yeah.
I mean, first of all, these radiance fields are representing the appearance in 3D space using a very simple, fully connected network architecture. And that's not something that can scale up easily. So one thing that we have done recently is we have proposed a convolutional version of these implicit representations that can scale to higher resolutions. And we think that this can also be helpful maybe for these radiance fields, and not only for things like occupancy networks or sign distance fields. So that there will be something. But then, like, building a generative model is always harder than building a discriminative model. So yeah, so that there will be, as you could see, like the results that we obtain, even the results with these radiance fields models is not on par yet with a discriminate version of it that works on a lot of images and can produce very high resolution novel view synthesis results.
I was wondering whether maybe there's actually an answer from the computer graphics community who have been building like scene representations or data structures of scene representation for years, right? Whether we should go back to that.
Yeah, that's interesting. I think like these representations that they are building are made typically for designers. So yeah, they are not so easy to work with from like a perspective of continuous latent space generative models. But I think there's exciting work along these lines also to build recurrent networks or something that can maybe also build these type of models. Yes, but I think that's a good point. Yeah, we should probably look more into these, like what Pixar uses or Disney uses for creating their movies.
Yeah.
Do people on YouTube actually, can they join this Zoom, or do they have the option to chat, or how does it work?
What they can do is they can ask questions through the chat, and we will relay that to you then.
Ah, okay. I see. I guess it's also pretty early in US.
Yes. But we have a couple of questions. So Jim asks, what does the ideal end goal look like? Do you want to be able to create scenarios with just textual descriptions? How about particular details like vehicle A overtaking vehicle B at time T?
Oh yeah, that's a good point. So we haven't looked at time yet because just modeling space is so hard. And for time, the problem is that even the data sets are missing. But we have some data sets. So for instance, we have Carla now, where we could, at least in simulation, create a lot of scenarios that are maybe good enough for these generative models. So it's definitely something we are interested in and we'd like to do at some point. The question is, what is the end goal? Yeah, so the end goal, like the ideal end goal for me would be to have a system that can like go like a system like the kiddie car that can be driven through the environment, or an indoor system that can scan the environment, that may be equipped with expensive sensors, but that doesn't require any supervision in terms of annotations. And then there's an algorithm that builds a simulator of the real world, where you have space and time, and where you can replay interesting scenarios so that you can validate and test and train intelligent systems. I think that would be the end goal, and that you can maybe, you know, if there is situations that occur less rare in the real world, such as like in the case of self-driving, where you have collisions more rarely on video, then you could change your simulator such that these collisions happen more frequently and you have more observations of these rare events.
Another question that came up is, do you have any thoughts on how these representations may be used in SLAM maps? What are the current limitations?
Yeah, as I pointed out in the beginning, I mean, this is an interesting question. I think there's no definite answer to it. As I showed in the beginning, I like very much these object level representations, and I think one fundamental limitation of these approaches is that they require a lot of supervision in the form of scanning 3D objects and so on. So if you have a model that can automatically decompose scenes, I think that will be very valuable, because this can lead to very compressed maps, right? You don't need to store millions of local key point descriptors, but you can just store what's relevant. And you can, like, if you have objects that reoccur throughout the scene, like you're driving through a city, you have many houses that look alike or many cars that look alike, and that can be described by just a few bits difference. Or you walk indoors where you have like a lecture hall with a lot of chairs that are all like each other. You need much less bits to actually represent that scene compared to representing that scene using an actual landmark-based kind of classical SLAM map.
That sounds great. Looking forward to the first SLAM systems that actually do this.
Yeah, we are quite far from that.
Yeah, but I mean, that's why we do research, right? To get there eventually. One question regarding scaling radiance fields. So there are two big differences between networks trained on cars and foods and networks trained on Kitty. One is realism and complexity, and the other one is resolution. Which one do you think is more difficult?
I think both of them are I mean, okay, so resolution is, in our case, is just given by definition, because we can just query the radiance field at any resolution. But that doesn't mean, if you have a high resolution image, that doesn't mean that you get a lot of details, right? Which you probably would refer to by realism, right? So I think the resolution aspect, that's more a compute and memory aspect now. But the real challenge is to integrate the realism, in my opinion, because the real world is really complex and there's a fractal structure to it, and there's a lot of high frequency textures in the real world, and there's a lot of effects that are really hard to model, like lens flares and transparency and smoke and hair, and there's a lot of these things that are just very difficult to model. And so first of all, like, just because we can model these cars doesn't mean we can go to more complex image manifolds, and the real world is much more complex. And then there's all these artifacts of the imaging pipeline that also need to be considered. So I think the realism is really the hard nugget here, and the rest will come with computation and better engineering of the models, probably. Oh, if the chat says if I have time, I can go to. Oh, this is after the talk. So there's a channel where we can continue interacting. Okay.
If you want. One question is, do you think it's simple to cover domain shifts? I think that's a follow-up on what you just said.
For which part do you refer to now?
That's not fully clear from the question. Giovanni, could you maybe?
Okay. Well, I mean, if you build a generative model, then the generative model is built for a certain domain, and that's the domain that you cover, right? So there's no such thing as a domain shift in a generative model per se. But domain shift is an important problem if you now wanna use this generative model in order to train a downstream task in order to then apply it to the real world. But I think that's exactly where the benefit of this generative process is, right? So if you look at a lot of the simulators that people use for pre-training their models and then trying to deploy their models in the real world, they observe a huge domain gap. Now, if you would have a way of making these models more realistic by learning more data in a data-driven way, then you could potentially overcome some of this domain gap at least. That is at least the hope, I think, of these generative models, yes.
Another question is, for the current kitty odometry datasets, there are some time synchronization issues between IMU and Velodyne, which is only up to 10 Hertz sync or so, which is not suitable for multi-sensor-based SLAM and VAO systems. For your new dataset, do you provide high-frequency synchronization of IMU with image and LiDAR data?
Yes, that's a good point, actually. So we have all that data and we should really provide it. I will just make a note that we also do. Yes, so we should provide that. The data on Kitty, I think, is not necessarily wrong. It's just low frequency, and we interpolate between the timestamps, right? So we take the real timestamps and then we shift the measurements, because there is no synchronization per se. So the RTK measurement device is not synchronized. So the way the synchronization works in Kitty is that we have a little read contact that reads when the laser scanner is in a certain position. And then when that read contact reads, and that's typically when the laser faces frontally, then the cameras trigger. So those are synchronized with the laser pointing in a particular direction. But then there is no possibility to synchronize this, at least we didn't have a possibility to synchronize this with the OXT box. So we need to rely on the computer for synchronization. So there might be still small time gaps, but at least we can provide the original stream also with the GPS timings of what the OXT provides. I mean, that's what we can do, but we don't have any, unfortunately, that's hardware limitation, right? We don't have any real electric synchronization between the GPS and the LiDAR, unfortunately.
Thanks. Maybe one final question, which is the clarification of the domain gap question, which is generating images is cool and very challenging, but then systems have to work in the real world. How to train on virtual data and then use it on real data?
Yeah, I mean, that's again, that's the classical domain gap question. So I think this, thinking a bit more abstractly about these generative models can also be seen as bridging the domain gap when you have already simulated data, right? So you wanna make this simulator more realistic, right? That's also one line of work is looking into that problem, and I find it very exciting. So for instance, you could take a simulator that has some assets where the textures are maybe not photorealistic and maybe the arrangement is not photorealistic, but now you can take what the designer has done and take reconstructions of the real world, for instance, the Kitty data set or some data set that we have created, and then try to match the distribution of that real data set to that synthetic data set, or the distribution of the synthetic data set to the real data set, both in terms of the geometry and maybe time, the motion of the objects, as well as the appearance of the objects, right? So that's maybe one way to go about it. And apart from this, of course, there's all this work on domain adaptation. My personal take on this is that there's still a lot to be done in domain adaptation, because what we often see is that domain adaptation works well in the low data regime, where we have maybe, for downstream tasks, we have maybe 100 or 200 annotated images, then we can still outperform. But as soon as we have 1,000 or 10,000 annotated images, then the current domain adaptation techniques are not really helping that much. And that's really unfortunate, because that's the domain where we're really interested in, because for real problems, we often have the ability to annotate at least 1,000 images. And so I think there's a lot to be done. Yeah, thanks. Great questions all.
Yeah, thank you very much for the great talk. I think there are still a couple of questions. If you want to answer them on the YouTube channel, then please feel to go ahead. There were also some very enthusiastic reactions on the video for the new dataset that you showed. Just wanted to let you know. But yeah, thank you very much for the great talk. Very much appreciated.
Thanks, Thorsten.
Okay, so moving on to the next talk. So it's my pleasure to introduce Victor Prisacariu, who I think it was 2 years ago that I had the pleasure of working with him at Oxford for my postdoc. So a few words about Victor. So he got his PhD at the Activision Lab in Oxford, where he focused on methods for using priors in 3D reconstruction and tracking of objects. After spending some time as a postdoc, he became an associate professor at the University of Oxford, where he co-leads the AVL. Also, he co-founded 6D AI, where he was a chief scientist, where the startup worked on things related to the AR cloud, such as large-scale mapping and localization. And after the recent acquisition of 6D from Niantic, he's now a chief scientist at Niantic. So welcome, Victor.
Well, thank you very much for the intro. I'll share my screen now with the slides. Is everything visible properly? Just to double check.
Yes.
Yes, it works.
So hello everyone, I'm Victor, as Vasily says, and I'll be talking about some of the work we've done, mostly in the lab, on correspondence networks for matching and relocalization. One way of doing relocalization with correspondences, and there are many others, but one way to do it is to say that you have some sort of database of frames that you've built a priori, you've been somewhere, you filmed around, and then you have a new query image. And you have some magical way of finding the closest image from your database to that query image, where closest is something we would define somehow. And once you have the image pair, you pipe them through some sort of feature extraction, feature matching, and then you take the matches and you use them to give you a pose. Correspondence networks take the two blobs in the middle, namely the feature extraction, feature matching stage, and capture them as a neural network. Both the feature extraction and the feature matching will be dense. What this means is that I will extract a feature for potentially every pixel in the image, and then I will match every feature that I've extracted from one image with every feature that I've extracted from the other. The original approach for using neural nets for this sort of correspondence networks was NC network, neighborhood consensus network, and it looked or worked something like this. So you'd use a neural network to extract dense features from your input images. Then you would take these features and build them up into a correlation tensor C. And this is a rather big one because it's a 4D correlation tensor, which is something like width by height of image 1 times width by height of image 2. And at each location, you're going to have the probability of that specific match being valid. Then you would pipe this correlation tensor through your magical neighborhood consensus network, and you'd get a filtered tensor at the end. And if you were to take the points of maximum probability or maximum value within this tensor, you would get the actual matches. Another important thing here, another interesting thing is that this was trained in a sort of very weakly supervised way by just using positive and negative pairs of images. Now, the first work that I'll be talking about today is one that we have in the CVPR. It's called the NCNet, and aims at tackling sort of three potential, I don't want to call them problems, but the three potential improvements on ANCNet. First one is multiple matching candidates. You might end up with, or in many cases, a certain point will match to multiple points in your target image. You're going to have a scale or a viewpoint difference between your target, your source, and your target images. And ideally, especially when you look at SLAM, you would probably want to have the ability to do slightly more informed training. So ideally, you would use something that you can extract easily and automatically from the images, such as, say, sparse point matches. So let's start with the first part. And let's look at the standard sort of approach, NCNet. What this one does was that you take your two images, you extract features, and you use cosine correlation to build your correlation tensor. One of the things we added was another pipeline that works the same way as the feature pipeline, but this time encodes self-similarity. So we take the features, say the features from the source image and the feature from the target image, and we build SS and ST, the self-similarity features. And then these go through the same sort of correlation, cosine correlation, and build our target correlation tensor, but now in terms of similarity. The self-similarity module looks sort of like this. So you take, for each point in your feature map, you take the points around it, locations around it, you compute the cosine distance, and then you put all of these into your coarse level or self-similarity as 0. And then you do 2 more convolutions to distribute context a bit more, and you concatenate them all into a single feature S here. Once you have both of these correlation tensors, CF and CS, so one built for features and the other one built for the self-similarity, you can add them up, and then you pipe them through the adaptive neighborhood consensus, our equivalent to the NCNet. NCNet was sort of worked like you see on the left here, so it was a rather simple collection of 5 by 5 by 5 by 5. These are 4D convolutions. What we've added is another pathway through this network that uses non-isotropic kernels, so 3 by 3 by 5 by 5. The whole point here is to add a bit of robustness to the scale difference between the two images. Finally, the more interesting bits is how would we train this? Previous methods like NCNet trained using weak supervision, so positive and negative images. Ours is also weak, but is less weak. So we're using matched key points. If these are semantic classes, you'd have to manually label them. These would be like the various parts of birds from one of the more famous data sets. But in a relocalization scenario, these would be feature points from the structure for motion or SLAM that you'd be able to project into the corresponding two images. Now, the loss has 2 aims in our case. The first one is that we want the peaks in our correlation tensor to actually project to key point location in the 2 images, S and T. So if you have a point of high probability in your correlation, that should correspond to feature location or to high probability of being meaningful points in your pair of Z images. The other thing we would care about our loss is that we should only have at most a 1-to-1 match. So each final feature point from one image should correspond to at most 1 feature point from the other image. It might correspond to no feature points because that specific part of the image might have disappeared, but you do want to have at most 1 match. So when you build the loss, it looks sort of like this. The key component here is the matrix M, and this is very simple. It is just a slice through your correlation tensor where you've taken the specific slices that correspond to your key points. And then the final loss has 2 components. One is looking at making sure that the positions of the maximas in your correlation tensor match the locations of the key points in the image. And the other one is what we call the orthogonal loss, and this comes from or is inspired by graph matching, and this aims at encouraging uniqueness. A few results. You see on the left is the result for dense matching. And you see the source image, for example, the top you have a Renault and a Mustang there, and you see that NCNet does a good job, but ANC, at least in this case, tends to look probably a bit more realistic. I mean, neither of them really looks realistic, but ANC tends to look a bit more like you'd expect. And the same for the dog and for the couch. On the right, you see an example of sparse key point matching. So here we want to match the leg of one dog with the leg of a different type of dog. In green, you see the ground truth, and in red, you see the prediction of the method. So you see that we take the green from one, and our method does well. The other ones do fine, but not as well. Now, obviously, anyone can find pretty pictures to show results for, but we're also doing reasonably well quantitatively. So we're able to get effectively state-of-the-art data results on the approaches that existed at the time of submission. So this approach, the ANC, basically looks at dense correspondence estimation, and it's trained with sparse key points. And it works well because of those three, or collection, I'm going to call them hacks, but collection of net changes to the network. But what about relocalization? Well, ANCNet, as it is, uses a lot of memory. Uses much more memory than NCNet because it creates a separate pathway, and it effectively doubles the amount of the size of the correlation tensor because it uses the one for self-similarity. So when we actually started to use this for localization, we saw that we were only able to fit small images in our GPU. So there wasn't enough RAM to fit big images. And this was before sparse NCNet, which is another approach, was introduced. And interestingly enough, we found that the higher resolution the feature map, the better results you'd get for relocalization. So for example, to get state-of-the-art at the time, in relocalization data sets, NCNet would use an input of 3200 by 2400, and this would generate a small feature map of 200 by 150. ANCNet would have been using the same type of input, but would have needed even more memory. So the second approach I'll quickly walk you through today is dual RCNet. And this is a network architecture that aims at outputting higher resolution feature map with hopefully as large GPU requirements as if you weren't as NCNet. And it works effectively by adapting the feature pyramid concept both to the features, as people have done before many times, but also to the extraction of the correlation tensor. And the way it works is that we start with a standard feature extractor backbone, sort of like that, and then we run NCNet on the coarses resolution of the features. You could also use ANC or any one of your favorite approaches for correspondence. There are a few others that I didn't mention here, such as sparse NCNet, for example. At the same time, we're also going through a feature pyramid, a network that extracts or builds high resolution features, as shown in the middle of this slide in blue. And this is why we're calling this a dual resolution feature generation. The next step is to then figure out what are the points in the low resolution correlation tensor that are likely to be good matches. So you only select the ones with high scores, and then we only upload the ones with high scores. And then similarly, for the location of high scores, we're also building score maps. But we're building these ones from the higher resolution feature maps built by the feature pyramid network. So what we end up at the end is with two correlation tensors, or two sets of slices through the correlation tensor, one coming as a simple upsample from the original NCNet, and the one being computed from the high resolution feature generation. And then you multiply these, and that is your final output. It's a rather simple approach, but it turns out that it works really well. So here is on a few results on Inloc, and we are able to, we were getting state-of-the-art on this, including when compared to sparse NCNet, which is an approach that I think is 2 months old, which popped up after we had started work on this, and we're still getting good results. Of course, no paper would be complete without us trying to sort of shame the authors of the state-of-the-art. Obviously, there are very good results in both sparse NCNet and ours, but here are a few examples where ours behaves better. Similarly, we look at the Aachen day and night data set, and here we get competitive results. We're as good as sparse NCNet in some cases, or better than sparse NCNet in some cases, or good as sparse NCNet in some other cases. And as before, we are able to generate nice-looking matches. Some conclusions on dual RCNet. Feature size, or feature image size at least, matters. And you can take these sort of coarse-defined approaches that you've done in feature pyramid networks and adapt them to the same sort of correlation network, and it gives you very good results. So, and this sort of the first sort of chunk of my presentation, I showed you sort of two approaches for getting state-of-the-art-ish results for feature correspondences, ANCNet and dual RCNet. ANCNet combined the various tricks and hacks to get better results, whereas dual RCNet just aimed to increase the resolution of the match. But both of these methods are not very quick. They both take a few seconds on a good GPU. And even sparse RCnet is still looking, a sparse NCNet, which is sort of a simplified version of NCNet, also looks at 1 or 2 seconds on a GPU. So how can we take these methods and apply them sort of in a more scenario where Niantic is interested, as in things that run on mobile phones? Well, we can do similar stuff. I won't exactly explain how that works, sadly, but I will show you a few videos and demos. So here's an example that some of you might have already seen. The video is, here we have a mobile phone, and I'm moving around the Department of Engineering Science here, and I'm building a depth image. So this is entirely monocular, and is building a depth at each frame. It takes about 15 milliseconds per frame. And you see that it is able to obtain, let me scroll back a bit to here. It is able to obtain sort of nice reconstruction of the space. Then I can walk around a bit more, and I'm able to build another reconstruction. So I can just commit to the same, and I can actually go all the way and close the loop in this case, both indoors and outdoors, and I've built a nice dense map, again, entirely on a mobile phone. But the demo that I haven't shown much so far is that we can also use this for relocalization. So you can upload it to the cloud, and you can download it to the device, and then you can relocalize in it. So, and you can also see annotations that people have done on that specific map. So here I'm walking to a map that I've uploaded before. I'm relocalizing relative to that map, and I can show the position of the mobile phone in that specific map. And now, and hopefully I have, yes, I still have a few minutes. I will try to demo this. And this is the first time I do a public demo over Zoom, but hopefully this will actually work. So I will stop my screen share of this, and I will instead share my mobile phone. So here I have my mobile phone. I am hopefully, yes, hopefully everyone can see my mobile phone. That's my kid. You're going to see his toys soon. So we can start with the first build that I showed you, how to build a map. So here's, you see the live stream on the phone, and I can move around, and I'm reconstructing live, and I'm building a 3D map. I'm going to walk to the other side of my house. Excuse the mess, but when you have a 4-year-old in the house, things are not entirely stable. Neither are his parents after a while. So I'm able to build this reconstruction. I can tidy it up a bit. This is the sort of reconstruction I was able to build. And this is nice, but it's a bit nicer if we can use it for relocalization. So here I'm starting the other app, the relocalization demo app. And I am going to create a new reconstruction of this, and I'm going to call this CVPR20. And I'm going to scan. So here I'm doing the same. The child is about to come barging on. I'm doing the same sort of reconstruction I did before. There. And I'm uploading it to the cloud. It's piping it through the cloud mostly for cleaning up textures. So now it's doing some texture cleanup on the cloud. It's giving it down. It takes about 14. You see on the screen share, it takes about 11 seconds. I'm waiting for this. Finish. Okay, so now after this is done, it's going to download it from the cloud. And you see, so it's a much smaller reconstruction than I did before, but it's sort of see it looks. Now I can put a note here somewhere. Let's move this note so that it looks like it's sort of on top of the couch there. And I can relocalize. So now it's going to download the data that I'm using for relocalization. And then I relocalize. So this entire localization ran on device, and I did it live right now. I can do another one. And the symbol is still there. Another one. So this one. All right. It usually runs like that. Now, another fun thing you can do with an AR cloud is to share your map and should give it to other people. So what I'll do is another phone. And now I will stop sharing from this phone, and I will start sharing from my other, from my other phone, and that's my other phone. So now I'm going back to my map, and I am sharing it to my other mobile phone. So now the map was shared through magical Apple, as it takes a second for it to pop up. This is updating, and now I'm downloading the second map. And if all goes well, after the rather slow download, I should be able to relocalize in the same world. Apologize for the speed of my internet. So that's the same map as before, and we can see the node. And now we can relocalize. And it's there. Another fun thing we can do, let's see, hopefully this works, is I'm going to relocalize with the other device. I'm going to put it there. And I don't know how this will work very well. Okay, let me put it there. So I still have my other device, and it's there. So I can go and see where it is. And all of this is sort of transmitted live on the device. Anyway, enough with the demos. The same sort of, thank you very much for appreciating the cleanliness. This is running the same sort of approaches as the sort of stuff I showed before, but optimized in different ways because you need to run these on device. Well, thank you very much. Magically, I was a bit quicker than I expected.
Thanks, Victor. So this is a virtual clap. So yeah, first of all, we have people claiming that it's not that messy for your house, and a lot of impressed comments about the demo. So yeah, if anyone has questions, there's a bit of a delay due to the YouTube stream, so I can start with one. So you said that these things are based on the same methods. You somehow try to make them faster to.
Yes, I will. So the one thing I can say is that they're both using neural nets and they're both using concepts related to the stuff I presented before, but simplified in a way that will run in 100 milliseconds on a mobile phone.
Okay, yeah, that's because normally when you have things like 4D correlation maps, or you have two big feature maps and then you try to match everything with everything, it becomes very messy, I guess. At some
Do you
point.
really have to match everything to everything? That's
actually related to something else I want to ask. So you said you want to enforce either 0 or 1 in terms of it has to match at most 1, or it doesn't match at all, right?
Yeah. So
how do you? There are probably many ways to do the 0 when you don't have any match, because you might have two completely different images, or you might have an image that is included by something else. Let's say, is there any difference between these two approaches, or is it the same?
If you were to force a 1-to-1 match, you would just say M times M transpose minus identity equals to 0. So that would say that I have to have at least when I'm matching something against itself, I will have to have a 1-on-1 match. So you'll end up with an identity there. Now, if you say that some of those can be 0, then suddenly you're allowing it to match to nothing. So if you do M transpose minus M transpose with the ground truth, then you're basically saying I want the sort of self-correlation to be the same in between ground truth and non-ground truth, which means I should only have at most one sort of self-correlated. No point should correlate with others. That's basically what you're saying, or have 0.
Yeah. Okay, so we have a question from the YouTube stream. What are the privacy implications of this sort of system that you showed now?
It's complicated. We're spending a lot of effort making sure that, or making sure, again, a strong word. We're doing our best to send stuff that is not, that doesn't violate privacy, because this is running through proprietary neural nets that have had some effort to keep private. We're hoping that this will hopefully alleviate some of the privacy concerns. That being said, as it is, all the demos that I'm showing assume that everything is public. And of course, this will change at some point if this was to be developed further, but I cannot speak for the company on this.
Okay. Yeah. Next question is, have you seen Magic Leap's CPR 2020 superglue? Because it's similar ideas, feature matching, and they also have a demo. So how do you think it compares with the machine learning based feature matching you were showing?
Oh, we didn't compare. We compared with the super pixel. So before the super glue one, and we were drastically better, but I've seen them improving it a lot. So I think it's actually an interesting thing that we should compare against.
They were probably submitted at the same time, I guess, because
exactly. So when we were comparing with super, the super points, it was certainly better, but the super glue it might be.
Okay, next is, can you talk a bit about the scalability of the system? How much latency comes up with the increasing map size?
So it ends up borderline to, it goes up to a fixed amount and doesn't increase past that. The current tests show that we can run relocalization within 100 milliseconds on device. I don't want to say regardless of the size of the map, but with something the size of my house. It'll be within 100 milliseconds. After that, you have to do other tricks and hacks, which I can't comment on. But I would certainly hope that the ultimate aim is for it to always run within 100 milliseconds for a relocalization attempt. Whether that will actually be achieved in product, God only knows. But as it stands, we're sort of aiming for that.
Okay. Yeah, we'll have time, I think, for a couple of more if you also have the time.
That's fine, sure.
How do you deal with textureless areas with this kind of system, like white walls and occlusions around the object boundaries?
So one thing I can say about relocalizer there is it's not just 3D to 2D. So it would also look at 3D to 3D matches. So as long as you have some version of a surface there, you're likely to be able to relocalize. Now, if you don't have any surface at all in the reconstruction, and that can happen, then you'll be in trouble. But as long as you have some sort of surface, it would still work. You've seen the sort of Kinect style relocalizers that are able to relocalize even if there's nothing there.
Yeah. So I think the next question is related. What are the failure cases of the network? So
the biggest problems, I would argue, are still sort of day-to-night transitions. So when stuff doesn't look the same, and that means that obviously you can do things, you can build up the ways of compensating for this, but at some point things will just not look the same. You might have built your map now and you're coming back a month from now and at night. So the images are going to look different. The 3D is going to look vastly different. And we're doing some interesting work in the lab that will hopefully be published, first submitted and then accepted, that is looking at eliminating as much as possible the influence of furniture and of everything that can be dynamic and still being able to relocalize. But I would say that's the main limitation, is that the world changes and it is more susceptible to change than a human would be.
Okay, for running on mobile, I expect the train model would be light. Do you have any suggestions for keeping the models light on mobiles? Someone is asking from YouTube. Any generic tips?
So if you look at some of our other papers, I tend to like quantization. We've had a paper in last year's ICCV on quantization that showed good result. It was called DSConv. I also like the typical sort of mobile things, and we have some papers in ECCV which may or may not get in on training network architectures and looking at varying group size. This one's on archive, so you can tweak group sizes. You can optimize. So depth-wise is great, for example, for making mobile inference quick. But you can also improve accuracy by using group conv, and this is a paper that is on archive now and may get in ECCV. Yeah. So I don't know of any sort of magic bullet for this, but I do like stuff like the network architecture searches from Facebook, for example, FBNet, and the sort of quantization that would get stuff running quickly. But most of the time, I think the most important thing is custom code and common sense. If you're building your code for your specific application, you're able to extract a lot of benefit. But if you're going to try and make it generic for everything, it'll be slower.
So it's a mix of quantization, custom architectures, and custom code.
Yes. Yeah. These demos use entirely our own neural network pipeline with everything is implemented by hand.
Okay. Yeah. Next question is there are three different systems: standard mobile phones, then the iPad with a new LiDAR depth sensor, and full-fledged AR systems like HoloLens or Magic Leap glasses. How does your system USO compare with these systems?
So our system, as I said, one of the things that it uses is the sort of 3D to 3D relocalization, which means that the moment you give it a good depth image, it will behave even better. So it's in a way compatible with all three. You can have a headset that gives you a depth image and you can relocalize. I can't give examples, but back in 60 days in fact, I can give examples because it was public. Back in 60 days, we had a collaboration with Qualcomm where we were able to localize the headset from Nreal to the reconstruction map built on a mobile phone. So I would say in an ideal scenario, you would want a system that is compatible with all three. So you want to relocalize your phone in the map built by Magic Leap or in the map built by an iPhone. So you want all of that to work. So you have to worry about compatibility, even across mobile devices. One of the important things of our system was that so first of all, it worked between two different phones, and it actually works between two different phones, a different type of different capability, and that's something that doesn't just naturally happen. So as long as you're aware of this and you work towards it, ideally you would end up with a system that unifies all three.
Okay, yeah. Next question is, how do you deal with bad mappers? For example, if the map was built by someone inexperienced without good multi-view paths, I guess, or tracks, is there any magic trick there, or you just cannot build them?
I would say that's more of a work style. There's more of a style of development that you should do. One of our main aims is to make our life as hard as possible. So we've always tried everything we test on to be as realistic as possible. And sadly, some of it is still filmed by a computer vision scientist. So I think, unconsciously they're going to hold the hand straight. But we're certainly doing our best to make the videos as hard as possible. So it is something that you have to do when you're building a system like this. You have to ensure or assume that the person filming will not have a PhD in computer vision. So we're now how to actually solve for that. That ends up being robustness in the training and neural nets. That ends up being having robustness in the sort of computer vision component. But I would think it's much more important to assume that you will have to solve it and not make your life easier by filming all the videos yourself. So it starts with making sure that you're using the correct video to test on.
Yeah, I think there are no more questions, so I can say again that
I actually have a question.
Oh, yeah.
I very much like your comment. Great talk, first of all. Very much enjoyed it. Thanks for using our data sets, by the way. I like your comment about robustness and not being able to rely on having someone with a PhD to take the data sets. So are you planning to make some of the data that you capture available for other researchers to actually get this effect?
So from my personal point of view, and this is in no way, from my personal point of view as an Oxford associate professor, yes. But this ends up being a company decision, so it's not something I can speak for. But I would really like to.
Cool. Yeah, that would be nice. Thank you very much.
Okay. Thank you again.
Okay.
Okay. Good. So the next point on our agenda is actually the challenges. I guess I have a couple of more minutes, so than I had originally planned for. So I will present a few more slides than I had originally planned. Give me 1 second. Okay. So as part of the workshop, we had this challenge on visual localization in changing conditions. So what we essentially wanted to figure out is how robust are our algorithms when we capture a map under one condition and then try to relocalize under different conditions. More precisely, we had 3 challenges. So one was the autonomous vehicle challenge, where we provided 3 data sets: the extended CMU seasons data set, the robot car seasons data set, and the SILDA data set. And I'll show talk a bit about the data sets in the end, where you actually have images captured from something like a vehicle, where you have image sequences that you could actually use for this. We are going to have two talks here. The first one is the first place in the challenge by Martin Hummenberger and others, who present their work on robust image retrieval-based visual localization using capture. And the second place is by Unaga, Lindenberger, Celepidis, and Salin on 6DOF pose refinement via sparse to dense feature metric optimization. The second challenge was on handheld devices. So rather than having sequences captured from a vehicle that moves on the ground, we actually had images captured with with mobile phones that can undergo complete 6DOF motion, and where we actually have only individual images. So here we have two data sets, the Aachen day-night data set and the InLog data set. And here we are again going to have two talks. The first one is by Zarlin and others on superglue learning feature matching with graph neural networks. I think this is actually a CVPR paper this year. And the second one is by Fan and others on visual localization using semantic segmentation depth prediction. And the third challenge was the local feature challenge, which is only done on one dataset, Aachen day-night, where we're actually only using the nighttime images. And the idea here is that we wanted to isolate the impact of different feature detectors and descriptors on localization performance. So what we do is we provide source code for a simple localization pipeline, which does feature matching between a predefined set of images, then builds one local 3D model for each test image and tries to localize that model against this local model. And for this, we actually have code online if you want to use it. Here we have one winner, which is Zalin and others, Superglue, learning feature matching with graph neural networks. And we actually have two second places, which ended up with identical scores, Lu and others, based on two papers, learning local features of accurate shape and localization, and learning two-view correspondences in geometry using order-aware network. And the second one is Revo and others, R2D2 repeatable and reliable detector and descriptor. I think this paper was presented last year at NIMS. The way that we handled the challenges was we have this benchmark server at visuallocalization.net, where you upload a text file with image names and the 6DOF poses that you computed, and the server does the evaluation. So the ground truth poses are actually not public. So you just submit the results on that website, and then typically a few minutes later you get results. As an additional rule, we had the rule that there should be either paper or archive technical report that had to be available shortly after the submission deadline, so that we could verify what was done. In terms of the evaluation, so for each data set, we have multiple conditions. So what you see here is the Aachen day-night data set, and the first column is essentially the percentage of images localized within 25 centimeters and 2 degrees of the ground truth. And then the second column is percentage of images localized within 0.5 meter and 5 degrees, and so on and so on. So we get multiple numbers per method and per data set. And the way that we combine them is we consider this as, we use the Schulze method, which was originally designed for a voting problem where voters can vote for candidates. And essentially each voter produces a preference for candidates, which is a list where you say, I would prefer this candidate over this candidate over this candidate, and so on and so on. And then this method tries to find a global ranking that preserves those relative rankings. In our case, the voters are the different conditions. So for example, night at the highest precision threshold that we're looking at, and the candidates are the methods. So we use this method to get a global ranking. For the data sets that we used, we have the Aachen day-night data set, where which is a 3D model built using daytime images, and we query with relatively high quality nighttime. The model was built using daytime images. We query with relative high quality nighttime images, which were taken with a mobile phone and software HDR. We have the extended CMU seasons dataset, which is based on a dataset that CMU captured 9 years ago by now, where we have seasonal changes and a bit of illumination changes, and we again build a model under one condition and then provide test images taken under different conditions, so different seasons. There is the robot car seasons dataset, which is based on a paper by Will Maddern and others from 3 years ago, where they captured Oxford over a full year. And we use one of those runs a day to build a reference model, then have runs at different weather conditions. So we have rain, different illumination conditions, dawn and dusk, and so on. And also nighttime images. And this one is much more challenging than CMU and Aachen in the sense of there's motion blur in the images, especially at night. We have the SILDA dataset, which was captured by Scape Technologies and the Imperial College of London by essentially traversing the same block in London under different conditions using a wide field of view camera. And finally, we have the indoor dataset, INLOC dataset, which is an indoor dataset which captures 2 floors of a university building. That's the University of Washington in, don't fully remember where. So it's an existing data set, and which provides panoramas and depths that are registered onto a floor plan, and we captured additional test images a year or so later. So, and again, you have illumination changes, you have changes in the scene. So it's a pretty hard data set, especially since some of the regions are very weakly textured. I want to thank the sponsors that helped us make the challenges work. So that's Apple, Facebook Reality Labs, Microsoft, and Niantic. So big thanks to all of our sponsors. And we have one announcement to make, which is that we're going to run the challenges again at ECV this year. So we're currently planning for a submission deadline around August 15th, and the workshop will be taking place on August 28th. And since ECV is virtual, the workshop will also be virtual. If you want to know more, you can have a look at the workshop website. And I will also put the slides up on the workshop website later. Okay, that being said, we can start with the talk for the first challenge. That would be Martin Hummenberger presenting the winner of the Autonomous Driving Challenge. Martin, the floor is yours.
Hello, everybody. Can you hear me?
Yep.
Good, then let me share the screen. Can you see my screen as well?
Yes.
Looks good. Okay, so thanks a lot, Torsten. So hello, everybody. My name is Martin Hummelberger. I'm with Naval Labs Europe, and I will present our work for this year's Visual Localization Challenge, which is entitled Robust Image Retrieval-Based Visual Localization Using Capture. This is joint work with a couple of colleagues from Naval Labs. In detail, Johan, Nicolas, Julien, Jérôme, Philippe, Noé, César, Vincent, and Gabriela. So, Naval Labs is an ambient intelligence technology company owned by Naval Corporation, which is Korea's leading internet content service company. Naval Labs Europe is based in Grenoble and is the biggest industrial research lab in artificial intelligence in France. In the next 10 minutes, I will first briefly talk about the concept and methods of visual localization. I will introduce our method. In detail, I will present our image retrieval and local feature extraction methods. I will present the achieved results, And finally, I will introduce our new data format and computation pipeline, which we call Capture. Visual localization, as you know, addresses the problem of estimating the position of the camera using images. In comparison to GPS, the estimated position can be more accurate, and we can directly compute the camera's orientation. And furthermore, as we just saw by the impressive demo of Victor, it also works indoors. A lot of great work has been done in the last years in the field of visual localization in order to overcome challenges such as illumination changes, viewpoint changes, or any other changes between the reference and the query images. These slides should provide a brief overview about very relevant work in the last years. We believe that especially image retrieval-based methods are very interesting because they offer an interesting opportunity to combine data-driven and geometry-based approaches. As a result of that, they provide the basis for our method. So following the traditional pipeline, our method consists of two main parts. The first, our mapping part, computes a 3D representation of the environment, and the localization part computes the precise position of the camera in this map. And we implemented all these steps in our processing pipeline, which we called Capture. For mapping, we first select pairs of similar reference images using our global image features AP-GEM. Then we compute pixel-wise correspondences using our local feature extractor R2D2. And finally, we use CallMap to compute the 3D reconstruction. For localization, given a query image, we first retrieve the 20 most similar reference images using, again, AP-GEM. Then, given these pairs, we compute pixel-wise correspondences using R2D2. And finally, given the resulting 2D, 3D correspondences, we use CallMap to compute the 3D pose of the query image. Let me now explain more in detail let me now give you more details about the used global and local features. And I will start with AP-GEM. So AP-GEM stands for Average Precision Generalized Mean Pooling. And the method was published at ICCV 2019. And we have models and code available on our website. For deep image retrieval, usually a CNN is used to extract a feature map that is aggregated into a compact fixed length representation by a global aggregation layer. And this representation is first projected with a fully connected layer and then L2 normalized, so images can be efficiently compared using the dot product. The motivation of this work is that state-of-the-art methods in deep image retrieval rely on loss functions that minimize a proxy instead of the true metric used during model evaluation. And we argue that optimizing for the true metric leads to significantly better results. Thus, instead of using the triplet loss, which is not guaranteed to be aligned with the ranking metric, we propose to directly minimize the average position for a large number of images. And for more details about AP-GEM, I would like to refer to our paper. As mentioned before, for local pixel correspondence analysis, we use our local feature method R2D2. It was published in NeurIPS 2019, and again, code as well as models are available online. As you know, the one quality criteria of key points is repeatability. It is often used to find good key points, and it tells us how well a key point can be detected at the same location across different viewpoints. R2D2 revisits the question of what is a good key point by introducing reliability as additional criteria for feature extraction. Reliability essentially tells us how well a key point is suited for the task of matching. Here's the architecture that we propose to estimate repeatability and reliability densely at each pixel. At the end, we only keep locations that are both reliable and repeatable. And here's how we train the network using image pairs with ground truth pixel correspondences. For repeatability, we minimize the cosine similarity between detector responses in two corresponding patches. And for the joint reliability and descriptor loss, we maximize the average precision computed for each query patch, weighted by the estimated patch reliability. For more details about the losses and the training procedure, please again refer to our paper. Let's now talk about how our image retrieval-based method performs on the visual localization datasets. Since we are looking for a robust method that performs well under different circumstances, we did not change the method, training data, or any parameters across the datasets. Let me start with the datasets from the autonomous driving task. The final consolidated ranking can be found on the website, and here I will use the official benchmark for comparison. So on robot car seasons, we rank first out of 47, and our method performs particularly well on nighttime. On extended CMU, we rank 4th out of 30, and on Silda, we rank 3rd out of 10. For all datasets, whenever possible, we utilized image sequences and the multi-camera rig configuration to interpolate and to complete missing poses. We also ran our method on the datasets for the handheld localization challenge. So on Aachen day night, we rank 4th out of 55. And on InLog, we rank 28th out of 35. The results on InLog clearly show the limitations of image retrieval in such indoor scenes. And note that we did not change our workflow, which means that we did not follow the proposed InLog localization pipeline. Considering our experiments with the presented datasets, we can summarize the following findings. Most importantly, using a list-wise loss is beneficial for the task of visual localization because it enables to train the networks directly for the task at hand, using a large amount of samples in the loss function and without the need of hard negative mining. This is one reason why R2D2 and APGEM perform well. And structure-based methods provide a good way of combining machine learning with geometry, which also increases robustness. And we think that there's more potential in utilizing image sequences and multi-camera rigs. And of course, situations where the environment dramatically changed, for example, caused by snow, still are an interesting challenge for image retrieval. Finally, let me introduce capture. So during our work on visual localization, we often face the challenge that many datasets are provided in different formats. This does not only mean that data importers and exporters need to be adapted, it almost always means that coordinate systems or camera parameters need to be transformed as well. Furthermore, if you want to use a combination of multiple methods in a single pipeline, a lot of data conversion is needed. In addition, even if there are great tools like OpenMVG, as we heard yesterday, or CallMap available, the provided data formats did not include everything we needed. For example, we wanted to use Wi-Fi data or other sensor data. And that's why we created Capture, and we hope that it will facilitate research and development in visual localization, structure for motion, VSLAM, but also in sensor fusion in the future. So now let me give you more details about Capture. So Capture is a versatile and extensible format for structure for motion and other data. It's a set of converters between many popular formats. It's a set of tools, for example, for merging data sets or for evaluation and visualization of localization results. It also contains a Python library, which can be used to load, save, and manipulate captured data. And this library can be used to create new converters and custom processing pipelines. As an example, we will provide a mapping and localization pipeline based on CallMap, where you can either use CallMap SIFT features or you can use your own custom features and matches. And more functions will follow, which will complement existing tools. Capture will be released soon on GitHub under the BSD license. And we also plan to release a rich set of capture data from many popular datasets. And of course, we know that researchers who already work on structure for motion or VSLAM or visual localization might already have implemented their own toolset. But on the one hand, we hope that capture will still be interesting for researchers already active in the field. And on the other hand, we hope that it will actually attract new researchers. So this brings me to the conclusion. I presented our robust image retrieval-based visual localization method, which utilizes global features APGEM and local features R2D2. Using a single method, we report very good results on a set of quite different data sets. And I introduced Capture, a versatile data format to facilitate research and processing and visual localization structure of motion. We really hope that this will have a positive impact on the community to provide even more data sets and algorithms. And finally, I really would like to thank the organizers of this great workshop and the interesting challenges. This really is an inspiration for many researchers in the field. This concludes my talk, and thanks a lot for your attention.
Thank you very much. Just to bridge a bit of the time before there are questions on YouTube. I very much like the capture format. Do you plan to provide pre-trained data sets, so to speak? So will you convert like the data sets from the challenge into that format? Yes,
exactly. So that's, sorry, I need to modify. I don't see myself. Anyway, yes, thanks for this question. That's one of the main reasons actually we decided to release this format open source, that basically ideally all public visual localization data sets should be available in the same format, and that it's really easy to process them. And in particular, to your question, yes, the plan is to actually release all the data sets where we have like the rights for in the same format, that you just need to basically download this Python library and you're ready to go. Yeah, let's talk a bit about this after the workshop, because we can see whether we can host it together with the official data sets if there's interest from your side. Of course, that's very much. And if we're not running out of disk space. Okay, so by now we have a couple of questions online. So what is the real-time performance of R2D2? So R2D2 is, we extract it on multiple scales. And if you extract like all scales, which means, I don't know, 4 or 5, 6 scales, then on a good GPU, it's probably between 2 and 3 seconds per image. But if you reduce it, so in the code you can see that you can reduce the image size, and you can get it down to less than a second. Any did you, as a follow-up question, did you try to play with the architecture, like do model compression, things like this, to try to see whether you can push the limit there? So in terms of making it smaller and faster, we didn't do a lot yet, to be honest. We're currently working on, I mean, we are constantly running experiments with slightly modified architectures, training data, and we actually also achieved even better results than we could submit to the challenge at the end. But nothing was really yet consistent across all the data sets. So we decided to wait till we're really sure about this. But no, we haven't done anything in particular to make it faster or smaller. A question from YouTube. What approaches do you think could help improving indoor image retrieval performance? Yeah, that's a good question. And that's actually a question we ask ourselves a lot. Initial experiments we did by combining multiple global features were actually quite promising. Again, nothing really consistently working across all the data sets was found yet, but we plan to investigate in this direction, to combine multiple global features in a way that they like the combination of many is better than each individual. If we would only like to stay with image retrieval based methods, right? I mean, there are other ways of improving this with like including more geometry, for example. Thank you very much. Yeah, thank you very much for the very interesting and nice talk. Thank you. Oh, wait, there's actually
two more questions. So maybe we do one of them. Is the weak performance in global descriptors for indoor cases mainly due to the fact that they are usually trained with outdoor data? I think that's actually an interesting question.
Yeah, I mean that's what we assume as well. I mean, there's in indoor you always have also the problem that like slight orientation changes might completely change the appearance of the image. But for example, APGEM is trained on Google Landmarks, and yeah, so that certainly is a problem. Yeah. But we will actually further investigate this.
Great. Yeah, thank you very much again.
Thank you.
For the next talk, I think we're actually going to have three speakers: Ayak, Kumar, Philip, and Nikolaos. Yeah, the floor is yours.
Hello, thank you. Let me just start my screen. Okay. Yeah. Welcome everyone. I'm going to present our work on 6D pose refinement via sparse-to-dense feature metric optimization. This work was in collaboration with Philip, Nicholas, and Paul, and we are master students at ETH Zurich. Our approach for this challenge was to look at the current approaches, find their limitations, and try to improve on top of it. For example, it's well known that sparse key point matching is not repeatable. So rather than that, we use the sparse to dense feature matching, which was proposed recently. Another problem with the learned descriptor and learned features is that they are not well localized in the pixel space. So we are trying to do pixel level feature metric optimization, which can improve localization errors without any additional training of the features. At the end, we will present our results on robot car and CME. Let's start with the sparse feature matching. It's a well-known approach where we detect key points in reference and query images, and we try to match them. However, the problem with this approach is when we have a large illumination changes, for example, here from day to night. Even well-known descriptors like superpoint and hypercolumn, they are not able to get good number of inliers to find the good pose. Another problem, which is with most of the learned descriptor, is that they are not well localized in the pixel space. For example, as you can see here in the top right image, we have reference key points, detected key points, and in the bottom right image, we have the matched query points. And if you can qualitatively see, the points are not matching well. The small pixel error, however, can result in large error in the pose estimate, as we can see in the left column. So recently, Germain et al. Proposed an approach called sparse to dense matching. Here, you detect points only in one image, for example, reference image, and you pass it through off-the-shelf trained image retrieval network, and you get your features. However, for query image, we don't do any detection. We just pass it through the network and we get the dense descriptors. Once we have the sparse and dense descriptors, we do the matching. Basically, we do the correlation map and we find the corresponding match. However, the same problem with this approach is that it's not well localized. The reason is that the output of the network would not be at the same resolution as the image. So as we can see here, the points in the left, where we have well localized corner points is the reference image, but in the query image, we don't have well localized points. That's what we are focusing on. We will try to improve that with this approach. Also, recently there has been some approaches which use feature metric based optimization in different applications like multi-weather relocalization or bundle adjustment. The common thing between these approaches is that they use multi-scale features to apply this feature metric optimization. We observe that in our network also we have multi-scale features. For example, if we take S2DHM network and pass the query image, our early layers are very sharp and our deeper layers are very smooth. So the smooth layer can maybe help us get the higher radius of convergence in optimization, and this sharper layer will help us achieve the pixel level accuracy. We observe the same thing when we look at the correlation map. For example, here we have a reference image, query image, detected key points, and correlation map. Now, if we zoom in, we can see that our correlation map have a gradient. And if we are a bit off from this gradient, for example, these blue points, then we can use the optimization to guide that point to the optimum. And based on these ideas, we define a method called feature metric based PNP optimization. Here I will detail it. So we have a 3D structure points, for example, capital P, and we have a projected reference point, small p. Using this, we can already define our reference feature map from the reference features from a reference feature map FR. However, for query feature map, we'll have to start with some initial estimate of our query pose. So we start with some initial estimate, we project 3D point on the query image, and we find corresponding query features. Once we have reference and query features, we define the error between them as a feature metric error. Our optimization will try to minimize this error. We are here using Levenberg Marquardt methods with the squared error loss formulation and iterative optimization. However, interesting thing to note is that this TQ cannot be arbitrary pose. Because we have a limited radius of convergence, we need some good initial estimate. So we initialize T with the PNP plus ransack. Now let's look at this in the qualitative manner. So first, main benefit of working in feature space rather than intensity or pixel space is that we can use optimization across changing condition. So for example, from day reference, we can do optimization on night query as well. Here, as we can see, if we start even with some wrong pose, our optimization guide all the points to their corresponding matches. Even as we can see, point movement is also pretty large, which shows that we have a good enough radius of convergence. Another way also we need to look if our feature metric error is actually decreasing. So for example, here we show the feature metric error heat map for the points marked in the colored boxes. We can see most of the points are going towards their minima, except for some points which are in ambiguous regions, like for example, black sky or the tree. Also, however, with the small movement in the key points, we can have a very large movement in camera, which was our first point, that even with the small movements, small improvements in the key point location, we can have a large improvement in localization, as we can see here in the right image. Next, we can see that after the optimization on the right image, after the optimization, our key points are on the right location than before optimization. Another metric to look at is the number of inliers. So we compare the number of inliers before optimization and after optimization, and we get more inliers in cases when we apply optimization rather than using the original PNP plus ransack pose. Now let's look at some quantitative results. So we use this method on robot car dataset with S2DHM features. First, we use off-the-shelf given S2DHM features with their layers, and we apply our feature metric PNP on top of it. Here we find improvement in most of the threshold except for some threshold in daytime images. However, when we use the combinations of different layers, as in earlier layers and deeper layers, in those cases, we find improvement in all the cases, and this improvement is very strong in the lower threshold, but we have a medium decrease, medium increase in some medium thresholds. Nevertheless, this approach seems to work for all the threshold in the robot car dataset. However, for extended CMU, the story is a bit different. Here, our feature metric PNP didn't improve the results. But we use the different hypercolumns than what S2DHM paper proposed, and it needs a bit more investigation. Let's look at the pose change. So after the optimization, our pose should change a bit. So here we show that after the optimization, our robot car pose change around 0.45 meter and extended CMU change around 0.2 meter. This explains the performance increase in the lower threshold than the larger threshold because it's a local optimization and we can't converge if the original pose is very far from the actual pose. So in summary, we present the feature metric error optimization based on sparse to dense feature matching. We use the idea that features have a gradient, and you can use this gradient to do the optimization and improve your current localization without any additional training. This approach works very well on at least robot car, and it performs state-of-the-art on night-all sequence. We will have our code and report on archive in next days. Thank you for listening.
Thank you very much for the nice talk. I think we have time for one or two questions. And so maybe I started off with, so here you're doing the
Yes.
sparse to dense matching, right? Can you think of a way of taking the lessons that you learned and lead for training better sparse to sparse features?
Yes, so this is where the next part will come in. Basically, we can, there are methods, there's BNet, right? And also the GNet loss. That's what they do basically. They use this, you can use the loss itself to guide your feature training. And this will, in response, will generate smooth gradients and smooth features, which can be used for sparse to sparse matching as well. But plus you can optimize on top of it because they are smooth.
Yeah, that sounds good. Let's see whether there's still one question on YouTube. Do the other organizers have a question? Well, so there's one question on YouTube. Is it possible to directly optimize the camera pose?
We are optimizing camera pose, but we have to define some kind of metric for it, right? So here we use a feature metric error, and we don't have any ground truth camera pose. So no, we just use the feature metric error as a surrogate metric to optimize for our camera pose.
Okay, thanks. Yeah, then thank you very much for the great talk.
Thank you.
And for participating and for submitting.
Yep.
Actually, there's one short question. Maybe you can answer this. What might be the reason why the proposed approach does not perform well on the CMU dataset?
Multiple reasons, I guess, but one that we thought of was that we used a different layers than what S2DHM originally proposed, and we didn't tune anything on the S2DHM approach. Like we didn't tune our optimizer at all. So while working with it more, it should become much better, I guess.
And maybe one final question in terms of runtime overhead. How much does your optimization introduce in terms of computational?
Optimization is fast because it only depends on how many points you have, how many inlies you have. But it might take a bit more time in terms of, because you'll have to store the dense descriptor to get the gradients, right? So it might take some more memory, but in terms of runtime, it's pretty fast.
Okay, great. Yeah, thank you very much again.
Thank you.
Our next speaker is Paul Edouard, who will present the first place in the Local Feature Challenge. The floor is yours.
Thank you. Let me share my screen. All right. Can you see my full slide?
Yes.
Perfect. Then let's start. So hi, everyone. My name is Paul Edouard Solin. I am a PhD student at ETH Zurich, supervised by Mark Polyface. And I will now present our winning entry to the local feature challenge based on our paper, Superglue, Learning Feature Matching with Graph Neural Networks. This work was carried out at Magic Leap as my master's thesis in collaboration with Daniel Detone, Tomasz Malisiewicz, and Andrew Rabinovich. So Superglue is a deep neural network that performs feature matching. It reached the first place in actual 2 visual localization challenges. One is the local feature challenge, which is specifically evaluating image matching for day-night localization, and that will be the topic of this talk. And the other is the challenge for handheld devices, which evaluates a full indoor-outdoor localization pipeline. So I will describe our pipeline in a later talk scheduled in about 25 minutes. And for now, let's see how Superglue works. So Superglue combines the best of 2 worlds: deep learning with graph neural networks and classical optimization with optimal transport. It is a deep middle end that estimates matches between local features into images while rejecting unmatched points. As you can see here, it can successfully match image pairs with extreme baseline in real time. And this results in state-of-the-art pose estimation with both classical and learned features like superpoint. So let's first look at the typical 2-view matching pipeline. First, key points are extracted, actually detected in each image independently, and the corresponding descriptors are extracted. So this can be done with classical methods like SIFT or learned ones like superpoint. These features are almost always matched by lookup of nearest neighbors in the descriptor space, which is naive and often prone to failure. So then incorrect matches are filtered with heuristics like the ratio test, or recently with deep network classifiers that operate on sets. And finally, a relative pose is computed by a robust estimator like RANSAC. So in contrast to these, our Superglue jointly performs context aggregation, feature matching, and filtering in a single unified architecture trained end-to-end. And the ability to leverage context, particularly global context, is critical in situations that exhibit little texture or extreme self-similarities. So in this checkerboard example, local descriptors are really not sufficient to correctly match most corners, while knowledge of nearby and distinctive objects like this book can disambiguate all difficult corners. So our deep matcher takes as input local features extracted from 2 images, and each composed of key point coordinates, confidence, and a visual descriptor. Each key point can be matched at most once, and some will be unmatched due to occlusion and failure of a detector. So we seek to output a soft partial assignment matrix. Superglue is composed of 2 blocks. First, a graph neural network processes the appearances and positions with powerful attention mechanisms. It encodes contextual cues and priors into deep features, and it reasons about the underlying 3D scene. These deep features define the cost of a partial assignment problem, which is solved in a differentiable manner. This produces the desired partial assignment, enforcing thus the domain-specific constraints. So let's look at the architecture in more details. We first combine the local visual appearance and the position into an initial representation using a multi-layer perceptron, this MLP here. For each key point, this representation is iteratively updated using information from other key points, either in the same image or in the other image. And we can actually see the 2 sets of key points as nodes of a complete graph with 2 types of edges, what we call self-edges and cross-edges. So we thus use a kind of graph neural network called a message-passing neural network. At each layer, the state of each key point, its deep representation, is updated using a message computed from the self or the cross-edges, depending on the layers. So for a given layer, the aggregation along these edges is performed using self or cross attention. And this is akin to a soft database retrieval of values corresponding to entries with keys similar to a given query. And it's implemented as a simple weighted average of the values, with the weights being the similarity between the query and the key. And the queries, the keys, and the values are computed from the current states of the key points via linear projection. So since the state we've seen encodes both the appearance and the position, a key point, here tile, can query its spatial neighbors that are nearby, self-similarities, or other cell-in key points anywhere in the image. So self-attention, we've seen aggregates information from key points in the same image. It can, for example, attend to distinctive key points to disambiguate self-similarities. On the other hand, cross-attention enables inter-image communication, attending, for example, to candidate matches. Together, they define a soft graph that is data-dependent, sparse, and interpretable. So the final states are called matching descriptors after a few attention layers, and the dot product defines a score matrix representing the affinity between key points in the two images. And because of occlusion noise, some key points, of course, cannot be matched. So we add a dustbin by augmenting the score matrix with a new row and a new column with constant value, what we call the dustbin score, Z. And the score matrix is the cost of an assignment problem solved with the Synchron algorithm, which iteratively normalizes along the rows and the columns, and we get a soft partial assignment from which correspondences can be extracted. And we train that end-to-end in a supervised manner by simply maximizing the likelihood of ground truth correspondences, which we can get from ground truth poses and depth maps. So we trained first a superglue on indoor scenes with superpoint local features, and our deep network consistently predicts more correct matches in green here and fewer mismatches in red than existing classical and learned approaches. Interestingly, we also train another superglue for outdoor scenes using structure from motion. And we observe the same striking superiority to classical here and to learned baselines. So in our paper, we evaluate relative pose estimation with different local features, both SIFT in blue and superpoint in red. And we see that superglue consistently yields large improvements over classical heuristics and recent deep networks for both indoor and outdoor environments. So when it comes to the local feature challenge, it runs on the Arendt's dataset. The first step is to triangulate a 3D model with the daytime images. Here we use superpoint features, and we see that superglue yields a denser model than the vanilla nearest neighbor matcher, with overall 10% more observation per 3D point. And this difference is particularly striking in areas that have many self-similarities. We can, for example, look at this brick wall. And here we see that superglue matches all key points well at both day and night times, which requires the aggregation of a large context that superglue has. For the localization task, superpoint originally lags behind new learned features like D2net or R2D2, that's superpoint. But superglue provides a big boost of performance and makes superpoint competitive. It's hard to say whether it's truly better than the other challenge entries, given that the benchmark is a bit saturated and the ground truth pose is inaccurate. But superpoint plus superglue reaches such performance with 2 to 10 times fewer key points than other approaches. And this is due mostly to the higher repeatability of superpoint four corners, like windows and tiles, which are prevalent in man-made environments. So that results in a smaller 3D model and a lower memory footprint. If you want to learn more about localization with superglue, do not miss the second part of this talk, which will focus on how to integrate superglue into a complete pipeline for indoors and outdoors. We'll see practical tips and why superglue works. That starts in about 15 minutes. If you have specific questions, you can attend the 2 Q&A sessions on Wednesday. And lastly, superglue also won the image matching challenge this year, and I'll present our winning entry on Friday morning during the other workshop. So that's pretty much it. In the meantime, you can check out the paper, code, and slides on our website, piersolin.com/superglue. And if you have any questions, I'm happy to answer them. Thank you.
Thank you very much. It was a very interesting talk, and thanks for pointing out that the Aachen data, the local featured benchmark is a bit saturated. We'll have an updated version of this with what we believe are better ground truth poses at EC. So
yeah, I'm very excited about that.
And well, let's see where this goes. There's a couple of questions on the chat. I have one question. So I think it goes back to the 90s or so, the idea of using neighboring features to disambiguate matches.
Yep.
Did you compare against any of those classical things? So there's a lot of literature on this also in image retrieval for fast spatial matching and so on.
Yes, there's some literature, mostly from the late 2000s, something like that. Nothing really recent and really kind of first easy to use and easy to evaluate, and second, nothing that is widely used. So we've seen GMS in the past years that kind of helps when we have very dense features. So we have some evaluation against that in the paper, and GMS is really not competitive with SuperGLUE.
Yeah.
But
GMS reinvents something that was reinvented in the 90s, that was reinvented in the late 2000s, that was actually invented in the 90s.
Yeah, I guess these are very old ideas, and it's interesting that we still don't have an easy-to-use handcrafted method that can actually leverage these cues.
Yeah. Okay. Thanks. Let's go through a couple of questions from the YouTube chat. One was, by using GNN, self and cross attention is required, but it looks like using CNN instead of GNN is also possible to do a similar thing. Do you think GNN is better in this problem?
So we use GNN, and for the context aggregation, we use attention. There are other methods to compute this message that we've seen previously, and these could be, for example, building a k-nearest neighbor graph, something like that. But we basically need a way to define some graph. And in our case, attention allows to learn this graph in a soft manner, which is we don't make any assumption on the structure of the problem, and I think that helps a lot.
Okay, maybe one more question. Do you consider all possible pairs of features when building the graph? If not, how do you select which features to connect in the graph for both self and cross attention?
That's a very good question. So we indeed use all the features. We assume a fully connected graph. And at each step, we either run the self edges or the cross edges. But basically, the union of the self and the cross edges define a complete graph. So that's indeed a bit expensive, and that's a bit memory intensive. So that's one of the limitations of a current approach. And I think there's a lot of potential to improve on that, using sparse attention, using sampling, so that we don't need to compute all these relationships. Because especially in the later layers, only a few key points are interesting to the network. So there's a lot of waste in compute. That's a very good question, and I think there's a lot of potential for that.
Great. Maybe one final short question. Do the weight of superpoints also get updated when you train SuperGLUE?
So in most of our experiments, we kept superpoint frozen so as to enable a better comparison with previous works. But we actually have some evaluation in our paper where we backpropagate through the descriptors of superpoints. And so we do that on ScanNet, on the indoor model, and we actually see some improvements by optimizing everything jointly. These are very initial experiments, and I think there's a lot of optimization to be done there to better train them end to end. But that at least everything is differentiable, so that's theoretically possible.
Okay, great. Yeah, thank you very much for the great talk.
Great, thank you for these questions.
And there's a lot more questions on the YouTube chat, so if you have some time, feel free to answer them.
I'll pass. Thank you.
Next talk is by Sichin. I think you wanted to.
Yes. So, hi everyone. So this is Jing, and first of all, I'd like to thank the organizers for having this fantastic workshop. Now I have recorded a video for this presentation. So in case of any network instability, And we will meet you later in the QA session. Okay. Yeah, thank you.
Can you hear the sound?
Nope. Yeah, that was my concern. I'm not sure.
I think if you reshare your screen and at the pop-up window, you can check the box. One box is saying share the audio or something.
Yes. I'm currently trying to figure that out.
Can you stop the sharing and reshare the screen?
Sure.
And
yes.
If you see the pop-up window, there's some checkbox at the bottom.
Wait, where? You mean, yes. Okay. Yep. Figured it out. Good. Things are a bit slow.
Still cannot hear the sound.
Okay. So if it doesn't work for you,
SLFit, which jointly learns local feature detections and local feature descriptions. We use its original model, which is trained on GL3D dataset, and select up to 10K key points and perform only single-scale detection. We have observed that the learned key points or dense feature extraction frameworks are in particular helpful regarding large illumination change. However, inconsistent conclusions can be drawn in the image matching workshop regarding large perspective change, which indicates that there still exists potential performance gap between handcrafted key points and learned key points. After local feature extraction, we apply OANet, which is a learning-based outlier rejection method for feature matching. OANet is separately trained on FTC dataset, consumes a set of putative matches that survive the mutual check, and rejects those matches whose confidence scores predicted from the network are lower than 0. As a result, we found that a learned outlier rejection is consistently beneficial for different learned features, such as context desk or ASLFit. As shown by superglue, more potential from an end-to-end feature matching method can be expected. Next, I will briefly go through the methodology of ASLFit. In this paper, first, we address the importance of estimating accurate local shape of key points for improving the geometric invariance. More specifically, we resort to deformable convolutional networks to densely predict and apply local shape transformation. Furthermore, we compare different parameterization of deformation and study what deformation is useful for learning invariant features. Next, we address the importance of key point localization accuracy for solving the geometry. More specifically, we adopt the hypercolumn representation and perform a multi-level detection to recover the low-level geometric structures and restore the spatial resolution accuracy. Meanwhile, we compare different network designs to explore the efficient way for feature fusion. We base our methods on D2Net framework and apply aforementioned modifications, namely deformable convolutional networks and multi-level detection. We optimize the implementation with other minor changes, such as a peakness measurement and an adaptation of advanced loss formulation. We thoroughly do ablation studies and extensively carry out experiments on image matching tasks. Structure from motion, image retrieval, visual localization, and dance reconstruction tasks. The empirical results show that our methods have delivered remarkable improvements upon the state of the art. Thank you for your attention.
Hi, this is Jiahui from Tsinghua University. I will give a brief introduction to OANet, a learning-based outlier rejection method presented in last year's ICCV. Here we focuses on the two-view geometry estimation problem, which is, given a pair of images, we estimate the essential or fundamental matrix. We construct putative matches by using shift or other learned local features. Then, to obtain accurate relative post-estimation results, we have to find these outliers. In this paper, we'd like to use a network to distinguish the outliers and inliers. One of the challenge is how to capture the local context for the putative matches. This is non-trivial because they are sparse and unordered, and our solution is using learned clusters to capture the local context. Here is an overview of our architecture. The input of the network is image coordinates of putative matches, and the output are inline probabilities and EF matrix. We use a unit-style architecture. The core of the network is the differentiable pooling and unpooling operation. The differentiable pooling layer clusters input nodes to a cursor representation by learning a soft assign matrix. Matches fall into the same cluster are learned neighbors. The network can capture local context by this clustering process. The differentiable unpooling operation can be simply seen as a transposed version of differentiable pooling layer. Besides, we show that these clusters obtained by the differentiable pooling layer are in canonical order, which means we can capture the relation between these clusters by using more powerful operations, such as fully connection layer between clusters. We extensively conduct experiments on several benchmarks. Our method can outperform previous handcrafted methods and learning-based methods. It works best when using ransack variants as post-processing. Besides, we also test the network's generalization ability on 4 different datasets, which shows our method generalize well and outperform both traditional method and learned method in these benchmarks. Thanks for your attention. You can check out our code on GitHub.
Thank you very much.
Yeah, thank you.
I think we have time for one question. If there is something from the audience. Otherwise, I have a short one. Have you thought of jointly training OANet with ASL feed?
We haven't tried that because OANet is quite memory consuming. Also for AS feed, the input to ASL feed is like 500 by 500 images. So it's also quite high resolution for training. And we also suspect if it is useful to propagate the gradient from OANet to the local feature module. So we haven't tried that due to those limitations. But I don't know, if we have better hardware devices, we can definitely try it out. Yeah.
Okay, great. So in the interest of time, we will move to the other second place finisher for the local feature challenge. If you still have questions, please ask them on the chat. And Sichin, if you have time to answer them, that would be great. Otherwise, yeah, thank you very much for the great talk. And I give the floor to Martin, who's going to present R2D2.
So thank you. I hope everything works. So this is Martin Humenberger again, and from Naval Labs Europe, and I will present our work R2D2 now a little bit more in detail than before. R2D2 is repeatable and reliable detector and descriptor, and this is joint work with Jérôme Revaux, Philippe Weinzäpfel, and César de Sousa. All right. First, I will present the problem we're interested in, and this is about finding pixel correspondences between images. And the classical approach is to first detect key points at scale space locations to the locally salient, or as we say, repeatable. And then for each key point, a patch is extracted and encoded into a compact descriptor. As you know, the most famous key point detector and descriptor is SIFT, and it's still widely used. And then finally, descriptors are compared between the two images. And when two descriptors are very similar, it means we have a pixel correspondence between the images. And the resulting set of pixel correspondences can be used, for instance, to recover the camera pose. In practice, however, the key point matching often fails. And we believe that one reason is that existing approaches only consider a single quality criteria when extracting key points, when that's called repeatability. And repeatability is of course important because it means that the key point will be detected at the same location across different viewpoints. In this work, we claim that there is one more essential quality criteria that should be taken into account, and we call it the reliability. It basically tells us if a patch is good for feature matching. This distinction between repeatability and reliability is important because patches can be repeatable without being reliable. For instance, in repetitive structures. To summarize, in this work, we would like to revisit the question, what is a good key point? Here are some examples to concretely illustrate the difference between repeatability and reliability. The first key point is obviously neither repeatable nor reliable. This one is very repeatable as there is a high corner response in the center, but it's not reliable due to the repetitive pattern. We formally measure reliability by searching for the closest key point in the descriptor space and then checking the difference compared to the original one. In this case, the nearest neighbor is almost indistinguishable from the original one. This one, on the contrary, is not repeatable since there is no salient structure at the exact key point location in the middle of the patch, but it is reliable as the most similar patch in the image is still significantly different. If you look at the boats, you can see that. And finally, here is a key point that is both repeatable and reliable, and this is exactly what we're looking for. So let me present the architecture that we proposed to estimate repeatability and reliability densely at each pixel. And so at the end, we only keep locations that are both reliable and repeatable, even though we estimate it densely. As we saw, reliability depends on the key point descriptor itself. So our network also computes the descriptor at each pixel simultaneously. And here's how we train our network. We feed it with image pairs, and for each image, the network computes descriptors, reliability, and repeatability at pixel level. Each image pair is annotated with ground truth pixel correspondences. They can be either generated synthetically by applying random transformations to an image, or they can be sampled from, for example, structure from motion datasets, in which case we compute the ground truth correspondences using conventional optical flow methods. Our network is trained from scratch using two different losses. The first one for learning discriminative descriptors jointly with an estimator of the matching reliability. In detail, we maximize the average precision computed for each Berry patch, and we weight it by the estimated patch reliability. And the second one is for predicting repeatable locations in the image. Here in detail, we maximize the cosine similarity between the detector responses in two corresponding patches. To summarize, with R2D2, we make three main contributions So first, we introduced the notion of key point reliability at extraction time, which we show is well complementary to repeatability. Second, we introduced two novel losses tailored to learn these confidences from scratch and without introducing any bias. And third, we demonstrate state-of-the-art results on tasks such as image matching and visual localization. Last but not least, the code is online on our GitHub. Thanks, that's it. And thanks again to the organizers for the workshop.
Thank you very much. In the interest of time, I think we have time for one question. Actually, I guess since there were actually so many questions asked on the YouTube chat on R2D2, maybe we skip this. But maybe, so do you have any, one short question, do you have any improvements on R2D2 planned, something in the pipeline that we can look forward to?
Yes, of course. That's something we are heavily working on improvements. We are investigating multiple ideas about changing the architecture, including more or less invariances, but also using other training data, more structure for motion models. So we're investigating many directions, and we hope we can provide an update soon. And let me say one thing. So together with our data format capture, we also think about releasing some extracted features for popular data sets, which should make even a comparison to other methods easier.
Great. Yeah, looking forward to that. Thank you very much for your talk.
Thank you.
And I hand over to Paul Edouard, who will give the second part of his presentation on superglue and superpoint.
Great. Thank you, Thorsten. Let me share my screen. All right. Can you see my full slide?
Yes.
Good. Thank you. So hi, everyone. This is me again, Paul Edouard Solin. This is the second part of my talk on our deep neural network superglue for visual localization. For those that just joined, I am a PhD student at ETH Zurich, and this is our winning entry for the localization challenge for handheld devices. It is based on our paper, Superglue Learning Feature Matching with Graph Neural Networks, an oral at CVPR 2020. So in the previous talk, we covered the internals of Superglue and its performance on the local feature challenge, which specifically evaluates image matching for day-night localization. We will now see how Superglue can be integrated into a full localization pipeline and why it helped reach the first place in the challenge for indoor-outdoor handheld devices. So differently from the previous challenge, here we are not given a list of matching images. So we need to rely, for example, on image retrieval to find these relevant image pairs. Additionally, we are now evaluating both outdoor and indoor localization on the Aachen day-night and the InLoc data sets. So there is much more diversity in environments, and we need a method that can generalize well. So last year, we actually won this challenge too, using hierarchical localization, which is based on our CVPR 2019 paper shown here. And to briefly summarize it, we can use deep learning for both image retrieval and matching by predicting global descriptors and local features. So we can do this for both database and query images, and we can also build a structure from motion model for the database, so pretty standard pipeline. And then for a query image, we can retrieve some relevant database images. We can cluster them based on the visibility information in the graph of the SFM, and then we can match the local features. And finally, from the resulting 2D, 3D matches, we can estimate a pose. So the best combination at that time was using NetVLAD for the retrieval and SuperPoint for the local features. This worked pretty well, but still had a number of issues. First, the retrieval is far from perfect, and it often has a low recall, so there is no relevant images in the top 20. Regarding SuperPoint, its descriptors are not really scale invariant, and its context is rather limited, so the matching can easily fail. And in addition, its key points are not subpixel accurate, so they are sometimes not so well localized. And it turns out that our superglue matcher can actually mitigate all of these issues. We'll see how. So as a reminder, superglue is our deep neural network that performs feature matching. It combines graph neural networks and optimal transport to estimate matches between local features in 2 images, but also to reject unmatchable points. And we'll see now how it can mitigate the current issues of hierarchical localization. So we first have a look at the training pipeline. And our outdoor model is trained on structure from motion data using pairs of relevant images with ground truth poses and depth maps. Given some detected key points, we can compute ground truth matches and label some points as unmatchable. So we have green matches and red points that we know are not matchable. And this is used to supervise the partial assignment matrix predicted by superglue. The matches are here in the green part, and the red part corresponds to the dustbins, the unmatchable points. And this actually means that superglue can learn the context of the concept of visibility. It can understand that some regions of an image are not co-visible with the other image. How does this help? Well, imagine that now we have a difficult query image and the retrieval fails. Or not that it fails, but the top, for example, 3 retrieved images are not really relevant. The nice thing is that superglue will not predict any match. Even though it was not trained with non-matching image pairs, it can still reject irrelevant images. That's because of a training process. So we can actually retrieve more images until superglue can find some matches. And here, image 39 is finally matched with 99% inlier ratio. So that shows that superglue, in addition to having a very high recall, so more matches, also has a very high precision, near perfect precision. So we can actually retrieve more images without affecting the inlier ratio, and we can basically boost the retrieval performance artificially. Similarly, we can look at another capability of superglue. As you can see here, we have 2 images with the key point locations, and there's actually already a lot of information in these key point locations. And we can even match these, these 2 windows, we can actually just from point cloud see that they're actually matching, and these are the same buildings without looking at the underlying images. And this is exactly what superglue can do when the visual descriptors are not informative anymore. It can learn to not trust them and instead rely only on the 2D point cloud. And this turns out to be very useful when there are large scale changes or many self-similarities, basically when the visual descriptors can fail. And here, so you see some patterns here, some kind of arcade, and we actually see the same here. We can recognize it in the 2D pattern, and that helps superglue to perfectly match this image and have a very nice estimated pose, while the actual original descriptors are pretty poor in this example. On different note, on a related tone, is the impact of the size of the input image. As we upsample the image, the receptive field and the context of CNNs shrinks. From here to there, we only see a small tile on the window. And as a consequence, the matching of the local descriptors is going to fail more often. But on the other hand, the key points become more accurate, especially when there is no subpixel refinement. And this helps the pose. And overall, the pose estimation when using the nearest neighbor matcher is not really improved because of a shrink of context. Superglue, however, expands the context of the descriptors to its maximum, basically the whole image. So we can now use large images and have a clear boost of performance because of more accurate key point without any loss when it comes to matching. And that's because it operates also on the 2D point cloud. Finally, one of the common concerns with learned methods is their ability to generalize. In our case, we observed high performance using a single superglue model for both indoor and outdoor. It works well despite different cameras, lenses, image sizes, aspect ratios, and doesn't require intrinsic parameters. It just works well out of a box. So our localization pipeline is as follows in the end. We match each query image to up to 50 relevant database images using superglue. Then these 2D matches are lifted to 3D using either a triangulated SFM model for Aachen or using the given 3D LiDAR scans for InLoc. Same pipeline, just two minor modifications on how we get the depth of the points. And it turns out that, as Martin said previously, image retrieval is actually really hard indoor because all corridors and all rooms have similar doors and furnitures, so we cannot really trust the retrieval. To that end, we use some temporal consistency to boost it. So in the InLoc dataset, the queries are ordered, but they're sequentially ordered, and they belong to two floors, the first and the second. So what we do is that we have a multi-step approach where we first localize easy queries and we save the floor wherever we're localized. And we can use that to deduce the floors of the hard queries that are temporarily adjacent. Everything is automated, it's just filtering. And finally, we can use these priors to restrict the retrieval of the hard images. And this helps quite a lot for some examples. For example, this query is originally retrieved in the wrong building and in the wrong location, but when restricting it to the right building, then we actually get the right place that is retrieved, and then we can get matches with superglue. Finally, some results. Superglue provides a big boost to original hierarchical localization. The pipeline is very simple, and we don't need dense reconstruction or semantic mapping like ONAVI. As a summary, so I presented superglue, a deep neural network for feature matching, basically the power of attention and optimal transport to provide amazing matching and localization, all real-time, robust, and well generalizing. So I'd like maybe to give 3 takeaways, if the time allows, on our experience with superglue. First, it's a paradigm shift. We found that using the key point positions to find matches greatly helps. We do not simply rely on the appearances anymore. Second, when we have a big model and a lot of data, a big data set, the data distribution matters a lot. Here we train superglue on extremely hard examples and obtain very good matching in a wide range of situations. And lastly, we should look around. Graphs are literally everywhere in SLAM, and maybe with our graph neural networks, we can learn useful priors and we should see what should be learned. So you can, if you want to learn more, if you have questions, you can tune in for our oral and live Q&A session on Wednesday. And you can also join the image matching workshop on Friday morning, where I'll give a talk, since superglue won the first place there. And you'll see some evaluation on superglue for 2-view pose estimation and structure for motion. So pretty different from our challengers for visual localization. And that's it. If you have questions, feel free to reach out by email or Twitter, and you can check our website for paper, code, real-time demo, and slides, of course. Thank you. And of course, I would like to also thank the organizers for these great challenges that everywhere are very fun to take part in, I think. Thank you, Torsten.
Thank you very much for the nice talk. We have a question online. Do you think, along with temporal consistency, forced explicit co-visibility while training could help more?
Sorry, could you repeat the question?
Do you think that along with temporal consistency, forced explicit co-visibility while training could help more?
Could help more. And so I think the training procedure could be refined. And I don't think that we need maybe that strong supervision when we have so much consistency in the world out there, temporal consistency and 3D consistency. So it might be possible to derive new training strategies that involve maybe not having any poses or depth, but rather trying to maximize some matching metric. I think that would be interesting to follow.
Let's see whether we have additional questions. So far you're looking at mostly at pairs of images, right?
Mm-hmm.
What happens if you go to, say, triplets or something like this?
So either triplets could be used, I think, for training or at test time. So at test time, it becomes a bit more involved because then we have a lot more matches and it's not really trivial how to handle that. But maybe triplets could actually provide a good supervision at training time. Because we could have some consistency beyond just epipolar geometry, we could actually have 3D consistency. That would be pretty useful. But at test time, I think that there sure would be a lot of things like that, kind of a learned structure for motion, but I don't foresee anything that is scalable, at least not in this paradigm of attention and so on.
Great. Yeah, thank you very much.
Great. Thank you.
And thanks for the great talk. Looking forward to the discussion phase of the superglue paper.
Yeah, great. Feel free to join, and thanks for the invitation. It's always
thank you. Thank you very much. Okay. And we have one final talk, which is the second place of the handheld localization challenge. Do you want to introduce things?
Hi, Professor Settler. Can you hear me?
Yes.
Please play back the recorded video for us. Thank you.
Will do.
Hi, everyone. Today, I'm going to present you the second place solution to the handheld device challenge. This work is done by Fan Huanhuan, Zhou Yuhao, Liang, Gao Shuang, Li Jingnan, and Guo Yandong from Opal Research Institute. This figure illustrates our localization pipeline based on a standard retrieval-based framework. During offline preparation, a map of 3D point cloud is constructed with CoMap, and a semantic label is assigned to every point. During runtime, we extract feature points from the query image and predict the semantic.
Is the video showing? Because for me it's frozen.
I don't think it's showing properly. Maybe you can change the player. Hi everyone. Today I'm going to present you the second place solution to the handheld device challenge. This work is done by Fan Huanhuan, Zhou Yuhao, Liang, Gao Shuang, Li Jingnan, and Guo Yandong from Opal Research Institute. This figure illustrates our localization pipeline based on a standard retrieval-based framework. During offline preparation, a map of 3D point cloud is constructed with CoMap, and a semantic label is assigned to every point. During runtime, we extract feature points from the query image and predict the semantic segmentation and depth map with CNNs. We perform image retrieval and check the retrieval results with semantic and depth consistency. After that, feature matching and pose estimation is performed using geometric, semantic, and depth knowledge. We then cluster pose with dbScan and remove outliers of pose estimate. Finally, we combine all 2D to 3D matches and perform an overall weighted ransack with semantic information. Firstly, we propose a method for image retrieval verification using semantic and depth information. Our idea is to leverage semantic and depth cures to identify and remove bad retrieval results. Our work flow consists of 7 steps. Step 1. We perform image retrieval with stealth algorithm. Step 2. Perform feature matching between every query and retrieval pair. In step 3, we count the proportion of matches with identical semantic label, producing a semantic score. In step 4, we also count the number of matches with low depth ordinal cost, producing a depth score. This will be discussed later. In step 5, we rank the retrieval result using semantic and depth score computed in the previous steps. In step 6, repeat step 2 to 5 and compute pose estimate for every query and retrieval pair. Finally, in step 7, cluster the pose estimate in step 6 and remove outliers. Our experiments show that superpoint and R2-D2 features have different spatial distribution. As shown in the figure here, superpoint on the left extract thick-like salient features, while R2-D2 on the right focuses on features with low repeatability. During offline map generation, we extract both features to produce a map of 3D points. And during runtime, we extract both features from query images and match against corresponding features in the retrieved images. Now, let's describe the use of depth prediction in visual localization. The depth map prediction is computed by a CNN using a single RGB image. We first verify the image retrieval results. The idea is to compare the depth of 3D points in camera coordinates with the predicted depth, assuming the pose is correct. In step 1, we compute the pose using 2D to 3D feature matches between the query image and a retrieved image. In step 2, we convert the 3D points to camera coordinate, take the Z value, and sort them in order. In step 3, we take the predicted depth values of the same XY locations, and again sort them in order. In step 4, compare the ordinal difference between the Z values and the predicted values. In step 5, the number of points with large ordinal difference is recorded as a measure of consistency of this retrieval result. We also leverage depth knowledge to verify feature matching results. The idea is to identify and remove matches with inconsistent depths. In step 1, we repeat step 1 to 4 in the previous section. In step 2, we remove matches with large ordinal difference. This slide shows a result on depth verification. The top figure is a depth map of a query image. The depth prediction network is trained with the megadepth dataset. We fine-tune the original model with data generated using the Archon dataset. A bad and a good image retrieval results are shown in the bottom row, where red lines represent bad matches and the cyan lines represent good matches. In the left pair, though there are some feature correspondence, they are heavily occluded in the query image, which is behind the tree over here. This makes feature matching mechanism return a large number of incorrect matches, which is mostly identified with the proposed depth verification. The right figure shows a good retrieval result with similar number of inliers, where all the matches have passed the proposed depth verification. Here is the second result on depth verification for feature matching. The left figure shows the depth map. The right figure shows 4 inconsistent matches. 2 of them are identified correctly, which is the one here, and another one is here. However, due to error in single image depth prediction. There are two false positives. One is on the top edge of the building, which is the one here, and another one is at the edge of the window, which is the transparent material. To handle this problem, we compute reprojection error before and after removing inconsistent matches, and only remove ones which increase the error. We apply semantic knowledge in the process of ransack using the proposed weighted ransack scheme. The idea is that we adjust the ransack threshold with semantic consistency weight. We also compute the score of model hypothesis with semantic knowledge. Consider the first equation here. The semantic consistency weight is essentially an alpha mix between the total number of inliers and the number of consistent inliers. The weight is then normalized by being divided by the maximum weight amongst all the retrieved images by the second equation. The workflow of weighted ransack begins with computing the normalized semantic weight. In step 2, we randomly sample 5 matches and compute a model hypothesis. In step 3, the new inlier threshold is given by the first equation here, which is the original threshold multiplied by the normalized semantic weight. In step 4, the score of hypothesis for every other matches is calculated by the conditional equation shown here in the second equation. Detail is in the paper. In step 5, repeat step 3 to 5 for a number of iterations, and take the hypothesis with highest score. Here shows an experimental result, where a large view variation is observed. The top figure shows the matching result computed without semantic weight, where all matches are incorrect. The bottom figure shows matching result with semantic weight, where only one match shown on the right is wrong. Note that they cannot be identified, since both key points are labeled as building. In summary, our work contains 4 main contributions. First, we re-rank the image retrieval results based on semantic and depth consistency. Second, we use multiple features to improve post-estimation. Third, we develop a new weighted ransack scheme using semantic weight. Our method has 3 major limitations. First, it will produce bad results at area where semantic segmentation or depth prediction is wrong. Second, it is highly time-consuming, which takes about 30 seconds per image on a regular PC. Third, it requires a lot of storage space for multi-descriptor 3D map and multiple CNN models. Thank you for your attention.
Thank you very much. We have time for 1 or 2 questions. So maybe I'll start. So one thing is, you mentioned it 30 seconds per image. Can you think of a way of making things faster?
Currently, we are using top 100 retrieval image. One thing I can think of is to reduce the number of retrieved image or use a better retrieval method. Thanks.
Thank you. Maybe one short second question. You mentioned for the semantic consistency that it's hard to get more information because a lot of things are labeled as building. Can you think of a way around that?
Yes, we also check the consistency using depth. If the depth is estimated properly, the false matchings on the building may be identified by the depth. Thanks.
Okay. And one final question. How is the delve local feature in the retrieval part of the pipeline used?
Sorry, could you please repeat the question?
The question was just retracted. Never mind, I guess. Yes, thank you very much for interesting talk. Joseph, you want to take it over from here?
Yes. So, so it's my great pleasure to introduce the next speaker, invited speaker at this workshop, who is Jana Kosecka. Oh, excellent, Jana! I can see you now.
Hi.
Hi. Great to see you.
What a wonderful background you have.
So, say a few words about while she sets up City.
So, can I go ahead
Can
and
you hear me?
share? Yeah.
Yeah, yes, please share your screen. Yes, yes.
Okay.
I'll say a few words about you, and then this stage will be yours. So Jana is a professor of computer science at George Mason University. She did her PhD at University of Pennsylvania and followed by a postdoc at UC Berkeley. She has done a lot of really exciting work on the boundary of computer vision, robotics, and of course, these days also machine learning. She won the Mar Prize for one of her early works on 3D computer vision. And I'm really excited to hear what she has to say today in the invited presentation. So Jana, please, the virtual stage is yours.
Okay, thank you very much for the introduction. So let me try to get started. Can you see my screen?
Yes, I can see your screen. I will verify if it's on the...
All right, so we should be okay. So I want to thank you for the invitation and also the opportunity to speak there. And thanks for the organizers for providing this sort of seamless virtual experience. It's unfortunate that we'll not be able to interact in person, but hopefully everybody is safe and we'll be able to see each other soon. So I'm going to talk about some topics which are related to localization and SLAM, but I would also like to sort of branch out a little bit and talk about these a little bit more broader questions of generalizable visual representations, which could be also used for a variety of tasks. So we are in exciting times these days. There have been a lot of technological advances made by which sort of spun out of SLAM-related research. Many of them sort of fall into these categories of visual or multimodal visual odometry, where we have sort of vehicles or unmanned aerial vehicles able to do localization and mapping in challenging environments. I'm going to primarily focus on visual modality, but there are other sensing modalities which are being used in order to successfully solve this problem. And sort of the early incarnations of these technologies have been exploited in the street view mapping application, where the focus was more on trajectory recovery as opposed to 3D modeling. Then we have these techniques also sort of affecting the developments in the AR and augmented and virtual reality, both on the cell phones, where sort of the camera tracking and local understanding of the environment is very important. And also it's sort of the AR setting for HoloLens, where we sort of need to understand how the head moves. So I would like to give you a little bit sort of my view of the components of these problems in order to sort of set up where my talk fits right now. So there have been a lot of efforts in development of techniques for visual odometry, basically trajectory tracking being vehicle or camera. And these sort of came along with different representations of the environment. And usually we had, there's always desire to get more robust solutions, but we have sort of good understanding how to jointly optimize the visual odometry given certain choices of representation of environments. And the most commonly used are the key point clouds, voxel grids, side distance functions. Right? And these typically work locally well, but if you want to kind of scale up, you encounter some drift issues, and this is where the need for some global constraints comes. And the global localization aspect there both needs to get kind of global, geometrically consistent trajectories, if that is what you desire. But if you do not strive to build these large-scale consistent maps, these aspects of global localizations are also related to kind of place recognition or semantic localization, where you may want to just localize given a single view where in the environment you are. And so for majority of these approaches discussed here, usually the localization or the visual odometry or the 3D model building is the final task which is being considered, and or the camera tracking. And so what I would like to do today is to kind of discuss some different ways how to look at the problem by considering different type of tasks which are more relevant for robotic settings, such as, for example, navigation or object search or reaching a particular target or human-robot interaction, and think that maybe if one considers these various task constraints, one can relax a little bit the requirements for very precise localization or requirements for kind of dense, geometrically consistent and metrically consistent models, and use some of these data-driven and learning techniques to sort of overcome some of the brittleness of the previous techniques. And also hopefully generalize some of these strategies to previously unseen environments. But before I proceed, I want to sort of give you a little bit of history, just so you kind of see my path, how I arrived to my current interests. So we have worked early on various aspects of visual odometry, and it is fair to state that if one can sort of achieve a reasonably stable feature tracking using key points across the frame, this is usually satisfactory given some additional constraints and proper optimization techniques to recover the pose of the camera and the trajectory over sort of local or semi-global area. And then if one encounters some drift, some global loop closure constraints can be deployed. So we have done some early work in visual odometry using panoramic cameras, and this is sort of well known that if you have a wide field of view, this problem is actually really well conditioned, and usually you encounter very little drift. And so historically, once you have the good poses, the 3D reconstruction problem has been considered separately. So these are some examples of some multi-view stereo techniques using the registered poses which were recovered using the visual odometry. So this is an example of basically being able to recover a fairly high quality piecewise planar model, assuming that the poses of the camera are quite accurate. So in case the feature tracking and the visual odometry fails, which we always know that it is possible, and most commonly encountered failures are the ones where you have extremely low textured environments or, sorry about that. When you have low textured environments where you cannot successfully match the features, there have been several approaches how to bring richer image representations into the final optimization process when it comes to pose recovery. And we have also done so where we're looking at mechanisms how to exploit a single view reconstruction and piecewise planar structure of the environment, which you could fairly reliably estimate using these data-driven machine learning techniques. So this is sort of this single view Manhattan layout where you can basically get this watertight model of the environment. And then we looked at ways how to actually integrate these models over time and build sort of high quality watertight models of indoor scenes where we use the trajectory tracking only in the translation space, and as well as the global graph SLAM optimization was then significantly simpler because the rotation estimates were obtained from the single view. And so this enabled us to obtain fairly high quality models, which were watertight, coarse, piecewise planar structure models of indoors environment. So we were basically looking only at the layout of the environment as opposed to the detailed structure. And this worked fairly well. So this was an example of bringing sort of stronger model structure in order to help the post-optimization process in situations where the key point features were not reliable in order to enable the tracking and the reliable post-recovery and reliable loop closure constraints. So in recent years, there have been a lot of advancements, mostly propelled by the development of object detection, semantic segmentation, and recognition using these data-driven techniques where we can sort of train large, deep neural networks, which can estimate, we can train in a supervised manner the large, deep networks, which can estimate per pixel labels of sort of important categories, both for indoors and outdoor scenes. And along the way, we can also estimate the depth of the scene. So we have also looked at some approaches where we can look at strategies where we can estimate the semantic segmentation and depth jointly sharing a common architecture and understanding how the depth estimation and semantic segmentation interact. And this was simply a training, kind of a big U-shaped neural network where we were both optimizing the semantic segmentation loss and the depth recovery loss. And so this is just a visualization of some weight sharing between the network, which does the semantic segmentation and the depth recovery. And we have been able to demonstrate that sort of they favorably interact in the sense that the depth recovery actually helps the semantic segmentation. And this was sort of our final evaluation criteria, which we used. So this is just kind of bringing a little bit bits and pieces of the previous work in. And so these advances enabled sort of big progress in fairly high accuracy semantic labeling, both for indoors and outdoor scenes. And so here are some examples on NYU data set where you have the scenes, then in the second column, you have the ground truth information, and these are the estimates by using our model. And then in the fourth column, we have the raw depth data, and this is the depth data estimated by our model. And this work is 3 years old. So since then, there have been a lot of advancements made in order to have a better depth recovery, sort of properly following the depth discontinuities, using sort of more sophisticated priors and so forth. But so what is nice that one can actually achieve this using this sort of single architecture. So and this sort of works well both in indoors and outdoor settings. So the semantic segmentation in the localization and SLAM community has been long recognized as very effective in sort of helping to overcome some of the challenges when it comes to large variations of viewpoint, weather, or time of the day. And we too had some early work in this area where we used the semantic segmentation for the problem of location recognition, where we simply used the traditional bag of words representations, which were sort of augmented by semantic information. And this is also, these ideas have been also around in the context of autonomous driving. So basically you take some geometry and some representation extracted from semantic representations, and this helps you sort of bump up the accuracy of the image retrieval which then sort of consequently serves as a place recognition. And here are some examples of being able to correctly recognize the building across big variety of query views, which vary across the time of the day and season, and the fact that the building features were matched to building features based on the semantic information sort of helped significantly. And these are some variations across the season. So this is sort of these bits and pieces which different lines of research brought together, and people have really made a sort of a big headway in building these rich spatial representations of indoor environments where you can have the correct geometry, you have semantic labels, you can have information about objects and their poses in terms of 2D and 3D bounding boxes. And in certain cases, this information, these representations were jointly optimized with pose recovery. In some cases, the pose recovery was considered separately, and then the post-processing was done using these 2D segmentation techniques or object detection techniques. So what I would like to do now is to transition slowly to and ask a question. Well, so a lot of the motivation when it comes to robotics and robotic tasks, so these spatial representations, which we have been sort of striving to achieve, were to some extent consistent to the type of representations people use with navigation and control, right? So you typically, in a 2D case, you have 2D occupancy maps. For a 3D navigation, you can have 3D voxel grids or 3D occupancy graphs, maps. You can have continuous representations of the environments, which can be approximated by some graph structure. And so this was essentially the interface between the representations built by perceptual component and make this representation amenable to the follow-up motion planning and control. But majority of the, so this was basically the interface, but majority of the motion planning techniques typically assume that the model is given. So in order to facilitate this interface between the perception and control, one would have to invest a lot of energy into building these accurate models before one could use these models for planning and control. And so what we started looking at and thinking along with some other researchers is that whether we can sort of overcome a little bit some of this brittleness of these interfaces and needing to actually build the complete models before we can use them for navigation, and see whether you can use some of these data-driven techniques to learn the navigation strategies directly without building 3D models, and then sort of consequently basically learning the right type of representations in order to facilitate the different navigation tasks. So let me kind of very broadly define this task of semantic navigation. So we would like to have robotic agents which operate in dynamically changing environments over extended period of times. We would like to learn a certain set of skills such that they can carry out a variety of flexible tasks, follow directions, and communicate with humans in natural language. And we would like to identify navigation skills and learn them in a robust manner such that they can be easily generalized to previously unseen environments. So the generalization aspect here is sort of quite important. And of course, you can imagine that if you could do something in previously unseen environment, then over time you can sort of improve and then gradually build the model of the environment and update the model of the environment in order to carry out your navigation tasks reliably and effectively. So let's have a look a little bit what the ingredients of this semantic navigation may look like. So So imagine that you have a robotic agent who you would like to instruct the agent to go to the refrigerator and open the refrigerator and get the bottle of milk. So in order for the agent to be able to do this, you need to have some ability to know where the refrigerator is. So the ability of detecting objects and their pose, because you need to know where the handle of the refrigerator is in order to be able to do this, is really critical in order to be able to figure out what the goal of the agent is. And this is only in the setting where the agent is visible. Then you need to understand a little bit what is the free space, what the obstacles are, maybe understand the context, whether you're in the kitchen or in the living room, and then be able to plan a safe path in the free space. So what I would like to do now is instead of focusing on the problem of localization, which is the where am I problem, and it is really sort of central to the problem of mapping, I would like to sort of focus a little bit on the problem of how to reach the goal. And perhaps we can come up with some strategies how to do it without necessarily knowing the initial positions, without necessarily knowing the exact localization. And we can explore different ways how to specify these goals. And you can imagine some intuitive motivation for tasks like this could be, imagine that you have visited, I don't know, 100 apartments and you know how to find a refrigerator. So when you come to a new apartment, which you have never seen before, you should have some prior knowledge, which should help you how to go and explore that environment in order to find your goal. And then along the way, maybe build a better map of the environment. So one way how to think about these policies, which I'm going to describe this, and how to relate them to some of this mapping and localization work, is to think of them as these navigation priors, because clearly they're not going to perform as well as the approaches where you have a perfect map and you can plan the trajectory, but they're a good starting point. And these are sort of a lot of open questions for current research, how to continue. Okay, so let me sort of go back a little bit and review some historical work, sort of trying to understand what are the meaningful skills, right? Because in traditional motion planning, one does not typically consider skills. You have always sort of starting point, goal point, and you need to find the collision-free path. But if we want to think about it as the skill perspective, we can sort of consider two different categories of navigation skills, and they require different level of sophistication when it comes to models of the environment or availability of the maps, and then also to what kind of maps do we need. So one class of navigation strategies are so-called local navigation strategies, and they fall into the following categories. They can be search, route following, so following a path which you have previously explored, or aim to reach particular target, or reach some relative position with respect to the target of interest. Another class of navigation strategies are topological navigation or survey navigation or some recognition trigger navigation, which require a little bit more detailed representation of the environment. So let me give you sort of some feeling for what this may look like. So the search, the simplest form of search is just simply random exploration of the environment until the goal is reached. Another local navigation, and of course, there can be a lot of additional constraints which one can impose on the exploration strategies. Another type of navigation skill could be direction following. So for example, if you have traveled a particular path or particular class of path, can you repeatedly execute the same kind of behavior in different environments? So these are sort of either variations of following exactly the same path in in previously seen environment, or having strategies like corridor following, where if you know how to follow a corridor and turn at an intersection in some environment, that you should be able to know how to do it in previously unseen environments. Then there are these aiming strategies. So if you have some salient goal, be it a view or object of interest, you can learn an ability to do some relative positioning strategies. So given some initial view of the target, how to reach some desired view of the target. And you can do this for objects or views, or you can do it also for locations which are specified using some spatial relationships between relative objects, which could be some interesting landmarks. So there's a big variety of choices one can consider here. And then the global navigation skills are the kinds which require some sort of map. So if you have some starting point and the goal point, you may have some ability using some topological navigation to find sort of intermediate location to pass through. But as long as this door is closed, then you need some planning ability in order to replan. And in order to do this replanning, you really need some more detailed spatial model of the environment. So you need to kind of know how to return to the place which was your original goal. So this is just to at least sort of briefly outline some of these different levels of skills and granularity and how they may affect the representations of the environment. So let me talk about what we can do when it comes to navigation, this very local navigation where you just simply want to reach a particular goal. So if the goal is in the field of view and you have some desired relative position with respect to goal which you want to reach, this is basically a traditional version of a visual surveying problem, which could be accomplished by establishing correspondences between the starting view and the target view, and then designing the control law, which is governed by the laws of perspective projections, in order to calculate the linear and angular velocities to reach the goal. But as these correspondence techniques typically go, this type of controls are very brittle. So as long as you lose the correspondences or you cannot establish the correspondences properly, these techniques fail and they're very brittle to this when it comes to this process. So we've looked at strategies, how we can actually take some of these initial representations and the learned correspondences derived from these mappings in order to learn this goal-reaching policy. And so here is a small visualization of the initial view, then the target of interest, and the final view, which the agent is trying to reach. And so let me sort of discuss a little bit the approach. So what we have done is we basically have taken the current and the target view, and using the depth map, we have computed the exact correspondences between the two views. I mean, exact modulo the errors which one attains on the computation of these correspondences. And we use these correspondence maps as an input to a deep learning network, which was a mapping between the correspondences and the control actions. So the perception component directly have taken the correspondences, and then we basically use the deep Q-learning in order to learn the probability of all possible actions. So we have considered a discrete version of the problem. So this is also why the motion is a little bit jagged, because the space of actions is discretized. And so we were able to show that this representation is sort of suitable for these local aiming tasks where the final view or the target of interest is already in the field of view of the agent. And this does not require any localization or knowing where the agent is with respect to the goal, as long as the goal is visible and some goal keyframe is specified in memory. So we have trained this policy by sort of sampling various configurations of initial and final views for different targets in Gibson environment. And we have, so this was an experiment which we carried out only in simulation. And we have demonstrated that by learning this policy, we have attained a navigation skill which was much more robust than the traditional image-based visual surveying, which was sort of relying on this sort of precise correspondences. So in some sense, the network somehow managed to pull out the relevant information from the correspondence map at the places where it was reliable in order to come up with the right kind of commands. And this was presented, this was a work of my student Yimeng Li, and it was presented just last week at ICRA. And we have done some comprehensive evaluation of these strategies for a variety of target views and targets. So this was the first setting where the target is already visible. So the second question is, well, what can we do? I mean, how would the navigation priors look like if the target is not visible? So here the question was, can we have these target reaching behaviors at the level of that you will drop the agent somewhere in the environment and you will say, go to the refrigerator or go to the microwave, and then agent will basically learn a policy, which is a mapping between the observations and actions in order to achieve this goal. And so we have considered this semantic target-driven navigation tasks for several targets. So we looked at sort of couches, microwaves, refrigerators, and the choices of targets was really mostly related to the availability of the training data for the particular class of targets. And so before I sort of discuss our strategy, I want to just briefly mention that this is something which has been of interest to several people in both robotics and vision communities. And previous approaches sort of try to tackle the problem by learning the mapping directly from images to actions using different architectures and different sort of mechanisms for supervision. Usually the approaches were formulated in the reinforcement learning framework, where the choice of the reward was usually choice of the reward structure was quite challenging because these type of problems typically require a large number of trials, and with sparse rewards, it's very hard for these policies to converge. So without sort of trying to relate it to all the work on reinforcement learning, I'll tell you sort of briefly what we did is, so instead of learning these mappings directly from images, we have opted to actually use as an input to this policy the semantic representations extracted already from the state-of-the-art available object detectors and semantic segmentation. So the input to our navigation strategies were object detection masks, semantic segmentation masks, and depth map. And these were trained using the state-of-the-art data sets in the supervised setting. So we used COCO to train the object detector, and we trained the semantic segmentation on NYU dataset. And then we've learned a policy where we learned a common embedding of these three semantic modalities followed by some fully connected layers in order to predict the action. And the first order policy was just a feed-forward reactive policy, which we then sort of later on improved by adding some recurrent component. So I will discuss the recurrent component in a little bit, but before I proceed, I want to sort of discuss a little bit these aspects of training and evaluation when it comes to learning policies, which so we have used the Activision data set partially for the training in order to be able to sort of understand and work with the real images and real depth data. So this is a data set which was sort of put together through our collaboration with the University of North Carolina, and Phil Amirato is the main force behind the data set. Phil sort of went and scanned 11 homes. There are right now about 30,000 images where you have 12 views per each location, and the locations are about 30 centimeters apart. And the entire home is fully registered. So we use the call map to register the views. So here at the bottom, you have visualization of all the registered views. And the nodes are the locations where the 12 scans of the environments were taken. And per location, we have both RGB and the depth data. So the data set is not very large, and it's certainly not sufficiently large in order to train these complex navigation policies. But here are some samples of the models of the environments. But we have been sort of successful in training it jointly with the simulated environment. And here are some examples of some of the training mechanisms. So we have simply, instead of training it in a reinforcement learning setting, we've used the imitation learning, where we have generated a lot of ground truth shortest path from arbitrary points in the environment to the goal. And this was serving us as a supervision. So we could then tell at each instance of time, we could give, so what we would like to do is we would like to predict an action which has the highest probability, which would be the action which would reduce the distance to the goal. And you can either do not reduce the distance, you can move further away from the goal, or you can move closer to the goal. And that was basically per state reward, which we could do to our system. So you can also think of it as being able to give the model extremely dense set of rewards, as opposed to just waiting for the reward once the agent finds the goal. And this was facilitated by this ability of computing the shortest path using just a simple Dijkstra's algorithm on this discretized navigation graph. So the first attempt was just to come up with the purely reactive strategy, and then the second improvement we have achieved by adding a recurrent component, which provided a little bit of a memory. So the way how these policies looked like, you give it as an input the semantic representation of the environment, and as an output the policy, you will learn the action. And I'm not going to go through the details of the performance. So we have done very detailed ablation studies on what matters in terms of semantic segmentation depth, image-only object detectors. And we further improved the training by using this joint training between the real data and the simulated data, which also significantly improved the performance. And the appeal of the approach was that because the representations which we used were semantic, we didn't really have to deal with this real to sim transfer and photorealism issues, because the models were basically trained using these higher level representations. So these are some sample training runs in simulated environments where we use the House 3D simulator. So here are some examples of the difference between the simulated and real data. So this is also sort of an important issue to consider. So the real data are significantly more noisy than the simulated data. So this is sort of something to keep in mind if one is learning the policies in simulation only. And there has not been sort of a thorough study to what extent these errors actually affect the navigation strategies, but this is a sort of definitely interesting question to look at. So here are some examples of some of these, some of the policy in action. So here is an example of target being couched. So you can see that the agent started in some random environment, looked around, realized that it's in the kitchen, and then it started heading down the corridor. And once it's found the couch, it started heading towards the couch. So basically, the policies learn some kind of semantic content, which enables agents, you know, if the agent is in the contextually wrong environment, looking for the target, which has never been seen in that previous environment, it typically leaves the room and starts exploring sort of other areas of the apartment. Here are some other examples of going to microwave and a refrigerator and looking for TV. So you can see that at the beginning, the target is not visible, but eventually the agent finds the target. So this was sort of exciting and promising, but as you can imagine from the robotics perspective, the results were in some sense disappointing, but not surprisingly, because again, we were sort of measuring the performance on previously unseen environments, and we were simply measuring the success of single episodes. So there was no exploration, no memory. It was just purely reactive behaviors. But despite of the fact the method achieved was significantly better than random, which would be the random exploration which we would have at our disposal if we were not learned the navigation prior. And in 55% of the cases, we have found the goal within, I think the episodes were within like 30 or 40 steps. So the next follow-up of this work, and I'll probably start going a little bit faster, we started late, was sort of trying to understand if we were to have a map, if we were to build a map in the process, whether that would help, right? Because this reactive strategy, you know, has a little bit of a memory, but there's no notion of a map, right? And so we have extended this work in order to incorporate a mapping component. So what we have, and also the localization component. So what we have done is that we have basically adopted the MapNet architecture, where instead of using the right features for localization, we use the semantic inputs both for localization and mapping. And so the way how the final architecture looked like is that we would give it as an input image, output of object detectors and semantic segmentation. We will build a 2D map. So where we would, at each instance of time, estimate the position of the agent, and each location of the map grid would have some learned embedding associated with it, which was learned from the semantic features. And then this map was then used as an input into the navigation strategy. So as opposed to just using an input image, you would also use the map in order to train the strategy. And so there were two components. We had sort of parts where we trained both of them separately. Then we had some experiments where we fine-tuned the models. But the essence was that the mapping indeed helped. And with the mapping, the performance of these target reaching navigation strategies improved significantly by some percentage. Okay. Again, mind that this is still just the evaluation of the single episode. There's no kind of there's no map building component. This is just improving a little bit the memory component of the model in order to improve the success rate. And we have done some experiments, both again on Activision dataset and Matterport dataset. So, and here are some visualization of these experiments as the 2D map is being built. So this is, you can see on the left is a bird's eye view of the map and the path the agent is following. And this is for reaching the couch. And here it's for reaching the TV. And here the 2D map is just simply occupancy grid, and the coloring is just the projections of all the 3D points on that particular occupancy cell. And it's sort of colored with, you know, the color of the points. So this is sort of some attempt to, again, learn a map where the information associated with each occupancy cell is optimized for localization and navigation, target-driven navigation task. Okay. So let me sort of slowly wrap up here. So another interesting experiment which we have sort of carried out in the context of this Activision data set is active object recognition. So in the robotic settings, the state of the art of the current object detectors dramatically varies and is affected by the amount of occlusion and viewpoints. So there are a lot of opportunities for developing active recognition strategies where the agent actively changes the viewpoint. And we had some initial attempts to do so in our initial dataset paper, and I'm not gonna go to details, but again, this was a policy where we were optimizing the recognition rate, and it was again trained in reinforcement learning setting. Another important component, which right now it's sort of not fully integrated into these pipelines, is the object pose recovery. So I'm a firm believer that the world is made of objects, and we really should seek some strategies where we can jointly recover the 3D pose of the object and integrate it into this sort of aiming and pose estimation strategies, and both in the context of localization and mapping. And we had some initial attempts how to do so in cases where the pose, so this was in a supervised setting when we were trying to estimate the 3D bounding boxes of objects, and we had only pose annotations, ground truth pose annotations in images. So for this type of approaches, one requires extremely large number of training data. And we have already heard some other techniques which have been very successful on this workshop, which, for example, use the CAD models in order to pre-train the techniques for pose estimation. So there is sort of this whole spectrum of choices and representations one can use in order to tackle these problems. And I will just fly through this. There is a reference to the paper. I'm not going to go through the architecture. And I would just like to wrap up and maybe open to questions. I think this avenue of thinking about the tasks which the environments will be used for sort of opens new avenues, how to think about what are the right kind of representations for the environments. In many cases, one can relax the assumptions of requiring exact localization, because now we are trying to tackle these tasks without requiring exact planning and control, but we can sort of learn these different navigation skills. Then, of course, the question is how we put these navigation skills together in order to accomplish these more complicated tasks. So I think I'm just going to leave with a lot of open questions. I think there are a lot of interesting avenues to pursue, especially when it comes to representations which use objects and pose jointly with semantic segmentation and that. So, and I want to thank my students and collaborators and the organizers again. So thank you.
Jana, thank you very much for the exciting talk. Thank you. I'll do this virtual clap. So there is several questions on from YouTube. I'll maybe start with one of my questions. So this is more, I also have this motivation of going eventually to real robots, maybe going indoors around hospitals, for example. So how big do you think the gap is from doing these experiments in simulation towards maybe running some kind of a system like this, which can navigate in a, say, hospital or in some kind of a real robotic platform. Do you think this will generalize directly? I'm sort of more thinking of this generalization rather than, of course, there will be issues about the platform and stuff. But do you think the visual systems will generalize?
So I think I would definitely not deploy a system like this and expect it to generalize. But I think about it more as navigation priors, right? I think, you know, when we are deploying these systems in real robotic settings, we should exploit all the constraints the environment is offering us. We should really try to build high quality maps as we go along and operate in these environments, because, you know, that's what we can do. I mean, if you buy a robot, you know, it will be at the end operating in that hospital. So these sort of mechanisms for building kind of robust metric, spatially coherent maps are, I think, meaningful. But I view this type of approaches as sort of some alternative in order to overcome kind of the brittleness of the other techniques, right? Because we all know that, you know, when these techniques fail, they fail really sort of badly, right? And so you maybe want to have some mixture where you sort of have something where you are building the map, but you have these kind of skills and recoveries that you can kind of recover and get back to that mode without sort of completely giving up. So I think a lot of these problems are, I think, motivated by this sort of holy grail AI questions of how perception, control, and planning interact. So I think this is one aspect which is, I think, really interesting. But I think the impact of these policies is also on being able to deal with dynamically changing environments, such that you don't have to sort of constantly, you know, rebuild the models, but you can adapt them along the way, right? So there are a lot of, I think, possibilities to explore along the way.
It's very interesting. Actually, Deva Ramanan was recently also saying this idea is that somehow the learning-based techniques sort of seem to fail more gracefully compared to the standard structure from motion. It's a very interesting property, which I think is
I agree. Yeah. Because, you know, I mean, if something is all resting on like 5 correspondences and you just only find 3, then there's nothing. I mean, so of course, exaggerating, but yes, so I think they provide sort of some systematic way how to build in a little bit of robustness without kind of hand coding and fine tuning things.
So ask them one more question from the YouTube. So the question was, how can we generalize this kind of navigation approach to continuous action spaces? Which I think is an interesting one. Can one go, how would one go, or have you thought of going to more continuous action spaces?
Yes, so there are sort of 2 avenues. So one avenue which is being pursued. So the problem with the continuous action spaces is that it's not trivial to get the dense supervision, right? Because you would have to basically solve the optimal control problem. So there are 2 sort of avenues people are pursuing. Either they just go with reinforcement learning. So you basically, supervision is sparse, you do what you can do, and then you get a reward at the end. And in order for these techniques to work, they need to usually set up a lot of auxiliary tasks in order to introduce more structure into the problem. And usually the auxiliary tasks are reconstruction, detection, you know, all the tasks which in some sense our representations are sort of offering. Another avenue is to, you know, have some mechanism where you still provided the supervision using these discretized representations, because shortest path is easy, but then have it kind of executed using continuous representations. So this is sort of something we are currently exploring in order to be able to have better level of supervision and stick with some combinations of this imitation and reinforcement learning. And at the same time, remove this jaggedness which sort of currently exists in the resulting control strategies. it also depends a little bit how the goal is specified. You know, when the goal is specified in the egocentric coordinates, then you actually have an option of deploying these optimal control techniques because you know where the goal is. But these techniques then require localization, right? So you typically assume that you're perfectly localized. So there are these, you know, pros and cons, and I guess we need to explore different angles to figure out what works best.
I'll ask you the last question, which is, I think, yes, please go on.
Oh no, I just wanted to say that I believe that, you know, there are a lot of, I believe that there is an opportunity to have many of these skills, right? So because there are a lot of different ways how we know how to navigate, and then, but then the problem will become how do you decide which skill you utilize if you are tackling more complex tasks.
And so I'll finish with last question, and it's related to semantics. Actually, there are sort of two related questions in the YouTube chat. And I think they are sort of more related to the sort of first parts of your talk. But I think actually this sort of idea of using semantics has been reoccurring through your talk. So I will kind of ask more general question, wrapping all these together. How do you think these approaches sort of generalize? So the question here is, well, if you train it for outdoor semantics, then, you know, how does it generalize to indoor scenes? And similar to viewpoint, how general is this with respect to the viewpoint? So, so can you maybe say a bit about the semantics and how do you see it sort of being used, and the idea of generalization between different spaces? Yeah. You have to retrain.
I mean, so right? Indoors, outdoors, it doesn't general. I mean, right. So one needs to consider just meaningful classes of the environments. Now, what the semantics does is semantics is tricky because on one hand, it reduces some of the specificity, right? So sometimes you can actually lose some of the information when it comes to localization. But because you have these models which are trained for categories of which have large variation in appearance, viewpoint, and lighting, these are the main components which the semantic information sort of helps you factor out when it comes to brittleness of these systems. But again, it's a tricky part because, you know, for localization, you can have semantically identical places, but they can be very different. So at some point, you need to have these different levels, right? You have a semantics, but then you have either the geometry or appearance underneath, depending on what you are looking for. But I would definitely not expect these things to generalize across different environments.
Yeah, yes. Okay, so Jana, thank you very much for this exciting talk. Thank you very much again.
Thank you for having me. Okay, good to see everybody. Thanks.
Thank you very much.
Okay. Stay healthy and safe. It must be late for you.
Yes, you too.
Not too bad.
Yes, you too.
It's
okay. It's okay.
Okay. All right. Thank you.
Thank
okay.
You. Bye.
Bye.
Kristen, please.
Rensham, was it on purpose that you stopped? So it's my great pleasure to introduce our next speaker, Jakob Engel. Jakob did his PhD at TU Munich in Germany with Daniel Cremers, then moved to Seattle to Oculus Research. He's now a research lead at Facebook Reality Labs. And you probably all know a lot of Jakob's work on LSD SLAM and on direct sparse odometry. And Jakob did actually something very rare in his PhD, which is one, both push research novelty and introduce novel concepts that are now widely used. And at the same time, he created actual systems that worked in real life and released code for that. So that's something that you rarely see in research. And yeah, I'm very much looking forward to Jakob's talk. Jakob, the floor is yours.
Cool. Can everybody hear me? Just a quick check.
Yes, I can hear you.
Cool. Yeah, thanks so much, Thorsten, for the introduction. I will just full screen my slides here. Thanks so much for the introduction and for the invitation to give a talk at this workshop. Also, thanks all the organizers for making it such a seamless experience, even though we are all across the world at this point in time. So that's really amazing to see actually that this works much better than I expected initially. So I'm going to jump right into it. I'm working at Facebook Reality Labs, and we're working at localization for AR and VR. As you've all heard a bunch of times over the last, over yesterday and today, location is a key ingredient to make AR and VR successful. It's also a key ingredient for a lot of other upcoming technologies, from autonomous drones to autonomous driving. And I'm going to focus on the AR VR one in this talk. And a classification that I've also heard a bunch of times is this kind of breakdown into global localization and local tracking. Global localization, talking about localizing yourself within a city or within a building and across large time spans. So seasonal variance comes in there. And local tracking is the very accurate local tracking that you'd need in order to, let's say, provide a VR experience or provide like a world-locked AR hologram. And that usually kicks off once you actually know that you're in your living room and now you need to track precisely in your living room. Now, both of these branches, actually, they don't only use vision. They use other sensors as well. For global localization, the typical ones or the usual suspects are GPS or wireless, Bluetooth. Almost all your devices that are connected to the internet know where they are simply by tracing their IP address. And for local tracking, the main other sensor that comes in are IMUs. These pictures here are from a publicly available video of the Oculus Quest device, which use exactly vision and IMUs to track your position and provide a VR experience. And in this talk, I want to do something a little bit special. I want to go into that one particular component, which are the IMUs, and talk about tracking without vision. Or talk about how you can actually estimate odometry, estimate your local motion completely from an IMU alone. And for that, I'm going to go over a project that we did over the last year here at FRL. It's called TLIO, stands for Tightly Learned Inertial Odometry, and it's going to be published at IROS at the end of this year. So this is very fresh off the press. It's joint work from Wenxin Liu, who was an intern in our group over the last year, as well as a number of folks from the team, David Caruso, Eddie Ilk, Jing Dong, Tassos Maurikas, and Wenxin's advisors, Costas and Vijay. There's also a website available where you can find the paper and later on the code and more results. Now, to give a quick overview over this talk, just to give everybody a preview of the next 25 minutes, I'm going to start with introducing the IMU as a sensor, because this is a workshop about vision, computer vision at a computer vision conference, and I want to quickly recap what an IMU does and what's important to know about it. I'm then going to recap like traditional visual inertial odometry methods, in particular the one that underlies one of the probably widest known or widest used one in the world, which is AR Core. And then I'm going to present TLIO, why it works and what it does, and I'm going to show some results. So let's start with a general overview of what IMUs are. In practice, IMUs are one of the most powerful complements to visual data. There are lots of different types of IMUs around, from very high quality, very expensive, very big and heavy ones that are used primarily in like military applications or in submarines, all the way down to tiny MEMS ones that you can find in every single mobile phone and every single laptop these days. Initially, they were put in there just to flip your screen when you rotate your phone, but by now are used for many other applications. An IMU at its core measures two things. It measures the rotational velocity, so how do you at which velocity do you rotate it in space? And it measures the linear acceleration, so it can measure how fast it is accelerating in X, Y, and Z direction. It does both of those things with like tiny mechanical systems that measure this, or in the case of more expensive ones, via like fiber optic assemblies. But those you won't have in your mobile phone. Now, assuming you know the initial state, meaning assuming you know where you are, your X-off position, and your initial velocity, that actually allows you to estimate the position in which or your motion in 6 degrees of freedom by integrating the rotational velocity to get your orientation, and by double integrating the acceleration to track your position. Now, like all other sensors, the IMU is far from perfect. There's a lot of noise, and that actually makes this break after a very short time in practice. How does the noise or the sensing error looks like in the IMU? Without this, we could actually track perfectly without any problems. So these are the mathematical equations. I'm not going to go into those, but I'm going to show a bunch of examples of what are the major sources of error in the IMU as a sensor. Starting with just the plain good white noise. So this is just a Gaussian random value on every single sample. It's zero mean, it's Gaussian, it's pretty nice. Or statistically speaking, pretty nice. It's actually not that large. The second noise source is an additive bias. So this is basically a bias that gets measured continuously. So every time you take a sample of your acceleration, it's going to be biased in a particular direction. It slowly drifts over time. It's usually coupled to things like aging of the IMU, or much more short-term things like temperature changes or temperature gradient changes of the environment. So it changes over tens of seconds. The third main component are just scale and axis misalignment. So an IMU measures things across three axes. They are not built perfectly, so they are slightly skewed towards each other sometimes. The scaling of the measurements, so these measurements are scaled metrically via like acceleration in actual metric units. The scaling slightly changes. Again, those are correlated to temperature. And last but not least, there are also things like G sensitivity. So actually linear acceleration messes up with your rotation measurements because they're mechanical systems at their core. And then obviously these are the first order terms, but then there are higher order effects that play in as well. So all these noise sources are the reason why inertial integration alone usually does not give you the best results. However, if you actually compare the IMU with vision, it's one of the most powerful complements to visual data because it can do exactly the things that vision cannot do very well. The IMU can do those very well. To give a bunch of examples, the IMU actually has or provides quite accurate probabilistic models with a relatively clean Gaussian noise profile. So that's nice for everybody who likes statistics. Compared to vision, where especially after you've like pre-processed the image and found some correspondences, noise models are generally a bit messy because there are a lot of outliers, there are a lot of like things that move slightly due to perspectual aliasing that you wouldn't expect to move. So there's a lot of weird stuff in the data that your like estimation framework later on has to deal with. The IMU doesn't generally have any outliers. There are some rare exceptions, but usually it's pretty outlier free. Whereas vision has a lot of outliers. There's a lot of things that, especially in the context of like localization or SLAM or VIO, just corrupt your estimation. This is because the IMU is not environment dependent, other than temperature having an effect on the like internal biases of the IMU. It is a purely intrinsic sensor versus vision is a highly environment dependent sensor. It works very different in different environments, which actually makes this field so very interesting. That's how I like to think of it, because it needs to work everywhere under all conditions. The IMU operates at a high rate, up to 1 kilohertz with low delay. Vision usually operates at a much lower rate, like 30 hertz cameras, for instance, with a much larger delay because you need to take pictures, which takes 10 milliseconds in a darker environment, for instance. It's cheap to process. The IMU is a six-dimensional vector. That's it. Vision is quite expensive to process, as we all know, at least when you want to put it on like embedded devices. The one big thing that vision has going for it is that its accuracy is independent of time passed, at least if you subtract out environmental changes. So you can actually localize yourself over, to the next day or to the next week. Obviously, environment changing makes that difficult, but it's essentially independent of time. Whereas the IMU is great in the short term, but it drifts as you accumulate error over time because it depends on this integrating of dynamics. Okay, so how does an IMU get used in a visual inertial odometry framework? And I'm going to take as reference here the so-called MSCKF framework that was developed by Tassos Marikas and Georgios Rumiotis in about 2007, and now is one of the probably widest used approaches across the field. So you start off with a visual front end that takes in images and establishes correspondences, matches points. This is a traditional indirect approach. It establishes point correspondences using your favorite point detector, descriptor, and so on. And then there is an estimation backend, which takes in the IMU data. It takes in those like 2D correspondences, and it estimates the state of the system. So that means it estimates things like where your camera is. It estimates things like where your point positions are in 3D, but it can also estimate other intrinsic model parameters, like for instance, online calibrate the camera projection function, or online calibrate the IMU values as well, such as the biases. And this is very important. So these two things are the main ingredients, and then the output of that state estimation is an odometry. Now, usually this becomes a loop where you not only have like a visual front end that just matches incoming images, but you also use the computed state to help this correspondence estimation. In particular, if you have an idea of how the structure looks like, if you have an idea of what the poses of the images are, that can speed up and help matching rather than trying to match like everything to everything. Very traditional pipeline here. Now, one thing that I want to highlight is that the IMU significantly helps vision, and this is the perspective that we mostly take from a like computer vision perspective, where using an IMU can solve some of the hard problems that you have in the vision and the state estimation part of the setup. In particular, it allows to reduce the space, the search space in correspondence estimation by using known camera poses. So you can like integrate up to the next frame in practice. You have like a prior for where the image is, and that allows you to like reduce the search region for all your point matches. The same is true if you know the 3D of a point, you can actually localize where you will match it very precisely. So it's useful for that. And at the same time, it provides initialization for highly non-linear or non-convex optimization problems in the state estimation framework, where it provides a good initialization for poses. So the IMU can help significantly here to basically get good initializations for everything. Also, one thing to note is that the IMU makes otherwise unobservable quantities observable. In particular, in a monocular system or in a monocular setup, it allows to estimate scale because it brings in this metric calibration, and it also allows to estimate your position with respect to gravity. So really, you only have to estimate 4 degrees of freedom that are otherwise unknown. Now, you can also see this from the other perspective, or the other way around, which is how does vision help the IMU? And this is really, if you look at the title of the original MSCKF paper, it's actually called Visual Added Inertial Navigation. And the idea here is that the big problem that IMUs have are those temporally changing bias terms that make it unviable to use it for like long time spans. And really, you can use another source of information, such as vision, to estimate these online and make integration of IMU or tracking or odometry via like integrating those acceleration and rotation velocity measurements much more accurate. And of course, vision brings in the things that odometry inherently doesn't do itself, which is allowed to do things like loop closure, or allowed to do things like getting an initial pose and saying that you're in your living room, or that you're out on the street, which falls into the like large scale localization bucket. Now, to give an example of how good the IMU can be if you use it in this kind of framework, I want to walk everybody through a quick experiment. Let's take a modern MEMS IMU, for instance, the one that you have in your smartphone, and let's run a state-of-the-art vision inertial odometry framework on it to estimate the velocity and the internal calibration of that IMU, i.e. those biases, that scale matrix that I talked about earlier. Now let's remove vision and just continue to integrate the IMU, continue to double integrate the acceleration, continue to integrate the rotation velocity to continue track that that device. Now what happens? Over the short term, things look pretty good. So this, and I wanna point a little bit to the axis here because that's important to notice. This is over the time span of half a second. And shows you a little bit how the error evolves. The blue line is the most important to look at. It shows you the total error that you will accumulate over 0.5 seconds of raw IMU integration, all the way up to like 1.5 millimeters and 0.004 degree here. Now let's do the same experiment over the long term. So over, sorry, the title is wrong, over 30 seconds here. So this axis actually goes up to 30 seconds. Again, the blue line is the most important one. It shows you the sum of all the different components, how they contribute to the error. And you can see it actually accumulates to something much, much more. So let's walk through this. Translation, measuring your position and time over the short term is really, really good. So you get about 1.5 millimeter error after half a second of integration. It's roughly linear growth, and it's actually dominated by having a bad initial velocity estimate. Orientation, again, extremely good over the short term. It's about 0.004 degree, which is like way less than a pixel in almost all cameras. After half a second, it's sublinear growth because it's dominated by white sensor noise, which means it like grows with the square root of the variance. Now, in the long term, things look different. So in the long term, over 30 seconds, it accumulates a drift of 3.5 meters, following a very strongly superlinear growth, which is dominated by biases and actually second-order effects that come in from wrong orientation. So this is pretty much useless after 30 seconds. And for orientation, it doesn't look quite as bad, but still kind of not all that good. So you get about 0.1 degree after 30 seconds of integration. It's roughly a linear function at this point, and it's dominated by biases. So great over the short term, 0.5 seconds. That's still then the 30 hertz video. That's still like 15 full frames, but really bad over the long term. So the reason why VIO works so well is because it can use vision to actually bring in this, slightly more long-term corrections allowed to continuously estimate the biases and the internal state of the IMU, and that way allows to track both in the short term and in the long term. Now the question comes up: can we replace vision with something else, with some other source of information? Obviously, that's a pretty old question. A lot of people have asked this. And one of the examples that I just want to bring in here because I really like it, that comes from the state estimation community, is yes, we can just attach an IMU to a foot, literally attach it to a shoe, and just use the information that a foot is typically not moving when it touches the floor. That's an additional piece of information, and we can use that to ingest that into our state estimation framework, like a Kalman filter. And use the observation that, well, while the foot is touching the floor, it's probably not moving. Use that to estimate all those biases and actually then track the motion of the user from that. Now that's obviously not really viable if you want to do AR/VR because, well, you don't really step on the floor with your head in that case. So in this talk, we're going to focus about another approach. It's the golden age of deep learning. So we're going to use machine learning to learn how humans move as a prior, and then use that to actually as actual additional information to correct all these IMU errors and track human motion over a longer time from just an IMU. Again, we're not the first people to do this. So this is the most related prior work from Furukawa et al. It's pretty exciting. It was published first at ECCV in 2018. And it is predominantly around how to track a smartphone from the IMU within it. It's focusing much more on that use case where you want to track people in 2D, so it doesn't really do 3D motion. And it also directly integrates predicted velocity, so it's very heavy on machine learning and doesn't do much else. We'll use this as a baseline for our proposal for our approach that we are suggesting here. Now, what does TLIU do? I started off with the introduction to give a quick recap of how VIO works, because we kind of take the same backend. So we cut off the vision part. We keep an extended Kalman filter as the state estimation part of TLIO, which takes an IMU, integrates that, and generates an odometry. Now, on top of that, we put a neural network. And that neural network takes in pieces or chunks of IMU data, 1 second windows. And from those, it learns to predict displacements over 1 second plus the uncertainty. So it looks at these chunks of IMU data and predicts how the human was probably moving in that time. The output of that, this prediction of displacement, is then what we use in the EKF or in the estimation framework as like a measurement or as an update to correct the state, correct the biases, and allow it to continue integrating the IMU very well. So we use the output of the network as a measurement in the EKF. One additional thing to note here, we do pre-process the IMU measurements before going into the network using the orientation from the EKF to subtract out gravity, put it into a gravity aligned canonical frame. So the network has to do less generalization in that case. And then we iterate that to actually obtain a fully self-sufficient inertial only tracking system. And this is interesting to look at because one, it actually works extremely well, super surprising. And two, it actually shows what the IMU itself is capable of and how much data actually is in that sensor. So let's look a little bit about on the details of what we're doing here. We're using a ResNet 1D architecture, which is pretty off the shelf. The input to the network, as I said, it's like a time window of gravity aligned IMU data at 200 Hertz. So that's 6 times 200 values, 6 values for the acceleration and the orientation in 3D each, and 200 values because simply we subsample the IMU data to 200 Hertz. And as output, it produces the 3D displacement, so the 3D motion over that 1 second as like a translation vector in X, Y, and Z. We also learn, and I'm going to go into more details of that later, we also asked the network to predict the uncertainty of that. So the network is allowed to produce both an observation as well as the uncertainty for that observation, which can then be used in the EKF. Now, as training loss, we use the log likelihood of a Gaussian, using as data set about 60 hours of diverse everyday activities. So people wearing headsets, walking around, going about their day, split roughly into 80% training, 10% validation, and 10% test data. For this whole thing, it's very hard to get ground truth on like a large scale and diverse motion and so on. So what we do is we use a state-of-the-art visual inertial system to provide like a tracking ground truth or pseudo ground truth for training and also for our evaluations, which is kind of reasonable because that is like very much more accurate than what we expect to get just from an IMU alone. Now, in the extended Kalman filter, we use a multi-state formulation. So in addition to keeping track of the current state of the system, which is the rotation, the position, the velocity, and the gyro and the accelerometer biases, we also keep a sliding window of past states or past poses, which is really nice because it allows to formulate the update, this displacement that the network generates, as a direct observation between two poses in the EKF. So the EKF literally contains like a pose every, I think every 50 milliseconds, and then that displacement just becomes a constraint on 2 of those poses. Afterwards, we can marginalize them out. At the same time, it uses the IMU for integration, so for forward prediction, for the prediction function in the EKF, and obviously still has the cloning to keep that history of past state. So this is quite standard. It's used in the MSCKF framework, and its chances are if you run an AR or application on your mobile phone, it'll do something similar under the hood. Now, something isn't right here. And I'm going to give everybody about 10 seconds or so to think through what I just said or what I just showed and come up with why this shouldn't work. All right, so I'd love to see the audience at this point, but that's not going to be possible with YouTube viewers. So I'm just going to resolve it like this. So there are a bunch of things that should have irked you. Number one, there is kind of like a golden rule in statistics that says never use the same data point multiple times. It's one of the primary ways of coming up with bogus studies or messing up with your state estimation framework. However, in this setup, we are actually using all the IMU measurements many times, a total of 21 times actually. So we run this network displacement prediction at 20 Hertz. Each time it consumes a 1 second window of IMU data. So actually each IMU sample is part of 20 displacement predictions. At the same time, it's also used in the EKF for integrating the motion itself. So each measurement is actually used 21 times. That's not good. Number two, we're actually asking the network to do something that is ill-defined, very ill-defined. So if you think about it, we're giving the network as input data about the acceleration of the system. We are not giving the network input about the initial velocity at the starting point. However, we are still asking it to produce a displacement, which effectively corresponds to a velocity estimate. Now, I put down a formula there that we all have learned in like 6th grade physics class, which kind of says if you want to compute velocity, that's the initial velocity plus the integration over the acceleration. The network doesn't know the initial velocity, and thus it has no way of actually estimating a displacement from the data it gets. That's interesting. It's actually intentional, and those two things kind of negate each other. So in this whole setup, we're using an EKF to do velocity integration, and an EKF can do that just fine. We know how to integrate an IMU. There's a lot of fancy like Lie algebra involved, whatnot. But we've had like as a community, decades of work on that. We know how to do that. What we need from the network is to contribute information that we don't know how to model probabilistically, i.e. prior knowledge on how humans typically move. Now, not giving the network access to the starting velocity stops it from effectively learning how to integrate data. Right? A convolutional neural network can do one thing pretty well, which is actually integrating data. So giving the network access to like an initial velocity and a vector of accelerations would give it a pretty mundane task of just integrating the input data. By not giving it the input velocity, we actually force it to learn something else. Instead, we force it to learn typical patterns in the input data, like those accelerometer and velocity motion measurements, and what typical velocities they correspond to in typical human motion. So we actually force it to learn the thing that the state estimation network simply cannot represent, which is a prior on human motion. That works quite well. And obviously we did a bunch of studies to actually look at what's happening here, and it becomes quite clear that this actually makes sense. So one of the things that we found is that it's quite easy to make the network give better translation or better displacement measurements by, for instance, giving it more data. So here I highlighted a concrete example with those like red ellipses, where we are giving the network, instead of giving it just a 1 second window of data, we actually give it 5 second windows of data to estimate that 1 second displacement. Network gets more data, network probably will produce better outcome. Talking about more input data on each inference, not more training data. And that's actually true. So what you see on the left of that picture is the MSE loss, so the loss function on the training, or the value of the training loss evaluated on the test set. In blue, the values we get for the 1 second window, in green the value we get for the 5 second window. It gets about 3 times better. that's great. However, when we use it in the full end-to-end odometry framework, actually things don't get better, they even get a little bit worse. Why? Because even though every single prediction by the network is better, in the overall system, it doesn't actually generate any new information. The filter can combine those like temporal observations just fine. It can combine the IMU integration just fine. And overall, this seems to not actually help the network to learn the thing we need from it, which is novel information that is not actually in the data itself. So this is an interesting validation that this actually makes sense. Another thing that I want to highlight is that we are very consciously asking the network or training the network so it can predict not only a displacement but also a uncertainty for that displacement. As I said, it's effectively limited to predicting what type of motion is likely in that kind of dynamics setting, which is quite uncertain. And in many cases, there's just no data in the input almost. So the network is allowed to basically say it doesn't know by outputting both the displacement as well as the uncertainty of the displacement as like in this case we took a fairly basic thing and just modeled it as 3 independent sigma values. What you can see in this plot is kind of a visualization of what the network learns to do, showing for each data point on the y-axis the predicted sigma, so the standard deviation that the network outputs, saying like how uncertain it is about its output. And on the x-axis, the actual error compared to ground truth. The red lines show the 3 sigma bounds. So we kind of want everything to be within that cone to be kind of statistically meaningful, and it roughly is. So that's good news. We use an approach that was spearheaded by Eddie Ilk in the context of optical flow. There's a bunch of details on how you formulate the error, how you like pretain without sigmas, how you parameterize something like a variance, and so on. Now this is cool. What are the results? So I mentioned at the beginning we use TLIO a bit we use Ronin as a baseline for TLIO. These plots show the performance over fairly large data sets of many hours of like typical human motion. They show it as a cumulative density function. So the solid line is TLIO, the dotted line is Ronin. To get a fair comparison, because the original Ronin paper only looks at 2D tracking, we actually did 2 things. We extended that implementation to a 3D odometry estimation. And we also retrained it on our data to adopt it to the same head-mounted motion patterns that are present in the training and test data, because we are looking only at head-mounted motion in this paper. Now, what you can see is on the left, it shows the absolute error over like 5 to 10 minute segments of data. In meters and in degree. More importantly, on the right, it shows the percentage drift and the yaw drift degrees per hour. You can see that in terms of drift, we are roughly twice as good as Ronin, with about a median of 1.5% drift roughly. And interestingly enough, actually for yaw, we are better as well. So median translational drift is about 1.3% of the move distance, which is pretty impressive. That means we can estimate just from an IMU your motion down to 1.3%. If you compare that to like the top kitty results like 5 years ago, it's quite close. We have 2 times less translational drift than the primary method that we can compare ourselves to, which is Ronin. We can capture both long-term motion and actually high-frequent details, and you can see that in the videos that I'm going to show in a bit. And one interesting thing to note here is that we also improve the orientation estimate of over Ronin. So what Ronin does is basically just takes a standard attitude filter that just estimates 3D of orientation, very, very standard, and uses that. We actually do more, and this becomes and this actually has an effect. This is interesting because the deep network actually only predicts translational estimates. It does not predict any orientation displacements. So by using these displacement estimates, then in a filter framework, that allows to correct not only the translational motion, but also to backwards correct the internal state of the IMU, specifically estimate those bias values, which then in turn actually improves the orientation. So this is a large sign that the EKF actually does something very meaningful, because it allows a prior on translational motion to also backflow and estimate and better estimate the orientation. So I'm going to show a bunch of videos. I want to highlight here that the video stream that you can see in the bottom left is obviously used to generate the ground truth from VIO, but it's also just here for visualization purposes. It's not actually used in TLIO. What you can see here is 3 trajectories tracking over time of somebody walking around a Facebook building. In blue, you can see TLIO. In red, our implementation of Ronan extended to 3D. And in green, you can see the visual inertial odometry ground truth. And if I let this play a little bit, you can see that actually the blue line is much closer to the green line than the red line is to the green line, which is kind of what I showed in data before. You can also see that it tracks quite well through things that are not just forward walking. Like here, the person is actually writing something on a whiteboard. Now, this is another sequence. This is interesting because tracking planar motion is quite common from things like smartphone. Like that's how your step counter and your fitness app work. This is a sequence that actually breaks that planarity assumption and contains quite a lot of walking up and down stairs. So again, you can see actually the high frequent motion of those 2 estimates that are quite close to each other. And now the person is going to walk up the stairs. You can see the stairs being walked up in the estimation. And as the video continues, person is going to walk up and down that stairs a couple of times. And you can see that estimated here quite well. So again, the light blue line is only from the INU plus a learned model on typical human motion. Looking at that in like a 2D plot actually makes it even more impressive. At least that's what I find. And you can see like the X, Y, and Z estimated over time here. Again, blue and green are actually the VIO that we treat as pseudo-ground truth and TLIO, which are really, really close to each other. I want to especially point out the Z-axis on the bottom here, which is incredibly well estimated over like a handful of up and downs of a stair. And something that you would never get from step counting, for instance, because it is like vertical motion. Last but not least, this is a sequence where the user just plays, where the person just plays pool. So this is a bit showing that the data sets are quite diverse, and we don't just show people walking around, but in this case, actually somebody doing something a little bit more unconventional, which is just playing pool. And again, you can see that actually the green and the blue line mirror each other quite well. There's some drift that accumulates, but otherwise the motion is estimated extremely well. So quick summary. Oh, actually one more thing. This is a slide that shows the failure cases. We have one data set in our data set where the persons are doing kind of what these 2 guys are doing in the XKCD comic that I put on here. It's a sequence where the person sits on a chair and rolls around the office. That doesn't work so well. It's completely unseen in the training data set. And the trajectory goes pretty wild. But that's what we would expect from a learned approach. So in summary, SLAM, odometry, localization, reconstruction using passive vision is omnipresent everywhere, and amazing progress is being made. I didn't actually talk about that, but I think from this overall workshop, that's pretty clear. IMUs are a very powerful complement to vision for local tracking, especially when online calibrated properly and those biases are estimated correctly. They can be extremely accurate over the short term, but suffer from long-term drift over longer time spans. We can track motion from an IMU alone using deep learning. We presented a method called TLIO. I gave the link to the website down here in the slides again. Key to this is to actually carefully understand where to use learning to learn the thing that we can't model, which are the motion priors, and where to just use plain old math and state estimation methods. And overall, this gives really impressive results. This is actually out of date, 1.3% drift, even on quite diverse motion. So with that, I want to conclude my talk and take any questions.
Thank you very much, Jakob, for the great talk. We actually have one question, or multiple questions on YouTube. One is, what's the loss function of the DNN to predict the unused bias?
The loss function of the DNN. So the DNN does not actually predict the biases. The DNN really only predicts the translation displacement. And the loss function, let me just go back to the slide very quickly, is exactly this one. It has two primary terms. One is literally just a mean square error on the 3D translation vector, which is this D, and a log determinant of the covariance matrix, which is the full log likelihood of a Gaussian and allows the network to actually push part of the error into uncertainty if it doesn't know how to predict. But the network does not actually know about the existence of biases. That all is handled by the EKF part of the setup.
Thanks. Another question is, how would you fuse the poses from TLIO with vision?
That's a good question, and we look at that in follow-up work. I think actually overall this is it's covering a bit of a different case. So there are many situations in which you simply just don't want to use vision, and you're okay with coarser accuracy. If you think about AR, VR outside in the world, especially AR outside in the world, which a lot of people think where this is going, putting a camera on your head that continuously films the environment is something that people have objections to. Google Glass has kind of tested that. So there are a lot of situations where you want to be able to roughly track your motion, ideally without having a camera. Also, cameras are quite big, cost a lot of power, and so on. So it's a bit of a instead of rather than in addition to situation here. You can draw that out further, right? There's plenty of situations where vision just doesn't work very well. Think of dark environments, outdoors at night. Think of very, very crowded places, like you walk around in a concert or in like a super busy marketplace where everything that the cameras see are moving people. Being able to still track your motion is extremely valuable there. But it's more of an instead of rather than an and.
Thanks. Another nice question is, have you tested this approach on people taking an elevator? That's one of my favorite tests.
So I can't go into too much detail there. Obviously, it's going to include some interesting challenges. I don't think we have specifically tested it. I do think the data set we have contains a sequence with an elevator, but I don't know where it exactly ended up in this work, whether that's part of the training or the test or the validation set and so on. So we haven't looked into this combined with elevators.
Another question is, can you elaborate a bit on the 1 second time window? It seems too short to learn meaningful priors of human motion. Perhaps there's some intuition you can share about why this is working.
No, but I share your conclusion. So in a nutshell, I have the same thought. 1 second seems kind of not enough, and we've actually tried a bunch of things to get around that, right? Extended to 5 seconds, and I showed that experiment. It actually makes the displacement estimates from the network better, but the overall odometry not better. We've also tried other ways of staggering and doing this. There's a lot of different ways of how you could mesh up the input data or give the network access to additional data. Even tried using a recurrent network that knows a little bit about the past state, but we haven't found anything that really there's a lot of things that you can use to make this much more complex, but none of them really made it better. So we didn't go into too much detail in that on the paper.
Another question is whether you have considered backpropagating through time via the EKF and training with odometry loss, which is essentially the metric that you care about.
Yep. So this is a really good question. I love that question. That's part of the follow-up work that I think makes a lot of sense. And it really boils down to, if you think about what's going on here, we are not using the right loss function in the training. we are using a loss function that basically encourages the network to learn good good samples that are trained completely independently of this like 1 second window displacement. What the EKF wants, it wants statistically independent samples. So it wants samples that are not correlated, and each data point that you use and update ideally should be completely statistically independent. Now, there's nothing right now that enforces that because the network does not know the history of its predictions. One way of doing that is to find a more elaborate training setup that actually trains the network to not only provide nice Gaussians about displacement, but also provides nice Gaussians in a way that the EKF would needs it for good odometry, which probably will mean that they should be statistically independent as one of the main things. That's a really good question.
Another question is, can you with the training data that you have for one IMU or slightly different version of one type of IMU, can you actually generalize to different phones with different IMUs and different activities? So IMUs with different levels of quality, different noise characteristics?
Yep. I think so. We haven't done that in this work simply because the data sets that we're using don't represent that. But the work that we're referring to, which is Ronin, looks at that quite a bit because they are specifically looking at tracking mobile phones that could be in the pocket of the user. I'm not sure how much they go into different mobile phone models, but I'd expect that that's possible as well. There's a lot of things that get very interesting there. So when you want to track mobile phones that are in the pocket of the mobile user, turns out a lot of people don't carry their mobile phone in the pocket. They carry it in like a handbag that swings around, or they hold it in front of them while texting. And actually a lot of the work that Ronan contributed is around actually distinguishing these different cases and dealing with that variety. We're not doing that in this work simply because the IMU is attached to your head in an AR or head-mounted AR setup, and that's the case that we look at.
So, I mean, you often have other sensors. So you might have a magnetometer, you might have a GPS, you might have some Wi-Fi signals. Any thoughts on integrating this in there as well?
Absolutely. Upcoming work. Absolutely, it makes a lot of sense, right? And I'm very curious. Like, there is a lot of things out there that can help also define scale navigation. Magnetometer is one of the things that's actually extremely useful because one of the biggest problems that all of this has is yaw drift. So it's drift around the axis that the magnetometer allows to estimate. At the same time, especially indoors, there's just so much junk magnetic fields around that it makes it really hard to use. So the learning may be a good approach to solve that.
How certain are you about your uncertainties? That's one of the favorite questions I like to ask. How good is the uncertainty estimate that you actually get?
So I showed a pretty picture that kind of shows that they are roughly right. But obviously that's very far from a proof, and there are a bunch of indicators that you could look at that obviously the network definitely does not produce statistically independent samples. It can't do that because it gets these overlapping input data segments, and we actually show that in the paper with a bit more deeper example. But otherwise, I think this is actually one of the key things, and it actually connects to the earlier question about training with an EKF in the loop, because the loss function that we use is a quite rudimentary one. Another thing that we're doing is we're just assuming like a diagonal covariance, i.e. we're using or we're imposing, a sigma for X, a sigma for Y, and a sigma for Z. That's obviously, not the most accurate model as well, especially in an environment where Z direction is quite special because humans tend to move quite differently upwards than they do sideways.
Another question is about potential biases. So you're using VIO algorithm to generate ground truths. Do you know how that changes if you would use another type of ground truth or a passive motion tracking system? Does that have an impact?
We haven't tested that. It's a really good thing to test. I think in that trade-off, we kind of chose data that spans a large variety of environments and allows us to walk around like buildings and so on, which is hard to get motion capture ground truth for. Not impossible, but difficult. I think like we made this underlying assumption that modern state-of-the-art VIO techniques, if you run them on like multi-camera data sets like stereo inertial odometry, is so darn good and so accurate that, you know, if we get anywhere close to that, we're happy. And it's fine to kind of use it as a ground truth for this. But obviously, you know, the VIO actually runs on the same IMU data that we're using here. So there is a bit to be careful of.
Maybe one or two more questions. So one is in the EKF update step, so where your neural network provides the measurements updates, does that network give you instantaneous measurements, or does it carry some form of previous history? So like an LSTM or something like that?
Yeah, so the network does not have any history. It literally takes in one batch of input data and produces one sample. It forgets everything, and then it takes in the next batch of input data. So there is no history whatsoever in the network.
Maybe one final question, which is, now that you have TLIO, can you save power essentially by shutting off the camera every now and then, and just doing everything with vision, without vision?
Probably. But I want to caution that, like, even the 1.3% drift that I showed here, like it doesn't always work, right? There are still situations where it fails, and for like a really good VR or AR experience, you probably still want to use the cameras. Let me put it that way. But as I mentioned earlier, right, there's all these other situations where maybe course location is enough or course odometry is enough, and you actually can't use the cameras simply due to the environmental condition or things like privacy.
Great. Yeah. Thank you very, very much for this great talk.
Cool. Thanks for the invitation.
Yeah, always happy to have you. I see this also as a great way of teaching computer vision people about IMUs.
That was a bit the idea.
Yes.
All right. Happy lunch, everybody. At least for me, it's lunchtime.
Yes, enjoy your lunch. We actually take a lunch break now. So for about 1 hour, we'll continue at 10 p.m. European time, which is 1 p.m. Pacific time. So 1 p.m. in Seattle, or 4 p.m. on the East Coast. So thank you very much all for joining in, and enjoy your lunch / dinner, and talk to you soon.
Yeah, it's all now.
Okay, so it is a real pleasure. It is a real pleasure to welcome the next invited speaker for this workshop, Raquel Urtasun. So Raquel is a chief scientist at the Uber Advanced Technology Group and the head of the Uber ATG in Toronto. She is also an associate professor in the Department of Computer Science at the University of Toronto, Canada researcher in machine learning and computer vision, and a co-founder of the Vector Institute for AI. So she received her PhD from École Polytechnique in Switzerland and did her postdoc at MIT and UC Berkeley. And she's also a recipient of a number of prizes, including 2 Best Paper Runner-up prizes at CVPR. So she's really one of the world leading experts on machine learning and perception for self-driving cars. And I'm really excited to hear what she has to say today. Her talk is pre-recorded, so please enjoy.
Hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at Uber ATG, as well as a professor at the University of Toronto. Today, I will be talking about localization for self-driving vehicles. Self-driving vehicles are one of the most complex and safety-critical modern-day applications of robotics. Leveraging rich maps can enhance performance and safety in areas such as perception, active prediction, and motion planning. In order to leverage these maps, the vehicle must know its position within them. This is the task of localization. Self-driving vehicles utilize high-definition maps, which contain both detailed geometry and semantic information about the environment. These are used for precise localization of the self-driving vehicle as prior knowledge for the autonomy system and for simulation. Self-driving companies are interested in creating globally consistent 3D maps of the world. In the industry, many passes over the same area are required for these maps to be complete. However, we would like to reduce this requirement as this is very expensive. Furthermore, maps typically require large amounts of memory to be stored, preventing them from being able to produce and use at scale. Finally, we would like the maps to only contain permanent elements that we will see every time we drive around the map area. Building geometric maps is typically a three-step process, where the data is first collected by a fleet of vehicles. Map building is typically done from multiple passes through the same area to ensure full coverage and to be robust to transient objects. Then the data is offloaded and the problem is decomposed into trajectory fitting of small chunks, which can be performed in parallel. This is then combined into a massive global optimization problem, which can be solved, for example, with graph slam techniques. The result is high-fidelity maps of our cities. In the video, you can see reconstructions using both LiDAR as well as cameras, which are very complementary sensors for this task. In the reconstruction I just showed, we have removed potentially dynamic objects, which are, for example, moving or parked cars, by exploiting a state-of-the-art semantic segmentation. This state-of-the-art technique is illustrated in the video here. Filtering these dynamic objects is important and results in much crisper maps. This is illustrated in green versus red in the video you earlier just seen. HD maps contain also very rich semantic information. This includes the location of traffic lights, lanes, crosswalks, as well as the rules of traffic at each intersection and road segment. As illustrated here, these maps are extremely complex and a great prior for the autonomy system. These semantic layers are typically manually annotated with very little automation. A process extremely tedious, time-consuming, and expensive. If you are interested in knowing how to automate this process, check out our tutorial on self-driving. The goal of localization is to, given a sensor observation and a previewed map, infer the location of the car in the map. We focus explicitly on map-based localization, that is localization within prior maps, since this is necessary in order to leverage the HD maps described in the previous section, in order to achieve maximum safety. Formally, we wish to model the robot's belief over its state space, where for localization, the state space corresponds to the robot's pose in the world. We denote the pose of the current time by xt, and the observations by z, and m denotes the prior map. The Global Navigation Satellite System, GNSS, is a common source of input, which is often involved in computing initial pose estimates, which are then refined with other sensors, such as cameras and LiDAR. Over the last 3 decades, cameras and LiDAR have been leveraged in a wide variety of localization algorithms, many of which will be discussed later. IMUs and wheel encoders are also leveraged as additional cues, as they provide information that is complementary to the observations from cameras and LiDARs. There is a wide range of representations which can be used for localization, in terms of localization maps. HD maps can be built and annotated with information such as lane boundaries, lane types, signs, etc. These kinds of maps can also be used for localization. 3D geometrical models can also be employed. These models can be represented as dense or sparse point clouds, surfers, or other kinds of 3D primitives. Topological maps are possibly non-metric graph-like representations, such as those found on OpenStreetMaps, OSM for short. They are typically much less detailed than the semantic maps described on the left. Finally, simple occupancy maps can also be used. They are often represented simply as a top-down view of the world. Such maps can also contain additional attributes, such as surface reflectance or color, and have the advantage of encoding rich information about the structure of the world, while also being easier to store than other representations. The main characteristics we would like from a self-localization system running at the scales are low cost, as we naturally want to map very large distances, the ability to localize in real time, high accuracy centimeter-level localization, and robustness, the capacity to handle and recover from failures. However, in order to achieve these goals, there are still several major challenges which we have to overcome. Localization systems must be robust to the presence of dynamic objects in the scene, as these are irrelevant for localization. Geometrically degenerate areas which lack distinctive geometric cues, can also be problematic. These areas are challenging for geometric localizers since observations can't be uniquely aligned to the map. Sensor noise affects all sensors in different ways. Multipath effects can affect both GPS and radar and cause difficulties localizing. Finally, environment changes such as construction mean that localizers must be able to adapt to cases where maps become updated. Now that we have gained some big picture context of what localization is trying to solve, it's time to dive into some of the mathematical foundations of probabilistic localization systems. There are two main parametrizations of vehicle pose using SDVs, short for self-driving vehicles. The minimal parametrization has just 3 degrees of freedom: the latitude, longitude, and the yaw of the vehicle with respect to the map. While very minimal, this representation makes sense for vehicles since they travel on the ground manifold, and the other 3 degrees of freedom, pitch, roll, and height, can be readily derived from the map. The full 6 degrees of freedom representation is more complete and fully describes the pose in the 3D world. It can lead to more robust state estimates, albeit at higher computational cost. It is also required in cases where the on-ground assumption no longer holds, as is the case, for example, in flying cars. Note that we do not only care about a point estimate of the localization, but also a confidence measure over the space. The probabilistic framework allows modeling of uncertainty as well as tracking multiple pose hypotheses and recovering from failures. We have thus established the benefits of modeling a probability distribution over the state space, rather than a point estimate: uncertainty modeling, multi-hypothesis tracking, and recovery from failure, to name the main ones. In this context, we can look at localization as a probabilistic inference problem, that is, estimating the belief over our state space, which in this case happens to be a position. Mathematically, we denote our states at time t as xt, and our observations, which can be later IMU or GPS, using z. We operate under the Markov assumption, where the belief over our state at time t-1 encodes all the information from the past states, allowing us to predict where we will be at time t. We will see why this is a good idea once we have a look at how this estimation is implemented in practice in the next few slides. Note that we restrict our scope to the case of online localization, which assumes a good initialization is always available to solve the problem. We will discuss global localization and system initialization later in the talk. Focusing on discretized temporal dimensions, for example, at 30 Hz, use localization as a recursive Bayesian filter, which can be solved with a simple yet effective algorithm. So right now, I'm going to give a very brief overview of how the Bayesian filtering framework works in the context of localization, but it's worth pointing out that this is a very general framework that is in no way restricted to the task of localization. There are essentially 2 main steps in the algorithm that keep getting repeated over and over as a robot moves through an environment. These are prediction and observation. Each iteration begins with the prediction step. This step uses a propagation model to compute a prior belief over the current state based on of the current state based on the previous state posterior. For localization, this propagation model can be given by a kinematic model, for instance. Since I was here 0.1 seconds ago and my velocity is this is where I will likely be around, assuming if I assume constant velocity. The rightmost term in the last steps belief is the last steps belief, while the middle one highlighted in magenta represents the propagation model built into our system. The second step updates the prediction from the past step based on the current observation. This is what integrates new observations from our sensors into our belief. On the right, we see an illustration of a Bayesian filtering procedure. The state space is unidimensional. It's just a scalar depending on the robot's position in the corridor. The robot on top begins with no idea where it is. The belief over the state space corresponds to a uniform distribution. Then, in the second row, the robot performs its first observed step and notices that it's near a door. However, the pose is ambiguous since it cannot tell which door it is. The robot then moves, applying its transition model to approximately propagate its old belief based on how it moves. This represents the first step of the second iteration. This increases its uncertainty, as denoted by the widening peaks, as the relative motion readings are typically noisy. Finally, in the second step of the second iteration, the robot observes another door and fuses this information with its current belief. This additional information helps disambiguate the robot's pose, allowing it to converge to a mostly unimodal distribution over its location. Note that this example is fully conceptual, since in practice we cannot solve the integral in closed form. Proper Bayesian filtering results in an integral over the state space at the previous time step that is oftentimes intractable. So there are a number of common approximations used to tackle the problem in practice. For example, we can assume that the distribution is unimodal, transitions are linear, and both the noise of the beliefs are Gaussian. This results in a Kalman filter. We can also approximate the integral via Monte Carlo sampling. This is known as particle filter or importance sampler. The third alternative is to discretize the distribution, which results in a histogram filter, which is easier to work with, but can be computationally expensive. So to recap, we can elegantly model recursive Bayesian estimation using a pure mathematical form. In practice, we have to make some trade-offs in order to implement this in a real robot. A Kalman filter is able to produce convenient continuous closed-form estimates, but it is limited in its modeling power. Its unimodal nature means that it is unable to track multiple hypotheses. Particle filters can bypass some of these issues and approximate the quantities by sampling. However, the modes of the distribution can still collapse as the number of particles necessary to model the distribution grows as an exponential function of the number of dimensions of your state space, which can be quite large. Histogram filters can also represent arbitrary system models and arbitrary noise models without risking any sort of collapse, albeit at a much higher computational budget and with limited resolution. However, later on this talk, we will see how we can still leverage the best parts of histogram filters without a large computational cost. A common element in all localization efforts is the need to always integrate new observations. Observations can take in a wide range of forms, ranging from direct census readings like the IMU, all the way to a neural network that perceives the 3D scene from sensor readings. Let's look at different observation models. Real-time kinematic systems leverage differential GPS and inertial measurement units to estimate vehicle trajectories. Semantic matching tries to match cues extracted from sensor observations to maps which encode the prior locations of such cues. Geometric alignment infers the vehicle pose by rigidly aligning the perceived geometry to a non-3D map. Camera-to-LiDAR matching aims to leverage inexpensive cameras to localize against maps built from more expensive LiDAR, either using heuristics or learned feature matching. Place recognition has localization as an image or LiDAR retrieval task. Localization then consists in mapping the sensor rhythms to a previously seen and localized 1BM nearest neighbor search. Finally, LiDAR reflectance matching compares the LiDAR intensity rhythms to the map at multiple candidate locations in order to find the correct pose. In principle, any of these approaches can work with any of the previously discussed frameworks. You can do semantic matchings via a timeline filter, a particle filter, or a histogram filter. You can filter GPS using particle filters, etc. I'm now gonna highlight a few observation models with some of the work that the lab have done in the past few years. Let's look at semantic matching. This approach leverages compact maps of a few kilobytes per kilometer, storing only semantic cues like lanes, signs, turns, and road type, all of which can be stored as vector maps. At runtime, the car must recognize these elements and match them against the vector map to localize. Unfortunately, due to the sparsity of the cues, these approaches cannot achieve centimeter level accuracy and struggle in areas where the detection is challenging. Examples of these approaches include Lost, which require an OSM or OpenStreetMap vector map, and our recent work which exploits lanes and signs for localizing on highways, which can actually automatically create these safety maps and then localize to them. Geometric alignment methods rely on aligning 3D sensor data to pre-build 3D HD maps. These methods can be very accurate, relying on well-established, conceptually simple methods that can be robust to outliers, such as the iterative closest point algorithm. The downside is that these methods require a good initialization for convergence, as registration is prone to local optima. Additionally, the storing and building 3D geometric maps can be challenging and expensive. Despite these drawbacks, these approaches are very popular in the self-driving industry, probably the most popular across all of them. LiDAR reflectance matching. This approach builds a map using LiDAR intensity imagery and matches online observations from the 2D image using simple template matching operations such as cross-correlation. These methods can be much more robust than geometric ones, especially in mostly featureless environments. For example, if you're in the middle of the desert. The template matching itself can also be implemented in a very computationally efficient manner and achieve centimeter level accuracy. At the same time, just like the geometric alignment methods, reflectance matching methods require good initialization. They also have relatively high map storage costs. Through the 2.5D maps used by these approaches are typically much easier to compress than 3D ones, as we will soon see. These methods also require very precise LiDAR intensity calibration, which can limit their scalability due to the difficult nature of this procedure, as when you are working in the self-driving industry, you need to have the same map for a fleet of vehicles. Potentially, these vehicles might not have exactly the same calibration settings. Finally, these methods are typically limited to estimating only 3 degrees of freedom, being unable to directly infer the height of the vehicle. However, as discussed previously, the height, pitch, and roll of the vehicle can be inferred from the map, yielding a good solution. Despite these drawbacks, many self-driving companies exploit localization systems based on LiDAR intensity matching. Our recent work has addressed the need for intensity calibration by learning a deep invariant mapping for matching in an end-to-end manner. First, we pass the online LiDAR sweep and the map through separate, fully convolutional networks to compute corresponding embeddings. Following the histogram filtering framework, we then compute a matching score for every pose within a limited search range of our dead reckoning pose. The search range is over X, Y, and heading, so 3 degrees of freedom. This matching can be performed very efficiently in the Fourier domain with the specialized CUDA kernels, yielding localization times that are real time. The matching therefore yields a 3D score volume, which corresponds to the observation probability in the projection filtering framework that we have reviewed before. This motivates us to go one step further. We incorporate a neural network compression model within this network. To encode the input map to a compact binary code. Importantly, we only need to store the binary code on the card. The compression model is highlighted with the gray box. This compression model is made end-to-end learnable. In other words, learning will decide what information will keep and what to discard. Unlike prior compression work, it directly optimizes the trade-off between compression and localization accuracy, as opposed to the trade-off between compression and distortion commonly used in the general-purpose compression literature. So overall, in this work, we use learning to get robust and compact feature representations. And we use model-based knowledge to formulate the problem and integrate prior into the variation filter. This is a technique that is extremely robust to any calibration issues, and I can achieve 3 centimeter error with millions of maps. As a result, we have reduced storage by 3 orders of magnitude with only a slight accuracy drop. And importantly, our approach is much more storage efficient and accurate than storing maps using standard lossy compression algorithms. Based on our computation, this compression allows storing a centimeter accurate localization map for the entire high-definition US road network in a single commodity hard drive. By combining machine learning with human knowledge of the world, we have made localization more scalable. The take-home message is that when designing data compression algorithms for robotic applications, we should exploit the fact that consumers are robots instead of humans, and our goal is to preserve downstream task performance. Here we show some qualitative results. On the left is our online radar. In the middle is the map, and on the right is the localization result. Vehicle pose predicted by our method is in red, and ground truth is in green. Note that in these cases, we can see that our pose and ground truth pose are almost perfectly aligned. I will now talk about a different topic, which is global localization. The method that we have seen so far have been focused on online localization. The natural question is, how do we obtain our initial pose? And how do we recover when Bayesian filtering method fails? This task is known as global localization. The challenges here are, for example, that the same place can look very different due to factors such as weather, time of the day, season, dynamic objects, and so on and so forth. Another challenge is that obtaining good large-scale training data for this task remains difficult. There are 2 main approaches for this problem, post-regression and retrieval-based localization. Post-regression takes images or later point clouds as input and directly outputs the pose for the car. This method is extremely fast, yet there is a lot of evidence that these methods do not achieve good accuracy at city scale. Retrieval-based methods, on the other hand, are slightly slower and have potentially large memory requirements because they have to store the entire observation dataset, but tend to be much more accurate in large geographic scales. We have investigated the retrieval approaches in the context of self-driving and designed a large-scale dataset and benchmark for this task.
We introduced PIT30M, a dataset for large-scale localization tailored for self-driving applications. For scalable localization in a city setting, we would like a dataset to 1. Be diverse, 2. Cover an entire city, 3. Provide accurate localization ground truth. Our dataset satisfies these 3 criteria and does so at an unprecedented temporal and geographical scale. Our dataset includes images and LiDAR point clouds, each localized with accurate 6 degrees of freedom poses. We also carry a consumer-grade GPS sensor, which we can use to bootstrap localization. Our dataset also provides a set of labels that allow researchers to better understand the limitations of current localization algorithms. For example, we provide sun angle, season, temperature, precipitation, and semantic segmentation as a proxy for occlusion. With over 25,000 kilometers driven, 30 million images and LiDAR readings, and an area of 50 square kilometers collected over 1,300 trips, our dataset is between 10 and 100 times larger than previous datasets released to the community. PIT30M provides a challenging benchmark for large-scale localization particularly suited to autonomous driving. We plan to create an evaluation server for automatic benchmarking and for keeping track of the progress by the community. We hope that our dataset will help researchers develop new and exciting algorithms for this task.
We also did an in-depth benchmarking, comparing multiple approaches on our dataset. The main takeaway point from our experiments is that the strong architectures with simple pooling schemes show excellent performance on this task. In this plot, the x-axis goes from 0 to 1 meter, and the plot indicates what % of the queries are correctly localized within a certain distance. As you can see, GPS struggles to localize even 5% of the images within a meter, which is not good enough for autonomous driving. We benchmarked baselines that are commonly used in previous work, including BLAD, NetBLAD, and LensBLAD. And we noticed that they only localize about 50% of the queries within 1 meter. These methods rely on BLAD pooling, which has established itself as a strong baseline for many retrieval tasks. However, training a ResNet 50 with average pooling performs very well on this task, returning over 90% of the queries within 1 meter, and over 70% within half a meter. Another thing that we can do is, instead of searching for nearest neighbor in the entire database, use GPS as initialization, and then search only within an area of, for example, 20 meters around it. This consistently improves results for all methods, and improves also our ResNet as well. The previous results were all using images only, but we can do a very similar experiment with LiDAR. Obviously, the performance of GPS is the same. The methods that we benchmark here are PointNet with max pooling, PCAN, and PointNet BLAD. These methods all process points individually, like PointNet, and rely on complex aggregation schemes at multiple levels. In contrast, we represent late and inverse view with a versa view representation, which we also use for perception and prediction in our vehicles, and are thus able to treat the point cloud as an image, which we pass through a ResNet 50 with average pooling. We have found that this consistently outperforms other methods as well. We can also use GPS for initialization, which helps most methods. It is curious, however, that GPS can slightly hurt LiDAR retrieval on short distances. This is because sometimes GPS can be off by more than 20 meters, so that retrieval methods initialized with LiDAR cannot recover from bad GPS in that case. Here are some qualitative results of our method. Note that on the left, we show the query, and the first 3 results are retrieved using the image. The last 3 results are retrieved using LiDAR. In this particular example, we see that the image retrieval network finds the same place only 61 centimeters away, but under snow conditions. This means that the network has learned to be invariant to the weather in the scene. LiDAR also finds the same place, but does so with only 17 centimeters error. In this other example, we see the image network retrieving the same place at night. Methods such as NetBLAD, and LensBLAD find images that look similar but correspond to a different place. Once again, LiDAR is consistently more accurate. The final example is a query that does not have a lot of distinguishable visual features for the network to latch onto. Nevertheless, the network can retrieve the same place by finding the same building. Again, LiDAR does a better job, finding an example that is only 12 centimeters away. Some remaining challenges in global localization include using both images and LiDAR. In the example that we described, the network uses images and LiDAR, and we found that fusing information from both is actually really non-trivial. Exploring for generalization of these methods to multiple cities also remains under explored. For example, we would like to train on a city on the East Coast and be able to generalize to cities on the West Coast, or even across continents. We would also like to explore systems that do both global and continuous localization training these two things together remains challenging. Finally, the state-of-the-art large-scale systems for approximate nearest neighbor search rely on data structures that are themselves learned. So jointly learning to localize globally and efficiently find nearest neighbors will be an interesting area of research as well. So to recap, we have first described localization with preview maps. Then we introduced Bayesian filtering for continuous localization. Here we discussed Kalman filters, particle filters, and histogram filters. We then gave an overview of methods for map-based localization, and finally we discussed global localization and its challenges. Important future directions include reducing our reliance on high-definition maps, as these remain expensive to build and hard to get right. Finally, Bayesian filtering typically discretizes time. However, in real life, sensor inputs come continuously, and they are typically at different frame rates, each one of these sensors. So designing methods that explore this fact remains challenging and very interesting. Finally, since we are interested in self-driving, we have to remember that we have limited computational resources on board. So designing systems that can reduce computation to do localization and other tasks such as perception, prediction will be a very interesting idea. Thanks for your attention. This is all from me. Thank you.
So since Raquel is not here with us, this was pre-recorded talk. We will move directly to the, so there will be no question time, no direct questions. We will move directly to the next invited speaker.
Okay. Hi, I'm Wunshan Wang. It's my pleasure to introduce Katerina Fragkiadaki. Katerina is an assistant professor in the machine learning department in CMU. She received her PhD from University of Pennsylvania in 2013 and was a postdoc in UC Berkeley and Google Research between 2013 and 2016. She has done significant research on video segmentation, motion dynamics learning, and on the area of projecting geometry into deep visual learning. Katerina's group develops algorithms for mobile computer vision and learning of physics and common sense by watching and interacting with the world. She received a Best PhD Thesis Award in 2013 and served as the area chair in CVPR, ICML, ICLR. Very recently, she got the NSF Career Award from NSF-IIS. She is an author of the SFMNet, Learning the Structure and Motion from Video in 2017, which has drawn a lot of attention and have many follow-up works since then. She pioneers the work of GRNN, Geometry-Aware Recurrent Neural Networks, in 2018. I have the privilege of working with Katerina in a recent project. I remember last week during the discussion, which is quite impressive. She asked her students to focus on the problems that are really going to make the difference and focus on the research that really makes things work in real life instead of doing incremental research or just improving the implementation. So I think that's quite remarkable. We can also see the same rationale behind her published works. So I'm looking forward to the talk. Let's welcome Katerina Fragkiadaki.
Yanshan, thank you for your kind intro. Shall I try to share my slides, my screen?
Sure.
Okay. Well, I'm supposed to be sharing now, right?
Yeah, we can see that.
I see. Okay. Thank you. That's very sweet. Thank you for your invitation and your introduction. So today, what I'm going to talk about will be less of how do we get learning-based SLAM, although I'll show you how we try to do our learning-based ego motion estimation. But mostly, what can you do if you have such ego stabilization? How can this help visual learning and visual understanding? Okay, and I'm very sorry that, you know, it's very bright, the screen. I'm not sure how to fix that one. So here is a baby, and we put a camera in its head, and the baby moves around actually must be a 1+ year old because it can, walk quite reliably. It didn't fall throughout the video. And this is actually the data that we get. And as you see, there is a lot of zoom in, zoom out, tons of viewpoint variability, lots of occlusions. And it's hard to parse this type of videos with CNNs. It's hard to parse. Why it's hard to parse? What is the problem with convolutional neural nets of passing every individual frame through a CNN? Well, first of all, there is no object permanence. CNNs process each image independently, right? And if the camera moves and an object falls outside of the field of view, then it's not represented anymore. Objects change size, both in the image as well as in the deep feature maps. Objects move with camera motion, and all those problems are due to the fact that the camera motion, the camera viewpoint is entangled with the appearance of the scene in those feature maps. And here is SLAM, which actually is pretty hard to beat, this Orber SLAM 2, V2. You take as input a scene, and here, despite the fact that there is a lot of camera motion and so on in the video, the output, you see this disentanglement. We have disentangled how the scene looks like. You see this point cloud map and how the camera moves, right? So now that this is good. And objects persist, like the teddy bear was in some frames, was out in some other frames, but in the map it's still there, right? So we have object permanence. This is great. This is some basic spatial common sense. But what is the problem with SLAM? Well, I wouldn't say that the problem is moving objects and so on. I mean, we can learn eventually, we can learn to discard those and so on. The problem is that a SLAM cannot imagine, unless you see a part of the 3D space, you cannot actually represent it in the map. Despite the fact that you may have seen many similar scenes, you cannot actually learn with experience. You still, at the next time that you go in the similar scene, still you need to go around to be able to capture the full 3D scene. And this is not how we humans do it, right? If I've been in many similar scenes, next time, even from a single view, I can imagine the full thing. So this talk is how can we use LAM, simultaneous localization and mapping techniques to help deep visual learning, and how can we use architectures that are such SLAM-enabled deep network architectures to actually learn visual representations without human supervision. So this is the geometry-aware recurrent nets that Yenshan mentioned that actually take multiple images as input. The images can be RGB or RGBD, right? And associated depth maps. And what they build as a hidden state is a 3D feature map, all right? Much similar to SLAM. So they try to build a 3D map of the scene, and in terms of this voxel grid, and every voxel is represented with a long feature vector, okay? And the two main innovations of GRNNs over previous either RNNs or LSTMs and so on is that the hidden state, the bottleneck of the network, is 3-dimensional, which makes this feature map, what I show here with colors, is 4D, okay, X, Y, Z, and the number of feature channels. So that's number one. And number two is the way they update the map over time. They actually compute ego motion, much like SLAM, and then they use the output of ego motion estimation to update the map in a way that I'm going to describe right now. So I'm going to discuss about a very simple video going around the toaster. Actually, yeah, I think it's a toaster. So here is a toaster image. So what we do is we first unproject, we shoot a long rays, RGB values, and populate some grid, okay? And this grid is super incomplete, right? Because it's just computed from a single view. So lots of holes in that grid. But then we pass it through some 3D CNN, 3-dimensional convolutional network, and we actually, whose job is to imagine, whose job is to paint the map. All right, so here's the map. And here's the next frame where the camera has moved, the scene hasn't moved, but the camera has moved. And again, we'll unproject. So this is a differentiable unprojection operation. And again, this gray is pretty incomplete, but we're going to densify it, and our CNN will become better and better by looking more and more scenes. It's going to become better and better at imagination, at painting the missing details. So here's what's going to happen. We are going to compute ego motion between the map from the first frame and the current frame, and we'll use the output of egomotion, which is a 3D rotation and translation, to actually rotate and translate the current map before we fuse it with the map of the previous frame. So this explicit feature transformation, which is just a parameter-free layer, right, that transforms features based on estimated egomotion using dense transformers, essentially make sure that information from the same 3D physical viewpoint, from 3D physical point, end up nearby the map, right? Because otherwise, the CNN, if the camera moves, you know, and then the same thing moves in the pixel image, there's no way for the CNN to associate them with its small kernels. Of course, transformers would help you, right? So explicit attention would help you. But here, on top of everything, we also have the stable 3D model of the scene. Here's a new frame. We'll do exactly the same thing, estimate egomotion, update the map, and so on. So this is like, so this 3D feature map now is the bottleneck of the network. Is geometrically consistent because it was built to be geometrically consistent, okay? And we can learn this whole network end to end from our favorite end task. But before we do that, we want to show that, look, despite the fact that the corner of the toaster is moving in pixel space, after the explicit transformation with this stabilization of the feature, right, that uses the pose estimation and how camera moves, essentially the same point lands in the same place in our mental 3D feature map, in the hidden state of our network. All right, well, it's all over the place in the 2D, and here you can see it. Here is a 2D RNN or 2D conval STM or GRU, what such a model would do. Well, unfortunately, there's no egomotion estimation during representation learning. So now the corner moves. The corner moves in the feature maps, the blue feature maps, and because the hidden state is updated convolutionally, this same corner lands all over the place in the hidden state. And now what dictates the hidden state is how the camera moves as opposed to how the scene looks like, all right? So things won't generalize across different camera motions. So what can you do on top of this geometrically consistent hidden state, which is like a map of SLAM, but is like in painting, and I'll show you what it means by in painted. It's like completed as opposed to just what you see from the visible views of the current video. Well, our favorite task for computer vision is detection of objects, and you can do exactly the same thing here. You can do 3D object detection. And so how are you going to do that? Well, you're just going to feed a Mascar CNN type of output on top of the feature map. Everything is differentiable. You can train it end to end if you have 3D object boxes, all right? And the only difference with Mascar CNN that takes 2D images and spits out 2D bounding boxes. Here we're going to be feeding 3D feature maps as opposed to 2D feature maps, and we'll be spitting out 3D bounding boxes. So the anchors also are 3-dimensional and so on. But beyond that, there is no other difference. So what you've gained is that even if your camera moves, because the 3D feature map stays there and the things do not actually disappear, objects persist over time. The features persist, so the objects also persist over time. So those operations have essentially this geometry-aware recurrent nets built-in object permanence in the neural network, all right? Because despite the fact that things move in and out or get occluded in the 2D observation stream, they actually persist and they don't interfere with one another in the 3D feature map, in the latent 3D feature map. The most exciting thing, though, regarding those networks is that you can train them unsupervised without human annotations just by predicting views, predicting how things look like from different viewpoints. Okay, so this task is called view prediction. It's a famous task because people think that it's biologically plausible that the brain learns by predicting observations in different levels of abstraction. Okay. Yeah, so let's see how to do it. Of course, you can do view prediction without having a geometry-aware neural network. You can have a bunch of frames. You can even fit the ego motion of some form, like concatenate with the image, and essentially train your architecture to do exactly the same thing, predict views. In fact, that's going to be our baseline. But here we'll show how a 3D bottleneck, this architectural bias of putting a 3D-dimensional neural bottleneck as well as doing ego motion stabilization while updating that bottleneck actually will allow you to generalize dramatically better, all right? So how does view prediction work? At training time, you collect a bunch of views. You make the 3D feature map by passing through the GRNN. I give you a query camera viewpoint, then you rotate the map to that camera viewpoint, and you project And again, everything is, differentiable, and you decode into some RGB image, all right? And then you backpropagate the gradients. And as we said, this is a self-supervised task, so you can train it with as much data as you like. Okay. By the way, at training time, you can have multiple views. At test time, you can just feed a single view. That's totally okay. So now let's see what happens. Let's see some results. So these are the different input views that I feed to the network. These look pretty simulated scenes, but soon we're going to go to real scenes. Okay. I just feed 3 different viewpoints with the corresponding RGBs. There's no depth here. And I let the network imagine the full scene, and I record the video. And here is the video is playing. And the cool thing is that you can compare the geometry aware recurrent network with another, neural architecture that does not have such a 3D, architectural bias. So there are some artifacts when the GIF is running multiple times. By the way, the same video is just iterated again and again and again. And you see that in the second 2 rows, you have scenes with more objects, and our model was never trained with scenes with more than 2 objects, and still it can generalize to scenes with more than 2 objects, while the other network that has never used a 3D neural bottleneck or any type of SLAM or geometry in its architectural biases, it cannot generalize. I mean, you feed it 4 objects and it still sees 2 objects. I think this is super important. How we can strongly generalize to novel scenes. And this all comes from the fact that space is represented in the bottleneck of the network in a nice way. So this was a simulation. And the question is, how can view prediction help us learn visual representations outside of the toy simulation worlds? And the answer is that yes, view prediction can still help us, but because the visual world is very multimodal, we may want to change the cost function. Instead of regressing to RGB values, we will be predicting features, and instead of RGB regression, we will be doing contrastive feature prediction in the following way. So here comes again the architecture. We have frames 1, frame 2. We have unprojected them and make a 3D feature map of the scene that the images depict. Okay, so this is this colored cuboid. And here comes a query view. And again, we compute the features from that view and the corresponding map. And we estimate, the first thing we do is we estimate the relative pose of that view from our current map. And what we do is we orient our map and even project it to 2D with some 2D network similar to the one that we use for predicting images. But now, instead of predicting 3 channels, we predict, let's say, 64 channels or whatever we want the number of feature channels to be. And then the same query view, we feed it through what we call a bottom-up 2D CNN. And what we do is we put some voxel-wise or pixel-wise contrastive losses there. So we have two of those. One is in the 3D space and one is in the 2D space. Okay, so the idea is that the map that I have built, when oriented to the query viewpoint, it really better match voxel-wise the 3D map of that target view, either in the 3D space or when it projected to 2D, as opposed to any other voxel or every other pixel feature vector. And the same tricks hold here for any type of contrastive learning. It's good to have a big sampling of negatives. You can use dictionaries, like recent papers suggest, outside of the current batch, if you want to sample more negatives and so on. And these are all helpful to help learn good features. And that's it. All these weights in this slide are learned end-to-end. Nothing is initialized. They're trained from scratch. And what you do is so I'm just visualizing now the 3D feature map from overhead, because you can visualize, you can project that map and visualize whatever you like. So here's how things look like. I mean, you can kind of track the cars and so on. And indeed, we have some follow-up work that we show that, yeah, these features are useful for 3D tracking. You can initialize a box and track it just following those features and just doing cross correlations of those features discovered from view prediction. So no annotations ever. And another test we did with those features is we use it as pre-training for 3D object detectors, the same task that I described earlier. And what we saw is that, yeah, it helps. And view contrastive prediction helps more than view regression, okay, of better pre-training, let's say, for 3D object detectors. But what else can we do with those architectures? We know that people can detect and segment objects in 3D without ever using any mask or 3D box, okay? They can detect and track without any supervision. So can we similarly discover objects without any annotations? So some things that we've tried to do with those architectures is the following. We take 2 frames and we stabilize them based on ego motion. And once we stabilize them, then we compute motion between those feature maps. And for this particular scene, which is a static scene, once you compute motion after stabilization, all these motion fields should be 0 because the camera motion has been factored out already, okay? So here is a dynamic scene. So far in the talk, we've only been looking at static scenes, like without independently moving objects. And here is how the map looks like if you superimpose 2 different feature maps before, stabilize them with ego motion estimation. And here is on the right is how it looks when it's stabilized. And you see when things are stabilized, the moving objects pop up. Unfortunately, other things also pop up because the features are not like perfectly slow. And in fact, this is the ongoing work. What is the golden architecture that can learn imagination of visual features beyond occlusions from single views that, you know, can generate slow features and so on and so forth. So we've been working on that front. But even with this kind of extremely naive 3D CNN architecture, still you see that, you know, the moving objects pop up, and then you can discover those flows. Like any optical flow in that 3D space that is non-zero signifies a moving object. And recently we even went beyond that, and we use larger time horizons to discover objects without any supervision in 3D. So this is discovery of objects in 3D, not in 2D, because of course all traditional video segmentation literature can segment objects in 2D, okay, by, you know, clustering point trajectories or something like that. And we've compared with, you know, using depth maps and ego motion. And because our model can in paint, can imagine, can actually, you know, predict the full extent of objects as opposed to only what's visible from the current view. All right. So we have endowed our architecture with the ability to imagine. So another thing you can do with those architectures is, can we organize our visual world into prototypes? All right. You know, there is this dream of building a knowledge base, a visual knowledge base, so that we can parse any new image in terms of that visual knowledge base. And the question is, what is the right representation from that visual knowledge base? What should be our visual prototypes over which we'll be parsing our images? And yeah, so I would argue that 3D is a good representation. Look at all these crazy variations. You know, there is a lot of different visual variations, but it's all the same 3D objects. So if you, you know, represent your prototypes in terms of 3D feature maps, right? There is all the variability depending on pose and scale and motion. You can factor it out during matching with the architectures that we just discussed. These are some data sets that we have used. Look at this nice replica data set. Is simulation, but it looks very, you know, like the real world. And what you see is things that look very similar in 3D. Once you project them from camera viewpoints, they look actually very dissimilar. All right. So that's it. So then if you want to discover concepts without annotations, without anybody telling you that actually this sofa is similar to that other sofa, all right, or this sofa with that, how to say, green pillow on top of it is not a sofa, it's actually a chair, like an armchair or something, is very similar to that other armchair with a white pillow. And if nobody wants to give you this annotation, then, well, maybe it's worth going into a 3D feature space, because in 3D feature space, the same objects, if you look at their feature context and you know, scale them and you search over the rotations, then you may really manage to get them to match. While in 2D projections, they actually look very different. If you project the chair from different viewpoints, it actually looks pretty dissimilar, right? So the important thing here, so here I'm showing the output of our system. And what this system does is it spits out 3D bounding boxes. And then it says C33. This means prototype 33, cluster 33. And then dash R40, this is the rotation. So basically, you discover sometimes of prototypes, and those prototypes are also represented in terms of 3D feature maps, okay, X, Y, Z, and number of channels. And then, you know, concurrently, you are learning a 3D object detector, which is initialized from, you know, a state-of-the-art 2D objectness detector where you kind of triangulate different detections from different viewpoints. So you iterate between detection, clustering, prototype learning, and then detection, again, clustering, prototype learning, and you know, kind of improve the detection over time. And essentially what you land at the end is a set of prototypes like those. Here we show the banana and the grape and the lemon and apple and so on. And then the images are parsed with respect to those prototypes by indicating which prototype it is, for example, cluster 10 or cluster 6 and so on, and in which rotation, okay? And all the different poses of a particular object, let's say broccoli, and all different scales are all explained by the same prototype, okay? So if you go into parsing, it's much more helpful to have your prototypes and your templates in that 3D format. Okay, so we did this in Carla and in the replica dataset and in some more simplified simulation environment and so on. But basically the hope is, yeah, you should be able to do this in any photorealistic scene. And yeah, we are using ego motion and depth, but we also use that in a real world scene where ego motion was actually given by some SLAM system and so on. And again, we parse in terms of clusters and rotations and so on. Yeah, and since this is a learning-based SLAM workshop, I just want to discuss our architecture for ego motion estimation. I mean, it seems that they're much, much better out there, but the idea of what we're doing so far is you have a map, you have the current frame, you lift them into 3D feature maps, and essentially then your neural network looks exactly like an optical flow with all the tricks of state-of-the-art optical flow, like coarse to fine, cross correlations, and so on and so forth. But instead of predicting dense 2D motion field, it predicts a 3D rotation and translation. And the other thing that you can do is, despite the fact that the point cloud is not complete, our 3D feature maps are always complete, okay? And if you want to see how the R ego motion and learning-based ego motion estimation is compared to a state-of-the-art ORB SLAM, let's say, well, it is not that great. Let me show you the numbers in the validation set of Kitty. Well, is 1.6, while ORB SLAM is 0.2. However, if you blow up the resolution with sparse convolutions, which we're going to do, and if you, so that's number one you can do. And if you also add a small motion CNN, exactly like optical flow V2, like the FlowNet version 2, where they have some neural network specialized for small motions, then you can drive that 1.6 lower. And I think the interesting is how you can play with the architecture and have dramatically different results. While I would say the traditional SLAM architecture is kind of plateaued. I mean, it's hard to improve upon them more. Yeah, of course, it would be fantastic to have a great ego motion estimation method that at the same time can also infer things from single view, simply because it has seen, scenes and objects, how things look like from different viewpoints. So I'm going to stop here. I'm just going to say that domain knowledge from simultaneous localization and mapping, a traditional geometry-aware SLAM can inspire neural architectures that can help generalization of deep networks for visual parsing. And yeah, and then we talked about ego motion stable 3D neural representations that help inject spatial reasoning to deep nets. We talked about object permanence. Can learn without supervision by view prediction and neural background subtraction, okay? And can help organize the visual world into a small number of prototypes by increasing compressibility thanks to the 3D nature of the, let's say, parsing element, the prototypes that can explain different poses and scales and so on. And that's the end. This is the papers that I talked about, and these are my students. And thank you very much again for inviting me.
Okay. Thank you so much, Katerina. Here's a couple of questions from our audience on YouTube. Just to read them. One from S.Y. Chen. He is asking, how do you determine the size of your 3D hidden features field of view?
How do we decide how big is the map, for example? Okay, so this map, when you have a moving car, right? That map naturally moves with the car. Okay, so the answer is the following: you just pick the biggest map that GPU memory fits, and the higher resolution, the better. And resolution is a huge problem, and we have worked with sparse voxel grids, and this definitely help. But the idea is that, you know, whatever fits in the GPU memory, imagine we're using our batch sizes are 1 or 2 or something crazy small, because yeah, these feature maps are pretty big in memory if you don't do something smart like sparsification and so on. Now, your question would be, okay, why don't you always sparsify? Well, the thing is, when you do view prediction, right, you do not know ahead of time what will be occupied or not from the other view, okay? So that's one difficulty. Yeah, so this is what we do. We put whatever big, whatever the biggest possible map that fits in our memory. Also, I need to tell you, since we're estimating camera motion, we know exactly what the camera is looking at. We know if the camera is looking outside of the map so that we can move the map to the right. Okay, so this type of memory allocation and management happens all the time in the network. Yeah.
Okay, one follow-up question from mine is like how large exactly are you using for now? Like
how large is what, the 3D feature maps?
Right, like if you take, for example, on KT dataset, how large is the feature map?
Yeah, it's like 100 by 100, and the height is much smaller. It's like maybe 16 or 32. This is the spatial dimension, and the feature may be 128 or something.
In meters? Or what's the unit?
Oh, in meters.
Okay.
Okay, so I do not know. The student knows how big is a voxel. I think a voxel is maybe 0.25 meters or something like that. Now I need to tell you something else. When we track, for example, we want to track objects here, right? And unsupervised. We detect an object, and then we create another map that is object-centric and really launch also that particular object, okay? So the truth is the following. With this type of architectures, the zooming in, zooming out, the foveation, all the time looking at different parts of the map and blowing up the resolution there is absolutely necessary. I think even if we go away from, you know, kind of extremely memory consuming voxels and we go to point clouds and feature clouds and so on, still foveation and zooming in different parts of the scene based on what you want to do is still extremely important. In fact, we saw it, like our tracking results went dramatically better once we were zooming on the objects that we were tracking. Okay.
Okay, cool. Here's another question. Instead of using 3D voxels as hidden feature, some other works use 3D mesh as hidden space based on PyTorch 3D. What do you think of these approaches?
3D meshes. Yeah, and these meshes, do they have features on their kind of nodes or not? That's the question. So so I may not understand the question correctly, but if the understanding is, you know what, take an image and predict a 3D mesh, which is just an arrangement of you know, many points with triangles and so on. So we did work on that before. For example, we're trying to recover 3D meshes of humans from videos. The problem with mesh is that it's very hard to be done if you don't have a low parametric model of that mesh. Okay, like you cannot just take a picture of my office, you know, which is absolutely messy and has tons of different objects and has even, you know, this type of paper towels and so on, that is very hard to figure out how to encode it in a mesh. While in the 3D feature map, you really don't worry. You just put the features there and you're saying, you know, those features are going to capture that paper. Whatever is the feature is going to be trained end-to-end from the final task and so on and so forth. In fact, that's exactly our problem with the meshes, that you really need to specify the geometry and the topology and so on. Yeah.
Okay, great. Path, here's another question from Path. Prototypes are rigid, which seems a big problem, and doing a rotation check over all angles seems extremely computationally expensive. What do you think of the problem?
Right. Could you repeat the question louder, please?
Okay. Prototypes are rigid, which seems a big problem, and doing a rotation check over all angles seems extremely computationally expensive.
Sure.
What do you think of that problem?
Yeah, sure. I'll tell you what I think. So this is our very first step. It's absolutely a baby step. rigid is bad. I'll tell you one progress we made, which is not a lot of progress, still rigid, but now we disentangle the object into content and style, and we only use prototypes of content or prototypes of style separately, and styles are 1D and contents are 4D, exactly like that. But absolutely, this is exactly what we're working on right now, how we can learn deformable prototypes, articulated part-based models to represent the objects. That's number one. Number two, this thing that you said with the rotation, that is true. It is extremely time consuming. First of all, it can be parallelized. You don't need to search every view separately. What I would imagine is that if we want to do 3D parsing, we really need to couple it with a policy learning that says, oh, based on this, which object shall I search first? And when you search for objects, you forget about the 3D arrangement. You can pull across the space, make some 1D vector, pick up your top 100 categories, then search there more. But you will see many people saying that, yes, inferring the right pose is actually very, very time consuming. It's much easier to tell me that this is a pen and much harder to tell me if the pen is facing upwards or downwards. Even for humans, it takes much more time to infer pose than to infer the label of an object. Yeah, that's my answer. Okay. But this is an excellent question.
Okay, so is the 3D representation limited to a single object, or the motions have to be around the specific object to let the model to learn enough to build a reliable 3D representation?
Yeah, I think the question is, do you put the objects in the middle of the scene? Maybe this is the question. No, you don't need to put the objects in the middle of the scene. The only reason to put the objects in the middle of the scene is resolution. If we had infinite resolution, we would put, a humongous grid, then we'll run our detector, focus into objects if we like to zoom in and more and get high resolution prototypes and so on. No, it shouldn't. In fact, the whole point of this architecture is that you don't know where the objects are, and you do this thing so that to infer where the objects are in the first place. In fact, the 3D detectors do very well on top of those representations, because things in 3D do not interfere with one another and so on.
Is the example of identifying cars from 2D image, in this example of identifying car from 2D image, how does the model learn the 3D representation of cars that are robust to changing of the background?
Great question. So how does it? Well, first of all, the first thing you do with this prototype thing that I mentioned is that you do view prediction. You go around tons of scenes, you do view prediction. So your network has learned to look at the backgrounds and so on, of any type of different background. Now I can tell you some super recent thing that we've done, which is the following. These neural 3D, I'm very excited about, but it's just extremely recent, so it's not like super mature. You have those objects, and then you have the background scenes, right? And our networks essentially disentangle background scene from objects. Then you can take those feature maps, go in your favorite new background, for example, your new kitchen, build a 3D feature map because it's a static environment, and then paste, like imagine pasting objects and different lemons and so on against this new background, right? Because those representations are spatially disentangled. And then you can create new training data for you, and you can train your object detector on top of those compositions, right? Because these 3D new representations are compositional, you can mix and match and so on. And now your object detection, where you learn the lemon against the gray background or against the kitchen of your friend, now you can detect the lemon in your kitchen by this imagination, okay? By this imagination type of training data.
Right, yeah, that sounds really interesting. Maybe let's end with the last question. So in terms, because the SLAM, you have already shown that using SLAM can facilitate the object detection, can help learn this 3D representation. So I was wondering, how can we use this 3D representation in terms of navigation, not other tasks like localization and navigation? You have already shown some example of. Yes,
very nice. All right, so the other way around. So first of all, I think the works of Saurabh Gupta and Devendra Shaplot and right, so they do use their 3D. No, they don't use 3D feature maps. They use 2D feature maps of the ground floor, because for navigation maybe it's not important the vertical dimension as it's important for manipulation or object detection and so on, right? And yeah, they do use those feature maps. They learn to paint, they learn how to move in those maps. So I would say it actually sort of started with completely unconstrained feature maps. Like basically every point on the floor could save whatever 1D feature vector it wanted. But it seems that in a recent actually CVPR 2020 paper, they just predict occupancy. They learn how to predict occupancy so that if you open your eyes from a single view, you can have a ground floor map of occupancy, right? Which is good. You don't need to go around to figure out if it's empty or not. So that's great. Now, how to do better ego stabilization? I'm pretty sure that eventually, you know, such a neural net will be able to spit out awesome ego motion. I think resolution is important. And the neural network architecture, I remember it also took quite a long time for optical flow to be learning based completely, right? From a flow net versus, you know, traditional method. And this had to do with the architecture. We had to specialize. In fact, it may have happened already and that I'm not just aware. I do expect in this CVPR or maybe even earlier that already there is some neural net that spits out pretty awesome ego motion. I think it's a matter of architecture, searching the right architecture bias to do exactly that. Yeah. So we are working on this because ego motion measurement is crazy important for this work. Mm-hmm.
Okay. Thank you. There's more questions on the YouTube chat. So if you have time, you can interact with them after the talk. Okay, thank you,
Sure.
Katerina.
Yeah, you can send me an email with the questions. Absolutely, yeah. Right?
Mm-hmm. Okay, great. Right. Thank you.
Thank you so much.
Okay, so let's move on to our next speaker. Deva Ramanan. Deva is an associate professor at Robotics Institute at CMU and a principal scientist at Argo AI. Prior to joining CMU, he was associate professor at UC Irvine. His research interests are computer vision and machine learning with a focus on visual recognition. He was awarded the David Marr Prize in 2009, the Particle VOC Lifetime Achievement Prize in 2010, NSF Career Award in 2010, and UCI Chancellor's Award for Excellence in Undergraduate Research in 2011, the PAMI Young Researcher Award in 2012, one of Popular Science Brilliant 10 Researchers in 2012, and the LeGrant-Higgins Prize in 2018 for fundamental contribution in computer vision. He is on the editorial board of International Journal of Computer Vision and is associate editor for PAMI. He regularly serves as a senior program committee member for CVPR, ICCV, and ECCV. He served as a program chair for CVPR 2018. He also regularly serves on NSF panels for computer vision and machine learning. Deva is one of the authors of very popular dataset, Microsoft Cocoa. He has published many influential papers on object detection, face detection, object tracking, activity detection, and so on. So next, let's welcome Deva to give us a talk.
Okay, thank you for the gracious introduction. Can you hear me?
Yes, I can hear you.
Okay, great. All right. Okay, so I will be talking about learning to understand the geometry and motion of dynamic scenes. This is very much work led by Gengshen Yang, who'll be presenting a part of this, some of this work at a talk on Tuesday, and then Pei-Yun as well. We've collaborated with Gengshen on 1 or 2 projects. Okay, so first some setup. I guess I don't really have to motivate why we care about scene geometry given this workshop. I will say that for my own self, it was a bit of a realization that I've tended to work historically more on high-level recognition problems, like object detection or activity recognition. And then in the time I've spent looking at perception for autonomy, it becomes very painfully obvious to me that the crucial question seems to be much more about geometry, of understanding what's out there in the world and how we can navigate and interact with it, rather than, let's say, naming it. The canonical example I give is if a trash can falls on the street and a bunch of debris comes out, I probably don't have detectors for every piece of garbage that's in there. but it's much more important rather than naming the garbage, just to know geometrically what's there and how it's moving and rolling around. So I think of it as somehow, this to me is much more open world recognition, which I think is going to be a crucial part of actually getting autonomy to work. So what are some particular challenges that may or may not be emphasized? So one thing that wasn't clear to me is that I think there's a huge difference between understanding the geometry of a static world and understanding the geometry of a dynamic world. And one of the really sort of scary cases is when let's say people walk out from behind an occluded car. Like here's an example. So what's happening here is that the geometry of the world is actually changing quite fast, and it's quite fast and non-continuous because of occlusions. And so that means you must be able to rapidly figure out dynamic changes of the scene. And that's really hard, because if you want to rapidly react to dynamic changes of the scene, then how do you know your estimates aren't just flickering over time? So maybe you want to reduce flickering by enforcing some temporal consistency by smoothing over time. But then if you do that, you reduce your ability to react to dynamic changes. So that to me seems like a fundamentally hard challenge. The other big challenge is that, especially as we move toward deep neural approaches for these solutions, to what degree are we kind of hallucinating the geometry we expect to see, versus to what degree are we actually measuring the geometry that the data is telling us? And the reason why that distinction is so important is that I think that's why LiDAR is such a powerful tool, because it's purely measurement based. It's not prior based. And so even if you have prior expectations that don't jive with what you're seeing, the data is golden. It tells you that there's something there even though you didn't expect to see it. And then finally, I think it's become super important to not just the way that we measure accuracy and success. It's not just, for these safety critical applications, I've heard before that we need to get to 100% accuracy or 99.999% accuracy. And personally, I think that we're not going to get there, but I think what we can shoot for is graceful degradation. So that when we do make a mistake, when we misestimate the geometry of a world, we do so in a graceful way. And so these kinds of challenges, one of the things that we've been thinking about as a philosophy for addressing them is, well, how do biological agents, how are they able to navigate in a world? Flies and rodents can seemingly move around in a dynamic world that's changing and understand what's happening. And furthermore, there's various human vision experiments that suggest that humans are actually technically not that accurate in estimating 3D metric geometry. I don't really know the number of millimeters to that corner of a wall, but it's kind of remarkable that if I don't know that, how am I able to navigate something moving at 60 miles an hour? So I'm gonna talk about some representations and approaches that are inspired by how we think humans might be doing it. Okay, so first I want to sort of start by motivating a lot of the low-level analysis of geometric estimation, such as like estimating stereo disparities and reconstructing the world from that, or even understanding how things move over time, local optical flow. The heartbeat of all of those approaches is really correspondence. In terms of stereo, if I have one point on the left image and I search over a scan line of possible matches in the right image, and if I can find the right one, that tells me the disparity of the depth. And for optical flow, I'm basically doing the same thing, except that now instead of searching over a 1D line, I'm searching over a 2D window. So I wanted to talk about some approaches that we've been pursuing for kind of neural modifications of these architectures that I think are kind of rapidly advancing the state of the art. Okay, so in order to sort of describe the approaches, I want to first just recall how would we classically do this? If I was doing stereo or optical flow, what I would first do is extract local features at every pixel, XY pixel. Then a lot of approaches classically compute what's called a cost volume, which is for every pixel in the left image, I search for possible candidates in the right image. And then I compute the match score or the match cost of corresponding this pixel with this pixel. And I'll store this essentially in a 4D array. That's X, Y, by U by V, where the UV is the search window. And if you have this cost volume, a naive approach might say for every XY pixel, just find the minimum cost UV offset. And that's sort of the simple way of finding optical flow vectors. And if you want to be, essentially there's this huge body of work of saying if you do that, it'll be too noisy and you'll suffer from aperture problems. So then we instead resort to sort of sophisticated methods for regularizing the optical flow or the stereo disparity so that nearby pixels have similar flow vectors or similar disparities. And one more thing I want to point out is, even though this is very classic, one really cool thing about this cost volume perspective is that essentially it enumerates possible interpretations of the geometric world. You know, does this correspond? Does this correspond? Does this correspond? And that gives you one kind of estimate of uncertainty, because you can look at the best scoring match and you can look at the score of the next best scoring match. And depending upon what margin you get or how far away those are, you can use that as a way of calibrating. You know, if there's multiple good scoring matches, then maybe you shouldn't be certain about your correspondence. You know, if you have like a featureless wall that you can't match well. So these classic approaches, even though simplistic, actually do something really nice. And a lot of contemporary approaches, including things like FlowNet and FlowNet 2.0, what they do is they'll start with this cost volume. You know, they first extract local features by computing some deep embedding, construct this cost volume. But then importantly, they'll take this cost volume, which sort of naturally is this 4D structure, and they'll collapse it into a 2D multi-channel data structure, a 2D multi-channel image. And so now subsequent processing of this data structure, you can just use 2D filters. And the reason for doing this is that this fits in really nicely into all of our existing, you know, convolutional frameworks. And at least what we found is that instead, if you keep this thing as a truly high dimensional volume, as a 4D tensor, you can get much better accuracy, much more better estimates of uncertainty, and even faster training and better generalization. So we have a paper this past NeurIPS that talks about using these techniques for flow, and then this last CVPR on using it for stereo. So let me just sort of give a little bit of high-level intuition of what are the tricks involved to getting this to work. So one is kind of an obvious one. A lot of these are obvious, and that is all of the standard kind of insights we have for 2D convolution, they apply for 4D convolution. So if we're going to train residual networks, that sort of, you add a delta to the previous estimate. If you're going to train a UNet architecture or spatial pyramid pooling, there's essentially very natural 4D equivalents of all this. That if you do, all of a sudden 4D processing becomes much more efficient. And this was one kind of important trick that it's kind of a cute mathematical observation that was also useful to getting this to actually work in current kind of neural toolboxes. And that is, if you have a 4D data structure and you want to convolve with a 4D filter, because those aren't native, such operations aren't natively supported or aren't that efficient, what you can do is you can take your 4D filter and do a low rank approximation of it as two filters. One that's 2D, let's say in the spatial XY dimension, and the other one that is, I guess, 2D in the UV dimension. It's hard to show that here. And what that means is you can essentially do 4D volumetric processing with a bunch of 2D multi-channel convolutions, but you have to reshape your data structure so that the batch dimension is different every time. So it's a little bit of work involved, but it turns out you can just do this using current routines. And I just wanted to stress that this is a little counterintuitive. This turns out to be much, much more faster and space efficient than actually treating this thing as a raw multi-channel 2D image. Because if you treat this as a raw multi-channel 2D image, you take all your UV dimensions and you flatten them out, and you have to train filters that have a huge number of channels because across every possible UV offset. So if you compare to the sort of FlowNet style architectures, this is 40x fewer flops, and it's almost 3,000 times fewer parameters, because we're essentially, the filters that we're using are really small, like 3x3x3 filters, instead of filters that go, I don't know the exact dimension, 128 or bigger in terms of number of channels. And finally, another sort of final trick that seemed to be quite useful is this notion of multi-channel cost volumes. And so the idea here is also pretty simple. Pretend that at every pixel, instead of extracting one feature or one embedding, you extracted three features, three embeddings, denoted by the colors yellow, red, and blue. And now what I'm going to do is I'm just going to construct three different cost volumes. So red, yellow, red, and blue. But now I'm going to treat these k different features or k different cost volumes. I'm going to treat the k as the channel dimension. So what this will construct is a h by w by u by v by k, a 5-dimensional array. But I'm going to think about that as a 4-dimensional multi-channel array. And the advantage of doing this is the hope is that these different feature embeddings capture some different notions of appearance. So maybe one is like a texture appearance, and the other is a color appearance. So the yellow cost volume tells you how well two things match in terms of texture. The blue cost volume tells you how much they match in terms of color. And now when you do volumetric filtering on top of this, those volumetric filters have access to texture similarity and color similarity. So it's much less of a bottleneck. If you just use a cost volume, you're squeezing everything down to one number that says how well this pixel matches with this pixel. But now we have K numbers that sort of tell us how well this pixel matches with this, and that can give a much richer description of matching. And then finally, because we keep with everything in a cost volume, we can still spit out a result that's a cost volume. That is still H by W by U by V. And then we take a min or a soft min or a soft max around that final UV dimension. And so now we still get uncertainty for free because we can look at the entropy of that soft min, or we can look at the next highest scoring one that's not the actual min to get a notion of how certain we are. Okay, so it turns out you can build methods for doing this. And here's sort of some examples on synthetic data where we have ground truths and tell. Below is some examples on sort of autonomous driving data from driving data from Kitty. And if you actually push through the numbers, this produces state-of-the-art or very close to state-of-the-art in almost all dimensions. And so the top table kind of just shows a bunch of numbers. It turns out in the flow world, there's this distinction of certain flow methods, if you train purely on synthetic, that's one domain of evaluation. And there's another sort of setup where you get to fine tune on real flow data, which is hard to get. And in both those settings, state of the art. When this was published, so I imagine there's new stuff coming up in CVPR as the rapid pace we live in. But I will say that it seems like even newer methods are now also keeping with this true volumetric approach, because it seems like that is useful. And perhaps one thing that really stuck with me is that when you look at this volumetric approach, the training time is dramatically different than when you train normal networks. So I'm showing that in the bottom left table and the bottom right graph. So essentially this thing converges to state-of-the-art accuracy after 80,000 iterations versus other methods that can easily take an order of magnitude more, 20 times longer. So this was something anecdotally that we saw, that it seems like if you architect things correctly, it'll train easier, it'll converge faster, and it'll tend to generalize more. And so what I mean by that is, I'll go to the next slide. One of the cool parts about actually having an explicit UV sort of offset dimension in addition to your spatial dimension is that we can actually train with one UV window and then test on a different size UV window. So in the extreme setting, and this is kind of neat, you can train a stereo network and you can test it on optical flow, because you're essentially just changing the dimensions over which you search over. Or you can train a flow network and test it on stereo. And one of the reasons that's nice is because it's actually hard to get lots of training ground truth for optical flow. And it's much easier to get training ground truth for stereo because you can use a sensor like active illumination, like LiDAR or Kinect. So that means, in fact, we can actually train pretty competitive networks that have never seen any real flow training examples. It's purely synthetic data plus real stereo data. And that sort of shows the ability of this thing to kind of generalize. We've also done cases where you can train it on very small offset windows, but then run it on larger windows for sort of ease of training. So you get to kind of speed up training a little bit, but that it seems like there's an element of generalization you get by using this cost volume structure. Okay, and so one example of this was actually trying to do this for stereo. And so the previous results I was sort of showing for flow. And for stereo, we actually started with a slightly different motivation. Our goal wasn't to explore cost volumes, but it was rather to explore this sort of targeted hypothesis, which is what happens if, is it possible that because geometry is so important for navigation, is it possible to replace active sensors like LiDAR with stereo? And for a long time, I thought that this was not possible because of baselines. Because if you really want to get accurate geometry for something far away, because of the way triangulation works, you need to have very far away baselines between your cameras. The closer the cameras are, the kind of more sensitive it is to the actual far away depths. you can kind of compute this very easily using error analysis. So that the error in the z and the depth that's estimated grows quadratically with the depth, and then also with the baseline and the focal length b and f below. But one thing that I didn't quite realize until someone pointed this out to me is that it's not really the baseline in terms of millimeters between the two cameras. It's really the baseline in terms of pixels between the two cameras. So if you just increase the resolution of the two images, you're effectively increasing the baseline count. Now you can grow to a baseline of 400 pixels from 200 pixels without actually changing the physical geometry, just getting higher resolution cameras. So what's neat about that is we know we're getting higher resolution cameras in our back pocket every year. That's a very scalable sensor. So what we really started to attack this problem with is what happens if we wanted to do very high res stereo to get accurate geometry far off. And the essential thing we ran into was memory constraints. Because if you're trying to build a cost volume, even with a 1D scan line for a huge number of pixels, this thing becomes too big to actually sort of run. So number one, you have memory constraints, and you also have latency constraints. And the other important part about doing this for navigation is that because the world changes fast, you have to estimate what's happening in the world quickly and then move on to the next frame. So you can't afford to spend a lot of time processing a single frame. So roughly speaking, one barometer might be a LiDAR sensor, which processes a sweep every 100 milliseconds. So there you have a snapshot of the world every 100 milliseconds. So if your model takes longer than that, somehow it's, maybe you should just use a LiDAR sensor instead. So the way that the way that we tried to address this computational burden, both in terms of memory and in terms of latency, was essentially also embracing a classic pipeline of course define. And so hopefully we all know of things like optical flow, Lucas Canade, course define is a very classic way of dealing with high resolution correspondence estimation. But one of the classic challenges in course define is that essentially the trick is if you have two high resolution images and you're trying to estimate correspondences, well, the first thing you do is just subsample, make them two low resolution images, and then estimate correspondences, and then use that to kind of initialize correspondences at the finer resolution. But the problem is that it's a well-known limitation is that if you have something small that's moving far between the two images, then when you look at the low resolution image, it becomes blurred out. You don't even see that small thing. And so you don't initialize a good correspondence from which you can then fine tune it at the fine layer. So it's fundamentally hard to find small, skinny things that are moving far. So an example of this in the autonomous setting is that if you have a pole that's actually close to you, that's really skinny, but it actually has a huge disparity between the left and right image. And in the blurred version of the image, you might not even see the pole, so you don't sort of initialize the right correspondence. The one kind of cool trick about one way to sort of set this up is that you can basically separate out the course-defined processing in terms of the feature extraction and the cost volume processing. So the feature extraction, we just do what we normally do. You just run it through a network at the high resolution, image. But importantly, when we construct features from a network, our features are inherently multi-scale. There was this old work from Bharat Harihan of hypercolumns. I can extract the descriptor, which extracts features from multiple levels of a convolutional neural net. What I can do then is I can take those features, which are inherently multi-scale by extracting them from different layers of a network, and I can first construct a coarse cost volume. So that represents the green box in the middle there. And by estimating a coarse cost volume, I can estimate coarse matches between geometry. And I can use those to initialize a finer scale cost volume. So we think this is kind of neat in the sense of you can apply this course-defined processing just at the cost volume at the cost volume stage. And so sometimes this is also known as a multi-grid approach. And it's interesting because the initial processing of the image, I oftentimes think of as fine to coarse. Initial layers of a network first do very local filters, and you get larger and larger, bigger receptive fields. So it's this way of splitting things up that allows you to then manage compute. And then a final kind of, it seems like a very trivial observation, but I haven't quite seen it made, is that if you do course define, another huge benefit is that once you estimate course matches, that actually gives you course disparity. You can just report those, and then while you're computing the fine scale disparity. So this has a very natural anytime component to it. So before you're done processing the network, you can get a rough estimate of geometry at 120 milliseconds. And that can tell you, roughly speaking, if you're a navigating agent, should you slow down, should you pause, because something could be there, even though it'll take you another half a second to precisely figure out the geometry of what's there. And if you wait long enough, you will see that. So that's another added benefit of building in these course-defined structures, which is actually somewhat straightforward in this cost volume perspective. Okay, and so because of that, we have, compared to on the x-axis is time in a logarithmic scale. On the y-axis is error, so you want to be at the bottom and on the left. And so that's that lone blue point. That pentagon is actually us. So the next best method takes quite a bit longer to compute. So if you actually were to draw that dotted line, which kind of represents real-time methods, we're quite a bit more accurate than previous methods on Middlebury. So this is certainly a highly benchmarked stereo data set. And a couple more tricks so we're hoping this notion of like high-res stereo could be sort of a thing that people work on, and we hope people work on, because it seems like it has the potential to rival other much more expensive and sometimes hard to work with sensors. So number one, there's not much high-res benchmark data for stereo available. Middlebury, I think, has 15 high-res images, but that is rapidly changing. And one of the reasons it's changing is because autonomous vehicle companies get high-res data that comes annotated with LiDARs all the time. So this is something that I think is, we're releasing some, but other folks are releasing some as well. So pretty soon we'll have a huge amount of this high-res stereo data. I think is sort of an interesting problem to work on. And one more kind of subtlety that we didn't realize until we worked on it is that one more challenge in the high-res stereo world is because you're working with such high-resolution pixel images, you now have to be very precise in terms of your rectification. Because if you have a slight error, you might actually match to a pixel on a different scan line. Before it didn't matter because we didn't have that many scan lines, but now you have thousands of scan lines because you have a megapixel image. So one of the things that actually helped performance was to add in noisy rectification during training. And we did this actually using synthetic training data. So we grabbed stereo images from renderings from Carla, and we perturbed intentionally. It's almost like data augmentation, but instead of in the image space, it's actually in the camera geometry space. And by training on that, this becomes actually so that the true match is not on the scan line; it actually lies off. Then the final networks actually become much more robust, which I think needs to happen when you're working at this high resolution. Okay, so that was sort of a quick discussion of multi-view sort of geometry approaches. And so now I wanted to sort of dive into actually one of the papers that Gengshen will be presenting in a couple of days in a talk. And so here, this really stemmed from the motion of, it stemmed from the observation that always kind of bugged me, which is, it seems like from a biological perspective, we don't need precise geometry. Clearly, we don't need lasers to shoot off and bounce off objects. But if that's the case, what do we actually use in terms of being able to navigate with the geometric scene around us? And this is no surprise, it's actually well known, or it's very strongly posited that we use cues such as time to contact or looming, where this is a figure from J.J. Gibson's influential early work that pointed out that divergence of flow gives you a clue as if you're approaching something or not. Essentially, things that move closer to you will get bigger, and so that's a very big clue as to a change in depth. So we wanted to see, can we build models and networks that employ that kind of intuition as a way of understanding dynamic scene changes. So the title of this paper is actually, it almost sort of summarizes the whole approach. But essentially, the observation is that, let's say the input is 2D flow, and I just talked about we use our own 2D flow network, but of course you can use anything. And the goal is to actually produce some estimate of what's dynamically changing in the scene. And I'm going to argue that a reasonable output here is 3D scene flow. So there's different ways of encoding this. You can think about this as every pixel, I want to estimate a 3D vector that tells me how it's moving in 3D. Sometimes you're also required to estimate the starting point or the end point of the vector. So that can be the depth of it. But in some sense, that's not going to be the focus of what we're going to estimate, although we'll estimate that as well. And the crucial observation is what we're going to do is we're going to introduce this new quantity, this new representation that we're going to call optical expansion. That at every pixel, we're going to estimate from a pair of frames, is it getting bigger or smaller? And we're going to use that to gauge, is that point moving closer to us or not? And it turns out that if estimating things are getting bigger or smaller, that we can do. We actually have pretty good tools for doing that, but we have to repurpose kind of existing flow networks. Okay, so here's a little bit of sort of theory to whet your appetite. So imagine it's a top-down view of an image plane. The camera center is the gray point. And now we have some flow vector, which we can't see because we're the top-down view of the image plane, but we have the two blue points. And now we can ask ourselves, here's a 2D flow vector. What are the 3D interpretations of the world that could correspond to this 2D flow? And basically for the source point and target point, there's a ray that pops out. And we just don't know where in 3D the source 3D element was on the ray and where in 3D the target 3D element was on the target ray. So there's actually 2 degrees of freedom that that are unknown whenever someone gives us a flow map in terms of understanding what's happening in 3D. And so the simple observation we make is that in addition to the flow map, if we can estimate if the point is getting bigger or smaller, that actually tells us the relative change in depth. And you can look to the paper for precisely what conditions this holds, but it kind of follows your intuition. Essentially, like perspective projection equations will show that if something gets bigger, sort of the ratio by which it gets bigger is equivalent to the ratio of the depth change, assuming that it's not rotating and not deforming. And this again is sort of well known in the psychophysics literature. Okay, and so now what we're going to do is we're going to build a network to estimate the sort of changes in scale. And what that does is that eliminates 1 degree of freedom. So now we actually know, this is kind of neat, we now know the true 3D orientation of that point, how it's moving in 3D. We just don't know if it's really a far away point that's moving far or a close by point that's moving a little bit. And then hopefully this picture shows you that if something else told us either the true depth of the source point or the target point, it would eliminate that last degree of freedom. And this is actually the pipeline that we talk about of sort of upgrading from 2D flow to 3D scene flow. Okay, and there's sort of a network for sort of estimating these things, and you can kind of go to Genshin's talk for more details. But essentially, you start with flow. We first get an analytic we analytically compute the divergence of the flow. So that's a sort of just no learning involved, and that's what we're seeing in the middles in the middle image. What's kind of cool about that middle image is that it looks like it's showing you 3D, but it's not. It's totally 2D estimates. It's just showing you what gets bigger. In fact, you can see, if you were to look at some of the more examples, that sometimes you see the one example where the car is moving toward us. It's not that there's nothing else rigid in the scene. Everything else is rigid in the scene, but everything else is moving away from us. So that's why that looks really dark. So this is actually a visualization of, in some ways, is time to contact. So bright things are things that we're going to hit sooner. So we can compute optical expansion, but we said before that that doesn't exactly correspond to changes in depth because of various assumptions that are made. Things have to be orthographic and non-deforming. So then we train a residual network to actually compute true changes in depth from that. And then finally, we take that, and that gives us the true orientation and direction of 3D movement. And we add to that something else that will tell us either the source or target depth, and that gives us the full 3D flow vector. Right. Oh, and for training, we can train on using normal scene flow data sets, but what's also cool about optical expansion is that there's a bunch of pretty exciting methods for self-supervised learning of optical flow that basically says if you have an image and you predict a flow, and I can push all the pixels forward by the flow, and I can compare it to the measured image frame in the next time instant. I can use the error, the photometric error between that as a signal for learning. You can use the exact same thing for optical expansion. So it turns out we can also train this in a self-supervised fashion on large amounts of data. And so we show various applications of this. So one is monocular scene flow estimation, actually trying to, from just a single image, from just a pair of sequential images, estimating the 3D scene flow. So there we end up using some other off-the-shelf monocular depth estimation network to provide us that 1 degree of freedom that our method can't resolve. We also tried stereo-based scene flow, which is also another benchmark. There, what's nice is we can just use some off-the-shelf stereo network to provide us that initial source 3D point. And in both of these methods, I believe we're now state-of-the-art. And I won't get into the details here. Here I'll show sort of, I think, sort of a really cool application that I didn't quite realize until Gengshen brought it up, which is there's this problem that's been defined called LiDAR scene flow or point scene flow, which is if you're given LiDAR sequences from 2 frames, can you estimate how one set of points, where those points will move to in the next frame? And usually this requires estimating, usually the input is 2 sets of LiDAR frames. What's kind of cool here is you can take one LiDAR frame, and because LiDAR is a continuous, essentially a rolling shutter sensor, it takes 100 milliseconds to revolve around and grab a frame. In order to get 2 sweeps of LiDAR, you actually have to wait for 400 milliseconds. What you can do here is the second you get 1 LiDAR sweep, you can take a camera or a pair of camera images instantly and use that with the techniques we talked about to actually compute a LiDAR scene flow where you expect these points to move before you even get the second LiDAR sweep, because cameras can be triggered much faster than LiDARs can be. So it turns out that these methods are much more accurate than the methods that actually require 2 LiDAR sweeps. So the error is on the last column. There's been other methods that recently use stereo as well, but importantly, what we're talking about just requires not stereo, but a single camera with, but still a pair of images. And we can basically get near the accuracy of stereo and still beating out a whole bunch of stereo baselines as well. So it's a sort of interesting problem of using kind of multimodality where you're getting not just higher accuracy, but also sort of increased temporal resolution. You don't have to wait for these sensors as much using this approach. Oh, and another, sorry here. Oh, another application, I think this is very much synergizes with what Katerina was saying, is that using these methods for finding objects that move, so moving object discovery. So now, instead of just using 2D motion, we can use 3D motion as extracted using this, this upgraded scene flow. And here's an example of someone riding an e-scooter where we don't really have detectors for e-scooters, but if you use motion-based object discovery, you can discover that someone is interacting with this object. And finally, this goes back to just classic structure for motion. It turns out that you can still use these ideas of optical expansion to improve the accuracy of structure for motion, and we specifically look at it in the context of 2-frame structure for motion, which is a pretty difficult setting. But if we go back to this notion, if I want to estimate the geometry of a dynamically evolving world, then you should be able to do it in sort of very quick, hopefully over very quick sort of sensor readings. You can compare it to other methods like CalMap, which is a very tried and trusted method for structure for motion, and then monodepth, which is a single frame depth estimation method. And ours compares quite well across these for, we evaluated on some benchmarks for structure for motion. Okay, so sort of the summary for this part is there seems to be, we can think of expansion, which is this very classic biologically inspired cue, as a tool for upgrading 2D motion estimates to 3D motion estimates. And then because we know that optical flows, it's used in so many kind of pipelines. And if you want to do action and activity recognition, many methods, 2-stream methods use flow. Or hopefully we want to convince folks that maybe instead of just using optical flow, you can just append that with another channel, optical expansion, which is almost as reliable to extract. And now you can get a little bit more sort of 3D estimates of what's happening for your downstream application. And I'll just conclude with like a little taster of an older piece of work, but I think is still interesting. So finally, all of these methods that I talked about were really multi-view methods that either require 2 views or 2 frames at least. And at some level, I do think that it's interesting and worthwhile to explore single frame methods, like purely monocular depth estimation. And I think there's a couple of really exciting papers that are coming out in CVPR that suggest that the accuracy of this is increasing quite a bit. The one thing that I want to stress is that if you look at some of these attempts, there's still some scary things that happen. So here's a method. Here's an example of taking a state-of-the-art monocular depth estimation network. When you look at things that are slightly unusual, like trucks, you'll often see really bad, unreliable depth estimates. And this, of course, is scary if you're going to use this to navigate, because you're misestimating where free space is. So I think what's super important in these settings is to again somehow structure the network in a way where we can understand what it's very sure about and what it's not sure about. This notion of degrading gracefully when there's a mistake.
And so we have this old piece of work that tries to say, okay, how can we use these networks to infer not just fixed depth, but sort of a distribution over depth, so we can tell where is the distribution really confident and where is it really diffuse. And there's various ways of doing this with Bayesian neural networks that sometimes are pretty expensive, and I think might be hard to actually pull off in a real-time navigation setting. But the approach that we take is actually inspired by this cost volume philosophy. What we do is we essentially just discretize possible depths in this log polar fashion. And then we train something that predicts sort of a confidence at each depth. And so what that allows us to do is, even though we can pick the most confident depth, we can see, is there another depth that's equally as confident, to sort of let the network tell us, is there actually multiple outputs that it might have been happy with. And although it's pretty simple, we found this compares quite favorably when you look at evaluations that score the ability not just to produce the best depth, but to make sure that you also are confident in the depth that you're responding with. And I think that those are somewhat less common evaluations, but I think those are super important if we're going to think about using these methods for safety critical things like navigation. And here's sort of a fun example of the top result with estimating depth in the middle, and then below is an estimate of entropy. So sort of looking at how certain is it about all the possible depths it could be. And here's one application that's sort of tied to the workshop theme of kind of map building, which is we take all these estimated depths and we stitch them together. But importantly, we only stitch them together and align them using confidence depth estimates. So we just threshold depth estimates that have low entropy and ignore them. In the subset of confident things, then we align. We can actually build geometric maps just from molecular depth estimation methods that are kind of close to the ones you can get from a LiDAR sensor. Maybe we'll sort of show this in just a second. So I think this is an example of where things have been thresholded to not take advantage of depth estimates that we're uncertain about. And the very end will sort of show 3 different examples here. Yeah. So LiDAR is the top one, and then we have like a version of ours that uses this uncertainty reasoning. Okay, so that was, I'll sort of conclude here. So what are the morals that I hope you can kind of walk away with? So one is this notion of discretizing possible geometric interpretations of the world, either through a cost volume or the simple sort of log polar discretization I quickly went over at the very end. That seems to be a very useful way to implicitly encode uncertainty and reliability. The other sort of take-home message is that a lot of classic tools for geometric processing really make use of spatial data structures like volumes and cost volumes. And even though it seems like we're using them in a lot of our network architectures, I argue that we're not, that oftentimes we take cost volumes and we smush them into 2D multi-channel things just so we can use our normal tools on them. But if we embrace the fact that they're actually volumetric, a lot of things end up being easier and more robust and generalizable. And finally, if we think about, the final goal is to, in some sense, not just estimate the geometry of the rigid world, but to really estimate the geometry of a dynamic world and estimate correspondences. So that ultimately seems like a 3D scene flow problem. And we can use sort of 2D flow estimates combined with expansion to hopefully get us there. Okay, I'll conclude there. Thanks.
Okay, thank you so much. Thank you for the interesting talk. I think next I'll ask a few questions for our audience. So here's a question in terms of deal with the memory constraints. So are there other possible ways other than multi-scale feature methods?
Yeah, I see. Okay, so what are so what are ways to deal with memory constraints? I guess my initial thought would be multi-scale or coarse defined. So I guess the memory constraint we run at against is we're enumerating possible matches. So if we have really high resolution data, there's a bunch of possible pixels that can match. But we know that the simplest way of fixing that is don't do high resolution data. And then you just kind of intuitively, I always end up back at these kind of coarse defined multi-scale methods. Historically, it feels like that has helped for vision quite a bit. But what I find intriguing is that we know that in the past they have certain problems like this example of something small that moves far. But maybe we can architect our neural solutions to compensate for those problems.
Okay. Maybe another question is related to this. So you mentioned the cost to find methods. So on smaller or coarse scale, so we may have some errors for the optical flow disparity. Do you have good ways to correct those errors along the way of upscaling the features?
Yeah, that's a great question. We've actually thought a little bit about that. So, I mean, another problem, of course, to find is that once you make a mistake, then you're kind of stuck as you go down to the fine level. And another version of what you could be saying is that at the fine level, maybe you can realize you made a mistake earlier and you want to correct it. So that suggests to me almost something else, something that's a bit more bottom up and top down, where you can use some fine scale estimates to help refine what you think the course estimate should be. One thing that that I hinted at that you could do is this notion of like on-demand searching. So you can choose what are the pixels you want to try to evaluate. And you can do that based upon initial things that you've looked at. So in theory, if by searching over some pixels at the fine resolution, you realize I actually want to search more around this region that I didn't get a chance to search through at my current sort of course boundary, then you can dynamically change. So that's something that I feel like by having a method that somehow factorizes the search space of which you're searching over correspondence, and then the other stuff, the feature extraction plus the convolutional processing, then the ability to sort of dynamically change where you're going to searching, that could be one way of getting sort of fine scale information to help sort of give feedback for the coarse scale cues.
Okay, yeah, we have another question from our organizer.
Thank you very much for the great talk. Very much enjoyed it. It's going in the direction of course to fine and the memory problems. I'm wondering whether part of the problems that we're seeing comes from trying to shoehorn everything into a dense data structure, where the sum of those signals might actually be sparse.
Yeah, that's a great question. So I guess, we're sort of somehow handcuffed by GPU land, where we know that sort of things, we can do stuff sort of naturally in parallel kind of easily. And they're oftentimes are not nicely suited for sparse. Like in many ways, I guess, like the other view, like a lot of the classic pipelines do operate in a much more sparse way. Start with interest points and then try to match those. It's a great question to think about how better to kind of do this. I will say that one of the ways in which we end up using this output is like we're essentially computing dense correspondences, but then we threshold based on uncertainty, and then we actually kind of pass that information for downstream applications. So that thresholded output I think of as somehow like quasi-sparse. So what we actually find is that, so like traditionally interest points, the sparseness, some of it comes from the fact of, okay, because if there's a flat region, don't try to estimate correspondences there. Here, I think a lot of times we actually are able to reliably estimate correspondences on flat regions, but instead the places where we're not certain is when there's occlusions or boundaries. So we end up kind of getting more coverage than the traditional sparse method. But yeah, sometimes I was wondering, maybe there's this notion of, maybe there's an intermediate regime, this kind of like quasi-sparse or quasi-dense, where most of the things you can get, but there's some things you definitely say, I don't want to hallucinate that. I want to get other information to fill that in.
Thank you very much.
Okay, the next question, I think you have already touched a little bit about this for self-supervised learning. So can you maybe elaborate a little bit, like how do you extend the volumetric processing method to a self-supervised approach?
Yeah, so essentially you could think of the self-supervised observation is really more about the loss function rather than the actual architecture. So I didn't really talk in detail about the loss functions, but there's almost two components of the loss functions we use. So one is, if you have training data where you have ground truth optical flow or ground truth disparity, you can just add that as a loss. You want the predicted disparity or the predicted optical flow, the argmin or the softmin. You want that to have low distance, L1 distance from the true one. There's another loss function that's natural to build, which we'll call photometric loss, which is in any of these correspondence tasks, you're always given two things, and you're trying to estimate. If you estimate the correspondences correctly, then I should be able to take one image and vect it forward by the predicted correspondence maps, the flow. That produces a predicted image, and I can compare that with the measured image, either in the other stereo pair or in the next frame if it's optical flow. And that gives me an error that I can backprop on. So essentially, it's the cost volume processing is a pretty natural thing that can still be used for self-supervised learning. Perhaps the more sort of subtle thing was that this notion of expansion can still be used for self-supervised learning, because one of the weird things is that like we don't have any 3D annotations in the normal sort of image sequence data that we have. So it's a little bit surprising that we can do somehow 3D-ish self-supervised learning. But it kind of is maybe a bit more straightforward to see. If all you're doing is really estimating 2D expansions of things getting bigger and smaller, that we believe we can kind of do with our kind of like 2D sort of like our 2D flow networks. Hopefully that answers that question.
Okay, right. Patrick, yeah, I think this is due to the time constraint. Yeah, this is end of the talk. Thank you so much.
Okay, thank you.
Bye.
Bye.
So maybe Go, you can take over and
Sure.
we can move on to the
Dr. Haibin, I saw he's here already. So let me introduce Professor Haibin Ling. And Dr. Haibin Ling is a SUNY Ampere Innovation Professor in SUNY Stony Brook. He received his BS, MS from Peking University and PhD from University of Maryland. Before SUNY Stony Brook, and he has been a professor in Temple University, researcher in Microsoft Research Asia, UCLA, Siemens Corporate Research. He has done extensive research in computer vision, medical imaging, and HCI. Especially, he is well known for his work in visual tracking. And recently, much of his research has been applied to augmented reality. Due to his excellent work, he has received Best Student Paper Award of ASM Symposium of User Interface Software and Technology, and NSF Career Award. I'm already looking forward to Professor Ling's talk. Let's welcome.
Thank you. Sure. Can I share a screen now?
Yes.
Can you see it now?
Yes.
Okay. Hello, everyone. Thanks for, first let me thank Guoyu and the organizers for the invitation. Yeah, it's really my pleasure to share with you guys our recent work on multiple orbit tracking. In fact, I noticed that the workshop is more on SLAM, and I have been hesitating a little bit because we do have some recent work on SLAM, but compared to multiple orbit tracking, so we decided to choose multiple orbit tracking because it's more comprehensive at this moment in our group. Okay, so the title of the topic is rank 1 tensor approximation for MOT. So this is a kind of a new tracking framework we have developed about several years ago, and we continue to improve that and extend that for different cases. So roughly speaking, I will first formulate the MOT problem as a multi-dimensional assignment problem, and then we will introduce our discovery of the equivalence between MDA and the rank 1 tensor approximation, and then we will talk about how to use rank 1 tensor approximation for MOT, and also model the structure and the context information. So after that, we will extend the framework to differentiable, and such that it can be embedded into an end-to-end MOT system. So, and after that, I will draw the conclusion. So due to the time limit, I will not get into details of techniques. So, but you are welcome to read our paper, so send an email to me and for discussion. So multiple orbit tracking is a kind of a very popular problem in computer vision. So roughly speaking, its goal is to locating targets and maintaining the target identities across the time. So just like many other vision problems, it has many challenges like occlusion, appearance ambiguity, illumination change, and so on. Okay. So to solve to achieve better robustness, our intuition and motivation is to use higher order temporal motion and local context, spatial context information for this purpose. Okay. So. In this series work, we focus more on the association problem in MOT. In fact, MOT, recently there's also other directions for improvement. But in this talk, we focus on the association part. Okay, so here we illustrate the basic setup like this. Okay, so roughly speaking, given three consecutive frames like t minus 1, t minus 2, we first detect some moving object, not necessarily moving, but detect some object, say. And then we find association across time, such that we can recover the trajectories of the objects. Okay. So we can also extend this formulation to tracking deformable structures. If we treat the deformable structure as a set of related objects, and then we can extend this framework to that one, as we will show later. So a natural solution to solve this kind of multiple frame association problem is through pairwise association between neighbor frames. We have two frames, and another two, we can just combine it together. Okay. So it boils down to finding the correspondence between two sets of points. So here, suppose we have two sets, and you can view these 2 points as detected objects. Okay, and then between each pair of objects cross frames, we can define or we can calculate its cost function. We call it CIO-I1, and then we can model this problem as a very linear assignment problem. It's a very simple simple optimization problem with certain binary constraint. And the good thing of this kind of solution is there are no efficient solutions such as the Hungarian algorithm. Okay. So, but what we're interested in is usually more than 2 frames. Okay. So here we show a toy example for the formulation. Assume that we have k+1 frames, and each frame has n detections. Okay, so here we use +1 just for notation convenience, and also we use n detections. I mean, we just fix the n, but in practice we can handle different different n by like, for example, using dummy points, something like that. Okay. So once we have this set up, I mean, the output, the expected output is trajectories over time, so which can be shown like here. So we want the trajectory to connect the object across different times, saying that, okay, these objects are from the same one. And this can be naturally formulated as the extension of this linear assignment problem. So this is so-called multi-dimensional assignment problem. Sometimes people also call it k+1 partite problem. I mean k+1 because we have k+1 sets. Okay, so here's the objective function. So it's more like we want to minimize the total trajectory cost. And here CI0, I1 to IK is a k+1 order. So each element here shows the cost of our trajectory from I0, I1 all the way to IK. So as illustrated here, we see C2, 3, 2, 3. Okay, and similarly we have this trajectory indicator tensor. So it's more like the assignment variable. Okay, and we also have this assignment constraint, which is essentially saying that okay, the assignment should be binary, either 0 or 1, and each object should lie on at most one trajectory. Okay, so those are very standard thing. So the benefit of this MDA solution compared to a sequence of bipartite matching, the benefit is it is naturally address the original problem, because the original problem by definition has more than 2 frames, and it can also have captured high order information. This is very important, especially especially when we are dealing with these objects that has little appearance changes. Actually, this is our original motivation, as we show in the first frame. At that time, our problem is to track multiple vehicles from the airborne videos. So in that video, all the vehicles, they look very similar to each other. It's really hard to distinguish them just by appearance. So we have to use high order information. But apparently this problem is challenging, and because the computational expensive. In fact, in general case, for more than 3 sets, so this problem is known as to be MD-hard problem. Okay. So in this frame, in this work, our ideas like we found that the MDA problem has very, very close relation to the rank 1 tensor approximation problem. And the rank 1 tensor approximation problem is kind of a well-studied problem in tensor analysis. And we know that there are some very nice solutions already. Not global optimal solution, but they are kind of known good solutions. So therefore, once we build the connection between MDA and the rank 1 tensor approximation, we can just borrow the algorithms from rank 1 tensor approximation to solve MDA problem, and then to solve the multiple orbit tracking problem. So that's the idea. Okay. So to find the relation, we first need to reformulate the original MDA cost function. Okay, so the first step is to the original MDA cost is like we want to minimize the total cost. So now we convert that to maximize the total, let's say, total affinity. So this one is actually very straightforward. You can either reverse the cost or add some number or something like that. Okay. So this is just for convenience for the rest of the derivation. Okay. So our intuition is like this. Okay. So in our definition, currently the affinity and also the assignment tensor, they are all of them are k+1's order, right? So they are indexed by each object. So therefore we have k+1's order because we have k+1 frames. Okay, but we are interested to see how to decompose this problem into local assignment problem. By local assignment, we mean the assignment between the first and the second frame, and between the second and third frame, and so on. We call such thing as local assignment problem. We know that the local assignment can be modeled just by a matrix, right? And we also know that for just the binary assignment problem, and we have a very nice solution like Hungarian algorithm. Okay, so that's what we are going to do for the reformulation. Okay, first for the assignment tensor X, it is very easy to do this reshaping because X, let's say Xi0 I1 to Ik can be easily decomposed as a product of E I0 I1 and E I1 I2 for the second local assignment. So here, this E indicating the local assignment between 2 neighborhood frames. Okay, so E was originally a matrix. Okay, so this is very straightforward. However, for the decomposition purpose, it's a little bit hard to decompose a tensor, a k+1 tensor X into K, into kind of a product of K matrices. That is very inconvenient. So instead, we actually stretch each local assignment matrix E into a local assignment vector V. Okay, so specifically here for a 3x3 local assignment matrix, we just stretch it as a 9x1 vector. Okay, so specifically here x2323 equals to E231, which indicating the assignment between the second object in the first frame, in the zeroth frame, to the third object in the first frame, and so on. Okay, and we reshape those E into V, which is a vector. So after this decomposition, then the second after this reduction of the order, the second one we need to deal with is about the affinity, because now we know that we have the K product, the K product of affinity, the assignment vector, tensor. Okay, so we also need the K's order affinity tensor. Okay, but the original one is K plus 1's order. Okay, so this one is actually also kind of straightforward, and the notation wise is a little bit complicated, but the idea is actually straightforward. So the idea is, instead of using each object as the index for this affinity K, we use a local assignment as the index for a new affinity tensor that's indicated as A. So therefore, for this new affinity tensor, it will index by K instead of K plus 1 local assignment matrices. Let's say this is between 0 to 1, between 1 to 2, and between 2 to 3. Okay, so then for those valid index, we just copy the affinity from the original K plus 1 order affinity tensor. For those invalid index, we just assign it to 0. Okay, I know I will give you a very simple example. To have understanding this process. Okay, so for this extremely simple example, we are dealing with 3 frames. It's essentially 0, 1, 2. We have 3 frames, and each frame contains only 2 objects. So therefore, the original tensor is a third order affinity tensor, that's S. So it contains 2 by 2 by 2. And for example, here, say 1 to 1 is the cost from if we treat the first black object and the second blue object and the first red object as a trajectory. So this is the cost for this one. Okay. I think I should use affinity here, but that's the same. Okay. So, and then what we do now is instead of using 3 by 3 by 3, the 2 by 2 by 2 and third order tensor, we kind of reduce the order to 2 and using the local index as the local matching as index. So then we have a second order tensor. And in this case, it's just a matrix. And then for example, this one indicating, this local match and this local match. So they form together a valid trajectory. So this trajectory should have cost C111. So then we just copy C111 to this new tensor. Okay. For some invalid cases, for example, if we want to join this blue one and this red one, they are not connected. They don't form a valid trajectory. In this case, we just assign 0 here. Okay. So by this kind of reformulation, we can easily convert the original problem to a new formulation. Let's say we have instead of K plus 1's product, we have actually summation. We have actually K summation here. So inside each summation, we have the new formulation here, and the inside here is a K product of V. V means the local assignment, and correspondingly, we also reformulate and rewrite the original constraint here. So it's just a kind of tedious but straightforward reformulation. Okay. So we go one step further to use some very nice and kind of looks more fashionable notation. Okay, this kind of notation is a K mode tensor product of tensor A with a vector. Okay, so roughly speaking, this is just the extension of matrix vector product to a tensor. Right? So with this notation, we find out that okay, the original object function here can be rewritten as the tensor A first mode product with V1. V1 is the vector of the local assignment between the first pairs of frames, okay, and the second mode product, okay, with V2, and so on till the case mode product with VK, okay. So this is a new formulation. It looks nice, but why do we do that? Okay, so we do that because the equivalence between the problem named rank 1 tensor approximation. Okay, so the rank 1 tensor approximation is defined like this. Okay, given a case order tensor A, we want to find the k unit norm vector V1 to Vk. Okay, and a scalar lambda to minimize the reconstruction error. Okay, this error is measured by the Frobenius norm. Okay, so the formulation is like this one. We want the tensor product among V1, V2 to Vk to be as similar to A as possible up to a scalar lambda. Okay, that's the idea. Okay, so basically after some not that difficult derivation, so we find out, okay, let's forget about lambda. We find out that this problem is equivalent to find out the set of vectors to maximize an objective function named g of v, which is defined like this one. So which is defined essentially by the square of the original tensor, mode 1 product with V1, mode 2 product with V2, and all the way to mode k product with Vk. Okay, so by comparing this one with our new MDA formulation here, you can see they are very, very similar to each other. It seems the only difference is about the absolute value and the square thing, right? But remember that now we are dealing with association problem. So everything and every element in V and in A, none of them are negative. So therefore, we can actually safely just kick out this absolute value, these things, okay? So therefore, we find out that the MDA problem and the rank 1 tensor approximation problem, they have exactly the same objective function, okay? So this is the discovery we found, and apparently that inspires us to do something and borrow some ideas from rank 1 tensor approximation for our solution. So that's our next step. Okay. So then the frame based on this discovery, we come up with a new frame for this multidimensional assignment. So roughly speaking, it looks like this. Okay, given the original input problem, we treated this problem as a sequence of a local assignment vector, and we want to infer this local assignment vector. But on the other hand, we construct this we construct this case order affinity tensor as what we described before, okay? And then we bridge this two parts with the rank 1 tensor approximation. So that's the basic framework here, okay? So then, as we mentioned already, the good thing of this discovery is there is already a classical solution for rank 1 tensor approximation. This is a famous tensor power iteration algorithm. And this algorithm not only has kind of very nice mathematical proof and to back up it, it also is very convenient for us to extend to handle all different cases. So we will show that very soon, okay? But here we want to mention something here, okay? So actually the original rank 1 tensor approximation problem, they request the solutions, each vector to be unit norm, okay? This may not be identical to the constraint for the MDA problem, because typically in MDA problem, we need an integer constraint. And we also need the L1 norm or row column and L1 constraint. So these are a little bit different than the original rank 1 tensor approximation. But the good thing is that the tensor power iteration is very flexible. So in our practice, we found out that we can just work on just revise the tensor power iteration algorithm directly. In practice, we didn't find the convergence to be something bother us. In fact, for the L1 norm constraint, we actually proved the convergence, but for the row column constraint, we didn't find out how to prove that. Okay, but it doesn't actually affect the practical performance. Yeah. So this is kind of an example. And this is a definition of this row column L1 normalization. Okay, so this is essentially what we defined before. Okay, so the next thing that as we mentioned, we can further extend this to model context. Okay, so this formula gets a little bit more complicated than before, but we can still recognize the first component here is A L1 to LK and so on. This is something we already know, right? This is our original formulation. And the second part, we say, okay, there's a new CLKJK. So this is apparently some kind of a cost, okay? And then the VLK, VJK. V is some local matching, right? So this part is essentially measures somehow the similarity between local matching. So as illustrated here, suppose between the second and third frame, so we have one matching from the first to second object, and another matching from second to third object across these two frames. Okay, so because this object, they are kind of neighbor to each other and spatially, so we hope that their kind of interaction should be similar, right? So therefore, we can somehow calculate some C to measure the consistency of interaction between these two local matchings. So this is the context information. Okay, so therefore this is modeling, and the rest here is still just the same as before. It's just assignment constraint. Okay, so now the problem is we did prove that without this interaction part, the original part here, they are equivalent to the rank one tensor approximation, but we didn't prove anything on this part, right? So actually we don't know how to prove that. But the good thing that with the tensor power iteration, all we need to do is actually just not here, okay, just inside each power iteration, inside each iteration, because inside each iteration is more like we fix the K. Intuition is more like, okay, now let's don't worry about the other frames. Let's just study the matching between the K frame and the K plus one frame. Okay, so by doing that, for each iteration for the block VK, in this case we can actually merge these two types of affinity. Essentially, we can merge this AK and the CK into a new, we call it augmented tensor affinity. We can merge them together, and then inside this iteration, we can work just as if we are just dealing with some global power iteration. So therefore, we can easily revise the algorithm. So that's what we did then. Okay. So this is the algorithm we used for modeling and for tensor power iteration with modeling of the pairwise interaction. Okay, so you don't need to get into the details here, but I just want to say, okay, this is just the iteration, and for each K means between the K minus 1 to K's frame, and we do tensor power iteration, and then we do normalization here. This is inside each iteration. That's roughly speaking, that's the algorithm. So one thing I want to point out this is, okay, this repeat, I mean, if we fix the amount of fix the number of repetition, then every step here, they are essentially some linear operation. So therefore, this can be done, and this can be made differentiable if we fix the number of iterations. This is something we are going to do very soon. So this is just some results we applied at that time. Okay, so next let me speed up a little bit. Okay, so as we said, we also extended the framework to handle structure tracking. Okay, so in this case, we want to track the deformable structure. These are apparently in medical imaging, And the idea is, okay, we actually add an actual kind of mapping between each object to a kind of prior model of this object. Okay, and this matching we find out that can also be propagated nicely across this cross frames. I'm just using this tensor iteration framework. Okay, so I won't get into details, and later we also kind of integrated the learning part here to further improvement the algorithm. So this is the result for this part. Okay, and finally, as I mentioned before, okay, if we fix the number of iterations, we can easily actually make the association step end to end. We can make that step differentiable, and therefore, once this is differentiable, we can make the we can actually end to end learn the affinity between all kind of objects in a potential trajectory, right? And we can also, before affinity, we can also learn the feature extraction from that. Okay, so therefore we kind of concatenate all these components together. We form an end-to-end MOT system. And here's some detailed component for each part that a little bit tricky, but it's end-to-end. Okay, and also just to mention some recent trend in MOT. It's not only from our group. Recently there are several other groups. So people start to integrating SOT and single orbit tracking inside here one, and people also now pay more attention to the target management to handle kind of occlusion and re-entering, all kind of things there. Okay, so this is our latest work. Okay, and these are the quantitative results on 4 public benchmarks. Okay, we got promising results on all of them. Okay, so this is a video here. Oh. Sorry, I don't know why it's not working. Okay, yeah. So yeah, you can just imagine very nice results here. Okay. Okay. So now conclusion. Okay. So roughly speaking, we for the first time we discovered the equivalence between the objective functions of multidimensional assignment and the rank-rank tensor approximation. Okay, and this discovery enables us to use rank-rank tensor approximation for solving association problems in multiple orbit tracking. In fact, we also applied that to graph matching, but that's a different paper. Okay, and the frame can be further extended to handling context and structural information. And finally, we make this framework differentiable and integrate it into an end-to-end MOT system. Okay. So I want to thank my students. They did basically all the codings. I didn't write any code here. Okay. So and also my collaborators here. And this work is supported partially by National Science Foundation. All right, I think that's all here. So thank you for listening. So I think I can take questions now.
Okay, fantastic, and thank you very much, Professor Ling, for your great talk. We have some questions. So for here, and when you do the optimization, when you optimize the tensor, you are taking offline optimization or online optimization here for your tensor.
So by online, offline, you mean I assume that you are talking about it in the context of tracking, right?
Right. Yeah.
So, yeah. The version we use is offline. So basically, we kind of using a fixed length window. Let's say the size of the window depends on the kind of scale of the problem. Let's say suppose the window size is 5, and then for every window we have 1 frame for overlapping, so that we can connect them together. But the algorithm, current algorithm is offline. Okay.
So in offline and online tracking, I think and when you have new frames coming in, so if we are doing that for online, new frames coming in, and if we, for example, we already have a very big tensor. In this case, optimization for the entire big tensor of tracking would be very time consuming. In this case, do you think there is some drop off strategy to be used here to increase the speed of tracking?
Yeah, we actually, I mean, not in these papers, we actually have another paper we did use this one for online tracking. So in fact, I mean, the speed is not a big issue as one may sort of, because I mean, the tensor here, the tensors are highly sparse here actually. So we apparently we don't use the original, I mean, the tensor multiplication. We use the sparse version. Yeah, that's a reason. Yeah.
Okay. Actually, this question is asked because I saw you have done quite a lot of object tracking. And in structure from motion and SLAM visual odometry, and there are also quite a lot of tracking involved. And but actually, tracking is somehow determines the entire pipeline's performance. And in this case, it's point-to-point tracking. And I can imagine for factorization-based structure from motion or other tracking algorithm, point-to-point tracking would be very time-consuming and compared with the object tracking here. So that that is the part of the reason we ask for the optimization, and because I can imagine this could be used for structure for motion for this kind of the tensor based. And have you ever tried any kind of this application to SLAM algorithm in point tracking?
We tried a little bit, okay, but not online version. Yeah. I think several years ago, I have a student, she's working with me for motion segmentation. In that case, because it's still offline, we have the video already. So we have, I mean, we first extract a lot of, I mean, feature points, and then we use this tensor power iteration thing to do the association. Yeah, it may not be tracking, but anyway, that's it. When we now we are also working on SLAM systems, but it's too expensive and so far to apply this framework for SLAM system. Right? So SLAM system, this key point based SLAM system. I mean, the number of targets is much more than the tracking system I'm currently using.
Yeah, it's something like easily goes to several hundred to a couple of thousand points.
Yeah,
and in this case, that is very, very expensive.
Yeah, exactly.
Yeah, and one more question is, could you introduce a little bit about the end-to-end tracking frameworks, the loss function for those frameworks?
Okay. So this one, right? Okay.
Right.
I think the loss function is I think loss function here is not something special. It's just a standard one. Okay. So here I would say, I mean, at least when we design the system, the first challenging part and kind of complicated part is to make this power iteration differentiable. I mean, mathematically, we know straightforward it is differentiable, right? Because I mean, it's just linear operation. But you know, for the derivation, especially for the implementation, you need to be very careful because everything including tensor. And this is one part. And another part actually, we think it's more plays a more complicated role is actually the affinity subnetwork. So which is shown actually in the bottom of this slide. So basically, I mean, we want to explicitly to capture this motion information, right? So for implicitly, it's like we have one object, it's some coordinate, the second object with another coordinate. We can calculate their motion directly, right? But however, I mean, this kind of calculation is hard to be treated as to model in the end-to-end system. So what we did here is essentially, okay, for one object, we draw a bound kind of rectangle square region, centered by this object. Let's say the object at time t, okay. And then for object at time t minus 1 and t plus 1, we use the same box. So therefore, when we put the three boxes together, okay, so their misalign, their location will be implicitly encoded into this feature, this affinity calculation. So that part is very tricky, I would say.
Okay, I got you.
Okay. I think we here we are about at the time right now. I would like to thank you again. There are more than 100 people watching your talk, and I would like to represent all of those more than 100 people to thank you for your great talk.
Yeah, thank you very much.
Thank you. So let's see the next speaker. The next speaker should be Dr. Xiaoming Liu. He's not here, seems like. I need to. I will need to. Okay, the next speaker will be here just in 1 minute. Yeah, address the message here. Okay, now we have Dr. Liu is here. Okay, great.
Sorry, I was in a meeting, so.
No problem. Yeah, it's about the right time. Yeah. I would like to introduce Dr. Xiaoming Liu, and he's an associate professor in Michigan State University. He received his PhD from Carnegie Mellon University. Before joining MSU, he was a research scientist in GE Global Research for almost 8 years. I think that should be the correct number. Sorry. Yeah, and he has been program chair for WACV 2018, BETAS 2018, an area chair for many top conferences, NeurIPS, CVPR, ECCV, ICCV, and associate editor for neurocomputing, pattern recognition letters, and pattern recognition, journal pattern recognition. He has been known for prior-based 3D reconstruction, and recently, from what I know, he has been working with Ford Motor Company for 3D object detection and depth estimation for those research work used for autonomous driving. And he has been granted for many awards, like best industry-related paper, run-up in ICPR, twice best student paper at WCV, best post award for at BMVC. We are looking forward to Dr. Liu's talk, and let's welcome.
Okay, thank you very much for the introduction. Sorry, I was late a few minutes. So let me share some of our work in terms of monocular vision-based 3D perception. Can you see my slides?
We can see, but it seems like we are in another mode. Is in another? Yeah, right now is correct. Yes.
Okay, very good. So yeah, so I think for people working on autonomous driving, we understand the importance of 3D perception, right? So conventional vision problem typically giving image sequences you like to understand seeing in the 2D sense. But for autonomous driving, 3D perception is very important. You wish to understand, detect object, tracking as well as forecasting, do everything in the 3-dimensional space. So for this kind of problem, typically we like to use multiple sensors such as LiDAR, radar, and RGB cameras. And sometimes not just one sensor, we like to use multiple sensors for the robustness. But from research perspective, oftentimes people in vision like to see that how much we can do with a single camera. Can I still do single camera-based 3-dimensional perception? So this is a question kind of interests us as well. So we have been working on this problem in the past 2-3 years. So we had a number of work in this topic. So today, I'd like to focus on 2 different topics. One is 3-dimensional detection from monocular image and videos, as well as 3-dimensional reconstruction. So in particular, giving an image in autonomous driving, we like to detect the object in the 3D scene, which means that you have a box around every single object, especially for cars, pedestrian, as well as bicycle, as well as cyclist. In addition, we also like to do 3D surface reconstruction for every vehicles, as well as potential other objects. So with this capability, eventually you can render or look at the the object from different view angles in this case. So let's start with the first topic of 3-dimensional detection. So this work was initially published in ICCV last year with my student Garrick. And later on, we had more collaboration with Gerard and Burnett. And this work right now is under review. That will be the second part for video-based 3-dimensional object detection. So I'll start with the first part. The goal of monocular 3D detection is that giving image or video sequences, we like to be able to detect all the objects here. In this case, would be the cars, pedestrian, as well as cyclist. So we want to have a single model can detect all 3 different object types. So we are certainly not the first group working on this. There has been previous work on this topic. In summary, previous work typically using external networks, and they also require multi-stage training as well as testing. For example, in this deep 3D box, which was in CVPL 17, there's a 2D RPN module trying to generate the boxes from 2D perspective, and then try to fit the 3D into the 2D detection results. And later on in the multi-fusion approach in CVPL 18, there's also a separate module to do the depth estimation. So this kind of module is fixed as well as it's an external network. In comparison, what we're trying to do is that we like to have a single network, have a single stage, do this kind of 3D detection work. Okay. So because we don't want to necessarily rely on the 2D information, we have to redefine the anchors. So in this case, when we define anchor, we have information indicate the 2D height and the width. We also information indicate the 3-dimensional H, L, and W, as well as the theta angles. And we also have the projected center in terms of XYZ P, right? So this equation describes how the XYZ 3D, which is where the labeled ground truth box information of Kitty database is, how they projected into a 2D projection through a projection matrix P, which is also given in the Kitty database. And the definition of the theta 3D is defined according to the Kitty definition, where you link the centers and then you define the relative angle compared to the axis. So with this kind of anchor definition, now we can take ground truth labeled 2D boxes trying to do a clustering, and will give me a set of essentially clusters of boxes, and we treat each one of them as one anchor. So in total, we will generate 12 different types of anchors. And for each one of them, we can compute what are the a priori distribution for ZP, WH, L, and theta. These are the kind of a priori distribution for different types of anchors. You can see that big car in 2D typically correspond to close-up distance in the ZP space, while smaller car typically corresponding to further away distance, right? So with this anchor definition, now we can try to visualize them in the 3D space. For example, this is a kind of default 3D anchor we have learned, and then we kind of visualize them in the 3D space. We have 12 different anchors in total, and this will be corresponding 3-dimensional view angle. This will be the bird's eye view of the same anchors. Yeah. So with these anchors, now the detection job is trying to place those anchors in the space, right, with different distance to the cameras, and we'll see that which of those anchors will be closer to the ground truth. If they are, then the network will try to learn what are the deviation. I can move around the anchor so that it will eventually overlap with the ground truths in the kitty. So this will be essentially the 3D detection problem. Yeah. So specifically, the supervision is like if every anchor box has a larger than 0.5 IOU with the ground truth box, we consider this will be the candidate. Now, for every candidate, the network trying to learn a set of transformation parameter, including C, that's classification, and X, T, Y, T, Z, T, P. This is essentially would be the center, deviation of the center, and next will be the deviation of the 3D boxes, and finally would be the deviation or transformation of the 2D boxes, right? By learning these deviation parameters, now you can move the initial, yellow anchor box into the final target box, which will be the ground truth is. So whenever this is happening, then the learning of the transformation parameter is successful, right? So once we learn this transformation parameter, now we can take the transformation parameter, which is the color variable, together with the anchor parameter, which is the black color variables, and go through this equation. We can generate the updated 3D boxes, and this will be corresponding updated 2D boxes, right? So because we need to know that how to use the transformation parameter, and those equations tell me how to apply it. So knowing this transformation parameter, now I can define loss functions. So we will have 3 loss. So one is classification, typical softmax. Secondly is trying to make sure that the estimated box is the same as the ground truth box. And finally, will be the 2D box will also be similar. So we will have 3 levels of the loss. So in terms of network architecture, we start with DenseNet. The network have 2 different branches. One is called global branch, which is similar to a typical detection network. A novel part will be the second branch. We call it the local depth aware convolution. So the idea is quite simple. That is, we think when the car object at a different distance, the optimal filter, convolution filter that can detect the key features might be different. For example, when the car is close by, maybe I should have a filter for detecting its tiles, right? But when the car is further away, maybe I should, use detect its generic shapes. So by doing this idea, we can actually have different filter for object at different distance. Yeah. And eventually, these 2 branches will be combined together using an estimated weights alpha, and finally, we'll have the joint deformation parameter in the end. So this idea of the depth-aware convolution actually being extended in the latest work. This is one of the CVPR work, at least in the bottom, called learning depth-guided convolution. So this essentially take one step further. Actually, they did quite some interesting things based on the general idea of depth-aware convolution. So you can check this out in this year's CVPR. So look at some experiments. So typical evaluation is done on kitty. So we have 3 different sets, validation 1, 2, as well as test set. Okay. So normally for each one of them, there are 3 different types of data, which is easy and moderate and harder data. So we test on all 3 cases. And this table is for the bird eye view evaluation. And you can see that in this evaluation, you don't care about the height of the box, right? But the other dimension will still matter. So you can see that compared to the previous best work, the improvement is actually quite large. And similarly, for the 3D detection, this is a harder problem. You can see that overall the number will be lower because even the height of the box will matter here. But nevertheless, we still have quite some improvement compared to the previous best work. Okay, so look at some quality results. So this is the detection for cars and pedestrians, and these are the cyclists, and this also pedestrians. You can clearly see that the cyclist is much challenging problem because the box tend to be larger and the orientation estimation will be hard as well. So this shows you some qualitative results in a video format. So the top is the input video together with detection results. In the bottom, we have the bird's eye view, where every cell is essentially 1 meter by 1 meter. Okay, and you can see that in general, when things are moving forward, we can estimate every single object, including cyclists, pedestrian, but most of them are cars. But one problem you notice that in the bottom, right? Certainly the detection is not very stable. You can see that the box kind of jumping around, especially in the post-estimation. So this is expected in the sense that this method right now is still an image-based method. We apply the detection algorithm on every single frame. There's no consistency over the video sequences. So this essentially motivates us to work on the second extension problem we call the kinematic 3D object detection. So the goal for this work is that we like to be able to develop monocular video-based 3D detection systems, utilize the video as input because this is a very natural input for autonomous driving, right? Even for robotics. And we like to utilize the temporal motion as well as constraints using an effective three-dimensional Kalman filter, which is the classic, tracking filter people have been using for a lot of 2D works. And finally, we also like to take one step further, improve the stability and accuracy of the detection algorithm in the process of trying to recover what are the physical motions in the metric space. For example, what are the velocity of the home camera? What are the velocity of every other car I'm seeing, right? For example, we're showing you one example sequence where we estimated the home camera have the speed of 7 miles per hour, while each of the rest of cars, we're also estimating its speed in terms of 13 miles per hour, 7, and 28. And we also have the green vector indicate its motion, its travel direction, basically. Yeah. On the right-hand side in the bird's eye view, because we're doing tracking in the process as well, so you can actually have a history of the previous car location. You can even do forecasting in the 3D space as well. Okay. So, what are the scenario for what are the previous work in this space? Video-based object detection has been done previously in a lot of 2D object detection case. Typically, those work with 2D optical flows, and you want to kind of warp feature maps, and then you can aggregate features from both counter frame as well as previous frame. And it typically help runtime efficiency because you don't have to apply the same algorithm to every single frame. And usually those data assume minimum camera motion. So unlike autonomous driving, we have constant motion, but those cases typically the camera motion is relatively smaller. However, in 3D object detection, there's no previous work in terms of doing video-based object detection. Okay. As we mentioned, we like to utilize a three-dimensional Kalman filter. So because we think it's efficient and also it's a parameter-free algorithm, it can easily integrate a series of measurements over time. You're also trying to model uncertainty naturally using Kalman filter, right? So you have model uncertainty together with observation uncertainty can be combined in a mathematical formulation. So this is nice. So for example, given the previous state variable, right, assuming it's a Gaussian distribution, you could apply a transformation matrix, which is a prediction step based upon some physical motion models. And this will give you a new updated state, right? And then the updated state will be combined together with the measurements you are receiving from the current frame T. And this combination will eventually lead to the newer, the next state variables. And this looping will essentially keep going. Yeah. In this process, there's a few challenges. Number one is that you have to assume, some sort of covariance for both the process or the model as well as observations, right? These have to be computed somehow. Secondly, you also have a known physical motion model. You have to assume that motion model for this to work. So for the autonomous driving case, to address those challenges, what we do is that we trying to physically model constraint so that we say that the car can only move in the direction of orientation, right? In other words, the orientation estimation almost tell us that which direction the car will be moving. Okay, so therefore the orientation estimation become quite important. And secondly is that we like to decompose orientation, into a number variable instead of a single variable so that we can increase the stability and the robustness of the orientation estimation. And finally, we have a self-balancing 3D confidence so that we can try to have more understanding about uncertainties, because uncertainty is part of the karma filtering requirement. Okay, so take a look at the self-balancing confidence score. The idea is that typical for detection problem, people typically having some confidence for the box by either estimating 3-dimensional RU or people reuse the classification probability scores. Yeah, and instead we want to define a self-balancing loss, which will producing a confidence. It can essentially try to help us, mining hard negative samples. So here's the equation we're using for this estimation. In this scheme, you can see that we're trying to balance between two terms, right? When the 3D loss is small, right? When 3D loss is small and omega tend to be larger, means that right now I'm more confident, right? Because smaller L3D multiplied larger omega is fine. And in that case, 1 minus omega will become lower. In other words, when L3D is larger, I'm less confident. In that case, I wish the omega will become smaller. So in that sense, you can see that it's a trade-off between these two different variables. So one benefit, you can see that eventually if we compute the correlation, right, between the score we're estimating as well as 3D RU, you can see that the correlation coefficient for our confidence is 0.4 almost. But if people using previous classification probability, you can only have the correlation coefficient of 0.25. So higher correlation coefficient means that we have a better estimation of the confidence. So overall, the framework is like this. So we have a backbone network taking the counter frame T as an input. It will produce a feature map X, and then it will produce the classification, and the T is essentially the state variable, and omega is confidence. Yeah. And the second part, we're trying to have an equal motion estimation module. Will take the feature map from the current time T and the feature map from previous time T minus 1 and send into a very simple, 2-layer equal motion estimation. And eventually it will estimate phi and rho, which are the 6D translation as well as rotation, the typical equal motion parameter. And then so the 3-dimensional Kalman filter will take the tau, that's a state variable, and doing the forecasting based on the motion model, and get the tau t prime. So this will be the update or forecasted state variables. And then I'm going to apply ego motion to the state variable so that the ego motion can be compensated, right? And because this is the important part. And then next, we're doing the association. You can build up history with the previous frame as well as doing updating. Updating essentially try to combine the model updating as well as observation based on the uncertainty to get the new state variable tau t. And this will essentially finish the updated step. Okay. So let's look at some results. And again, this will be tested on the KITTI database. So we are testing on the 3D detection performance. That's what's on the left-hand side. Right-hand side is the bird eye view detection performance. This is on the official test set, not on the validation 1, 2. Again, there are 3 different sets, easy, moderate, and hard. So you can see that compared to previous work on the 3D detection, right now we're further improving compared to AM3D. This is very recent work. I believe it's in this year's CVPR 20. And the M3D RPN, this is our previous ICCV work. And so we further improve compared to this works. And not only that, if you compute the efficiency, because AM3D involve a number of networks, so it's not a single network. That's why eventually the speed is roughly 3 times slower compared to us in terms of running time. So in the bird's eye view, I would say overall the two methods are competitive. They have similar performance. We are a little bit better on easy, but we are a little bit worse on the hard. Okay. So not only that, we also evaluate our performance in terms of velocity estimation as well as ego motion estimation. So in ego estimation, because ego motion estimation, because we didn't do anything sophisticated, we have an error about 6 miles per hour in ego motion. For velocity estimation, the current error is about 8 to 9 miles per hour. In other words, if the car is driving at 30 miles per hour, our estimation can be anywhere from 21 to 39. So that's current kind of velocity estimation. So let's look at some results. So these are some quantitative results showing some examples of different variety of estimation, but I think the video makes more sense. So over here, you can see that the top is ICCV work, image-based 3D detection. The bottom is video-based detection work. So you can see that in the bottom, we're estimating the home camera speed. That's the current my own speed. And the yellow number on top of every box, they are essentially the velocity estimation for other, detected cars. You can see that when I slow down, right? So everything, become 0 or almost 0. There's still 1, 2, sometimes it will become 1, 2 small numbers. But you can see that the number seems making sense. On the right-hand side, you can see we also have the tracking history for all the vehicles we are detecting because we do association over time. So you are actually doing tracking. In the meantime, you could also do forecasting. You can follow the trajectory, predict into the future if you like. Yeah. So the nice thing I like about this is that everything is done in the 3D space using a single camera. So you can imagine this could be a kind of the framework sort of built into the future. In the future, we can further improve the ego motion accuracy, and so that the velocity estimation will become more accurate. With better velocity estimation, and I think the video-based information integration will become more precise. It will help better, detection system eventually. Yeah. Yeah, I like to, watching this video. Actually, I think this is quite enjoyable to see how the detection, estimation the different speed of object you are detecting right now. Yeah. So compared to the top, you can see certainly the robustness is much better compared to top, especially we don't have a lot of jittering like what we have on the top. Okay, so with that, let's move to the second part we call the monocular 3D object reconstruction. So this is also ongoing work, and the goal is that giving a single image of a natural object, we like to be able to reconstruct the 3D surfaces in the sense that the complete surface should be estimated. And so this also there's quite some previous work in the space, but in general our understanding is that the previous work may do very well for the synthetic data, but they might have limited quality in terms of 3D shape reconstruction for the real data. And typically, previous work do not model albedo and lighting, and also very few of them try to leverage in the wild data for training. Most of them are trained from synthetic data. Okay, so this is the kind of the problem we like to address. We like to be able to train test on real data, even though we would have ground truth. We like to have a complete generic object model, including multiple components such as segmented shape in terms of pose and albedo and the lighting. Right? By combining all 4 of them, we can actually synthesize a natural image. Right, so this is essentially analyze by synthesize. If I can do this synthesize, I can actually have an analysis module to decompose the image into these 4 components. So that's the basic idea. So eventually, giving an input image, we have encoder. We like to estimate, lighting L, camera projection measures P, and FS is a shape latent code. FA is albedo latent code. And the last two of them will be sent into decoder DS and DA, which are both implicit functions and to recover the occupancy field as well as color field. And then by using a differential render, you can combine all four information and having a reconstructed image. And this should have, smaller self-reconstruction loss compared to input data, right? So this framework essentially try to combine the model fitting, model learning together. And when this are trained, DSDA are basically the model itself, and the E is basically the model fitting functions. So this framework was actually originally applied to face images. We have, a number of CVPR paper as well as PAMI paper on this topic. Right now, we'd like to see how well this can be extended into generic objects and what are the challenges. This is what we're trying to face right now. So in terms of shape representation, we use the implicit function, especially we borrowed the idea from Professor Hao Zhang in Simon Fraser University in terms of branched network output, where giving shape code as well as a pointer XYZ, we eventually generate 4 different branch, and these are indicate the segmentation part labels actually. The max polling of those 4 parts will give me an occupancy estimation. So when occupancy value equal to 1, it means that the point is inside the shape. Otherwise, 1 means 0 means outside the shape. And for albedo representation, we actually, propose somehow a new way of doing it. That is similar to the branched shape. Here we have the branched albedo as well, right? And which branch a point XYZ is chosen actually is depending on which shape you're chosen. That makes sense. So that if one point belongs to the body of the car, eventually the albedo we're learning from C1 is also coming from the body. So you can see that we essentially have a parts level, representation for both the albedo as well as shape. So in terms of rendering, giving a point in the final render image, we have a light ray from the camera optical axis and shooting through the point into the space. And this will help us to compute which surface point we are essentially interact by using the implicit function. And given the surface point, now I can send this into the decoder, albedo decoder, get RGB based albedo information. And this will go through the rendering equation where I have surface normal and lighting, eventually generate the color information of the point. Yeah. So in terms of training, we have 2 stages. The first stage is using synthetic data for training, so that we can learn the shape decoder as well as albedo decoder and the encoder. And the second stage is unsupervised joint training, where we take image reconstruction loss, silhouette loss, as well as regularization terms to do the training. The silhouette loss trying to make sure that the projection of the 3D surface will be consistent with the estimated 2D silhouettes. So this is the eventually learn the shape model. You can see that the shape model is quite continuous as well as cluster according to different car types. So with this shape space, you can see that eventually all we have to do is a very good encoder that can map a natural 2D image into one point in the space. If the mapping is precise, then we can generate reconstructed 3D shape. So let's look at some results. So these are the qualitative comparison with previous 3D single image 3D reconstruction algorithm on synthetic images. So most of the algorithm are doing fine, but our algorithm are doing pretty good. Our algorithm can also generate the parts-based segmentation information. And this is a real image. Of course, this is much harder. You can see that the performance improvement seems to be more than the previous case, as well as we're also generating the parts-based labeling for this case. So quantitative evaluation, we test on 2 different databases. One is Pascal 3D, one is the Pixel 3D. Notice that when we compare with previous work, we have 2 different models. One is S. S means that we have a single model, single 3D model, actually trained for multiple object category, okay? And the next one is the last column is actually the object specific model, means that for one object category, we train one model. So clearly, right, object specific model will have better performance. So therefore, the transfer distance error is smaller. Okay, the smaller the better. But no matter what, for both cases, even for generic models, we are better than previous method, which some of them are generic, some of them are object specific. So eventually the goal of this line of research is that we like to be able to do 3DMM, hopefully for ImageNet, meaning that for any natural object category, we like to build a 3DMM model, kind of what we have been doing right now. And hopefully with our 3DMM model, we can do object-specific fitting and to be able to recover the 3D information. Of course, this is a very challenging objective. Right now, we can do it for a few categories because we do have the support from the ShapeNet. But ShapeNet only have 50 categories, but ImageNet have 1,000. So there's still a huge gap. There's a lot of research opportunity here. Okay, so far I mentioned about detection and 3D reconstruction. In the lab, we're also working on other problems such as more low-level vision as well as some high-level for autonomous driving kind of problems. So due to the limited time, maybe I will spend next 3 minutes and talk about two relevant work. One is what we published in last year's CVPR, which we call the depth completion, essentially giving RGB image as well as sparse LiDAR. How do we generate the dense depth information or super resolved depth information? So conventional work typically have the smearing issue, meaning that you generate a lot of points with in-between depths of the foreground and background. Those points actually does not exist. So this will cause problem for the subsequent detection problems. In comparison, our model does not have this kind of issue because we have a new non-parametric called depth coefficient representation that can model the probability of possible depths in using a 80-dimensional vector, and this will allow me to minimize the smearing issue. So this shows some of the results where you have input sequence where bottom you have the estimated the super resolved depth information, and that is corresponding the bird eye view on the right hand side. So in addition to depth completion, we also do monocular depth estimation. So this is a work actually published or will be show up in this year CVPR in this week. So my student Shenjie, he observed that giving RGB image, if you let him do both depth estimation and the semantic segmentation, he found that in terms of the quality of the boundary, semantic segmentation have much high quality in terms of the boundary. So this gives him motivation to say that why don't we use the high quality boundary information from the semantic segmentation to help the depth estimation also produce higher quality boundary. So this is his motivation. So to do that, he actually try to apply a morphing, essentially morph the estimated depth according to the boundary of the semantic segmentation, so that this morphed boundary will provide a next level supervision for the network. And this will be done iteratively during the training process. So this will eventually lead to better quality, especially on the boundary for the depth estimation. So he shows that actually for the first time, his self-supervised depth estimation can achieve the same absolute relative error compared to the supervised depth estimation method. So this was not possible previously. And so this is kind of the surprising or interesting observation we have. So in summary, the take-home message is that 3D detection from 2D images are just in the beginning, and we feel that the modeling and recovering the motion actually may benefit detection. I think this is also a very natural thing to do for the motion estimation, recover the physical motion. And finally, we like to say that fitting category-specific 3D model can actually lead to numerical benefits such as reconstruction and the post-estimation as well as the lighting estimation. I'd like to thank my students as well as sponsors for working on different problems in this area. Thanks for your attention.
Thank you very much, Dr. Liu, for your fantastic talk. And we have some questions from the audience. And let's say first from the audience, the first question would be: for 3D object detection, do you apply detection and tracking or perform detection? I think what he wants to ask is whether when you do the object 3D detection, you first do detection and later tracking the detection result, or you do perform per every frame detection.
I think he is referring to the new work we're talking about, this video-based object detection, right?
I think so.
So yes, in this work, according to this network architecture, yes, it is correct that for every new frame, for every current frame, we go through the conventional image-based detection schemes, right? However, we are relying on the eagle motion estimation as well as Kalman filter to modify or update the detection result, update the single frame based detection result, so that eventually the state variable tau t will be a more precise 3D boxes. Okay.
Okay.
So you can imagine this 3D Kalman filter essentially is a model without any parameter, right? It's kind of a scheme that we are taking, you know, the estimation from the single frame as well as the model information to integrate information from the past into the newer results.
Okay, I got you. So for each new frame, you try to find the association between the last previous frame in this case, right?
Yes, we do association.
Okay.
Yes.
Yeah. Another question is how well does the proposed method work in real scenarios?
I guess it also referred to this work.
Yeah, I think so.
Well, right now the issue that there's not many database. I think we could try this kind of algorithms, right? First of all, you know, there's still quite some requirement for training this type of algorithm. For example, for the new scenario, you need to have camera matrix. Camera have to be calibrated, right? Both intrinsic and extrinsic parameters. Number one. Number two is that for new scenario, typically you might want to have some labeled 3D boxes for training purposes, at least for fine-tuning purposes. So the short answer is that we don't know. I think how to make this kind of model to be more transferable from database A to B to C or to real world scenario would be an interesting research question by itself.
Okay, I think in this case, I want to have a follow-up question. And I saw the current 3D detection compared with 2D detection. 3D detection's accuracy is much lower, and somehow quite a lot of time they have just for IOU bigger than 0.7, the accuracy maximum is something like 27%. What do you think is right now the bottleneck of 3D object detection?
Good question. So this slide I'm showing, I was actually hiding this slide. So if you look at this slide shows that depend on the 3D IOU criteria. Right now, the criteria is 0.7, right? When it is 0.7, you can see that the AP is very low. You know, for all the distance, all meters, the AP is as low as you know, about 20% ish, right? But if you relax the 3D IOU criteria 2.5 to 0.5 or even 0.3, you can see that the performance will be a lot higher even for 3D detection. So what it means is that we don't have much missing rate. We are detecting all the 3D boxes actually, but it's just the location of the 3D box is not very precise in terms of the compared to ground truth, especially in the depths.
Yeah. Actually, quite a lot of work for 3D object detection using the depth. First, they estimate the depth and then do the 2D detection in combination with the depth estimation together with the normal object detection. They try to do the 3D detection. And do you think this is something how you think about doing the similar thing, or you think quite now so based on anchor base is better?
Yeah, so this is what we're trying to contrast with in the beginning, right? You know, those approach, the modularized approach has its own benefits, right? Because it's maybe it's easy trying to figure out, you know, which module gets wrong. You can do more analysis. But we felt that, you know, the computation complexity of the model eventually is quite important. So we like to see that whether a single model is able to do what we want to do. So that's why we did not want to have separate modules for doing depth estimation.
Okay.
But yeah, maybe some implicit depth estimation might be helpful within the network. And,
okay. Yeah. Maybe we have one more question. So in your 3D and for albedo and the shape, for those two encoder and the decoder network, do you train separately and then combine them together, or you train them simultaneously?
We have multi-stage of training process. The first stage is we train the shape decoder first, Okay, because shape decoder you can train just based on the voxelized 3D models. You don't have to involve images. And once that's been trained, we actually fix the shape decoder. We never update it. However, for the albedo decoder as well as the final encoder, both two of them will be updated whenever we bring the real image into the training process, because both of them can be benefited from the real images.
Okay. Another question from myself is when in your 3D object detection and you use something like Atlanta and to control how much weight you gave to the how much confidence you gave to the 3D loss versus the 2D loss, and do you have a number that is normal? What is the confidence normally you assign?
So the omega is the confidence we're estimated, right? Omega goes through a sigma function, so it's guaranteed to between 0 and 1. So it's normalized the variable.
So do you have some number? And because if you have something omega is very small, that means your 3D loss is always very, very unconfident. And but if you on the other side, if you have very big number for omega, and that means the 3D object, the 3D loss is always very high, and that really determines whether later the efficiency of different losses.
So the only way we're utilizing the omega is by using common filter, because in common filter, you're trying to balance the uncertainty from the model prediction from the observation, right? If the uncertainty from the observation is very, very high, high uncertainty, you will rely on the model prediction to say where the next box. In comparison, if the uncertainty of the observation is very low, I'm so confident, I will almost forget about the model, only use my estimated location from the counter frame as my final estimation. So therefore, common filter naturally combine the information from model prediction as well as observation. And that's how the omega will be used in the fusion process.
Okay, and do you have something like an estimation from the omega, and how in common filter in the common filter always estimate what is in the range of omega here?
So omega can be anywhere from 0 to 1. For example, this is a typical kind of the range we're estimation. I would say most of them look like to be somewhere from 0.5 to 1.0. And you can see that right now the correlation coefficient is not so high; it's only 0.4, which means that the omega is only somewhat indicative of the 3D RU, but it's still not very precise. Right? If you have a very good omega estimation, I think this will be very beneficial for information integration over time.
Okay, thank you very much, Dr. Liu. I think we run out of time, and for the next speaker, and I would like to thank you again in representing another more than 100 people here.
Sure, thank you. Yeah,
thank you. Okay, so now I think we, Professor Matsushita, is my pronunciation correct? Professor Matsushita is already here.
Hi, how are you?
Good, how are you? Okay, I would like to it's my great honor to introduce Dr. Yasuyuki Matsushita. And Dr. Matsushita is a professor at University of Osaka, and he received his BS, MS, and PhD, and all from University of Tokyo. And prior to this position, he was with Visual Computing Group at Microsoft Research Asia for about 12 years, I think. He has very been supportive in the community's development. He's the editor-in-chief of International Journal of Computer Vision, IGCV, and also in the editor board of PAMI, Visual Computer Vision Journal, and many other journals. And is serving right now as the program co-chair of PSVT at 2010 and 3D IMPTV, which is currently 3DV in 2011, ACCV and ICCV 2011, and the general chair in ACCV 2014, and will be the general chair of ICCV 2021. I still remember during the time when he was a program chair of ICCV 2017, when he was very busy in organizing this conference, and he still takes some time to help review the papers in our workshop. He has already conducted extensive research in various methods for 3D reconstruction. Especially, he has pushed significantly development on photometric stereo, shape from shading, and some of his recent work has been applied using structure from motion and for calibration. I'm already very excited to see his talk today. Let's welcome for Dr. Matsushita's talk.
Thank you very much for very kind introduction. And I thank the organizers for having me in this workshop. From me, I'd like to share our recent work on light source estimation based on structure from motion. Okay, so let me begin with a little bit of context. In our group, we are interested in shape estimation from images observed under varying lighting directions. And suppose a static scene observed from a fixed camera. Then we can take a photograph under some illumination. Then we move the illumination only, then take another photograph. We keep doing this to observe, many different shading variations on the surface until we are satisfied. Then from such observation, we can obtain the shape in the form of surface normal. And this approach is called photometric stereo. So this visualization is basically showing the surface normal color-coded in RGB color channels. So for example, green pixel represents the surface looking upward direction, and magenta indicates that this surface point is looking at the right bottom direction. So this surface normal, the photometric stereo gives us a lot of information about the surface detail. For example, let's look at this video. Suppose we have a set of images observed under different illumination and also from different viewpoints. Then from this kind of input data, we can certainly apply some structure from motion or multi-view stereo in order to recover the shape. So that is something we call geometric approach based on triangulation. For this particular scene, without a lot of texture, it's not easy to establish the correspondence across different views. Therefore, geometric approach is not that great. But with photometric stereo, with photometric approach, we can recover very detailed surface. So for a photometric stereo to work well, we need to calibrate the light source directions or positions. Here is a very simple Lambertian image formation model, which is often used for photometric stereo. And of course, the goal is to estimate the surface normal n from a set of measurements m. This is a measured pixel intensity with the knowledge of the light source direction L. And in order to solve for surface normal n, of course, we need multiple observations and the different lights. But what's important is we need to calibrate the light source directions accurately as good as possible to recover accurate surface normal n. So this is why we are interested in light source calibration. We want to know the light source direction precisely, or light source position. And also the light source may not be directly observed from a camera. So that's the point. Okay. So this motivated us to develop a simple and accurate point light source calibration method that we call light structure from pin motion. As you can imagine from the name, the method uses structure from motion for determining light source directions or positions. The work is done by my student Hiroaki Santo here, and my ex-postdoc Michael Bechter, now with Facebook, and the Professor Samejima, now with Amazon, and the Professor Sugano, now with University of Tokyo. So these three people are gone, but this student is still with my group. Okay, so let me begin with problem setting. So what we want to know, either the light source position or direction. So one is that there are two types of light sources that we consider here. One is something called the nearby point light source, which is located near to the scene, so that we want to know the 3D position of the light source. The other type is directional light source. Point source located infinitely far away, so we only want to know the direction of the light source. In either cases, the camera may not observe the light source directly. Then how do we determine the light source position or direction? So this is a problem. There are some previous works to solve this problem. So one approach, one of the effective methods, uses multiple mirror spheres placed in the scene and observe the specular highlights on the sphere. Then, based on the triangulation, they can determine the light source position. Of course, we need to know the location of the spheres for doing this. Another method is also based on a mirror, but a planar one, whose pose is known by some marker, alcohol marker or something. By observing specular highlights at the different poses of the mirror plane, they can recover the light source position again by triangulation. So these existing methods are effective, but they rely on specular highlights on the calibration target. Therefore, they need to detect the exact position of the specular reflection. However, since the camera observes the reflection of strong light, the highlight can become very wide, which makes it very difficult to determine the precise position of the highlight center. In addition, sphere-based method needs to know the precise position of the spheres. To achieve this, it requires to measure the sphere distance in 3D and fit ellipsoids to the sphere boundaries in the image, which is not that easy to do. So in our method, we therefore avoid spheres and highlights, and instead use small shadows on the calibration target. In this figure, the left-hand side is just a camera and light sources, and the board on the right-hand side is our calibration target. The calibration target consists of a planar alcohol marker board and some needle pins randomly stacked on the board. Okay, this is, so I'm going to show you how this, this board can be made. So first we print the 2D marker on the paper and paste the paper on the flat board. After that, we pin needle pins on the board. As you can see, our target board can be made in less than 1 minute. An important point is that we don't need to measure the pin positions when creating this target. So pins can be randomly stacked on the board. So in a few minutes, from calibration target, why we can recover the light source positions or directions. So as shown in this figure, when we turn on the light source, we can observe the shadow of the pinhead. Like this. Suppose this light is on, and then it casts a shadow using this pinhead as a shadow caster. If we know the pinhead position, if we know this position, then we can easily compute the light source direction from this shadow position. So we are assuming that we know this shadow position because we know it's on the plane and we know the plane coordinates. However, the thing is that, so the important point is that it is not necessary for our method to know the pinhead positions. But we can just place the pin randomly. So we treat this pinhead position as unknown, but we can still recover the light source position or direction. Okay, but we move the calibration target in front of the camera so that it can observe the board under multiple different poses. So this is the condition. Okay, let's look a little bit into the mathematics. So we can regard the light source as an inverse pinhole camera. So here we have a traditional pinhole camera, and this camera projects the object point X to point S on the image plane. So this is a projection, right? Everybody knows about that. Now we replace the pinhole camera with a point light source. So instead of receiving the light through the point like a camera, it emits light from this point, light source point. As a result, it projects object point X to point S on the shadow receiver plane. Mathematically, both projections can actually be formulated in the same way. So 3D, 2D projection can be written using projection matrices. And so the left-hand side is camera projection, and the right-hand side is shadow projection. For left-hand side, we all know that, oh, something is wrong. Do you still hear me?
We can still hear you, yeah.
Oh, somehow my mouse cursor stopped working. What can I do?
Do you want to restart the sharing?
Yeah.
Another speaker told me he cannot hear you.
Really?
But I can. What about others?
I can hear the sound too.
Okay.
I'm sorry, my keyboard and mouse, they don't work.
So do you want to exist and restart the slides?
Can I restart my PC because I cannot control anything now? Sorry about this.
No problem. It happens always. That is always online issues.
Oh, okay. Well.
So I think Yasu is restarting. So I think we just wait one minute, and I think Dr. Matsushita is restarting his computer right now.
Hello.
Oh yeah, right now we can see you. It seems the screen is freezing again.
Okay, so I switched my PC. Sorry.
No problem. No problem.
Okay, good. So
we can
see.
Yeah.
Okay.
I can see the slides right now. Yeah.
Okay, good. So sorry about the trouble, and let me try continue the presentation.
Yeah, sure. Yeah.
Good.
Yeah. Good.
Okay,
Yeah.
so here is a image and
Dr. Matsushita, when we have some issue in hear you sound, it seems like it stopped somewhere, and I don't know whether it's my issue or anyone else has the same issue right now.
Okay, so can I go back to my original PC? It rebooted automatically.
Okay.
Take 1 minute. Sorry.
Sure. Okay.
Hello?
Yes. Now it's much better.
Okay, so now I'm back. Sorry about the trouble. So
always internet yeah.
Yeah. So this is a camera projection and shadow projection, and they are mathematically the same thing. And the left-hand side is a camera projection model, and we all know that this is we have intrinsics made of focal length and the optic center, and similarly for shadow projection we also have intrinsics made of the position of the light source, and also we have extrinsics here, left-hand side, rotation translation. The similar thing for shadow projection, we can write the extrinsics of shadow projection model like this way. And if we take a product of these intrinsics and extrinsics, we have a projection matrix. This is for nearby point light source, and which looks like this. And for our directional light, we have a very similar projection matrix, but the only difference is this part is 1 and this part is 0. Okay. Then in camera projection, the problem of structure from motion is to estimate the projection matrix P and the 3D point X from known observations S, observed image points S. So this is called the structure from motion, as we know. And in the our calibration method, we want to estimate the light matrix L and also pinhead positions X, which is a shadow caster, from the shadow positions S on the shadow plane. Since this is so similar to structure from motion, we call our method light structure from pin motion. So as you can see, the problem setting is almost equivalent. Structure from motion wants to know P and X from known S. And in our case, we want to know L and X from known S. Okay. The solution method is also essentially the same. So we rely on boundary adjustment. So we minimize the reprojection error on the shadow plane, shadow coordinate. So which is just formulated as the least squares of the reprojection error. So here red variables are unknowns. Unfortunately, this is a non-convex problem. So how do we initialize the solution? Because it's a non-convex problem, we want to have a good initialization. If we have that, it is likely that we can reach to our good solution. So we begin with this equation. So there are two vectors. One is from shadow point to the light source, so which is green. So this forms one vector. And also a shadow point to the shadow caster point, which is blue in this figure. And they should be parallel. So that gives us a constraint like this. So the cross product of green and the blue vectors should be 0 vector. Then from this, we can establish a system of equations like this. And we don't have to go into the detail, but the important thing is that these red variables are something we don't know, and the black are that we know. This contains some second order terms, but we simply ignore these variables, and then we only solve for this first order variables. Okay, so to solve for so we have now 6 unknowns, right? 6 unknowns, and we have a lot of equations. For this linear system, for solving this linear system, we need at least 5 pauses. This is the conditions that we derived. So the number of pauses required for solving this equation should be greater than 4 plus 1 over n number of pins. Okay, so we can increase the number of pins, but it doesn't help to reduce the number of pauses, essentially. So here I'm going to show some simulation experiment. And first I discuss a synthetic experiment. So here I show the result of experiment where we added some noise in the shadow detection part. So if there is no noise in detecting shadow position in the image coordinates, then the light source estimation is perfect, essentially. So there's no error if the shadows are correctly detected. And as we increase the noise level in the detected shadow locations in the image coordinates, then gradually the error increases. And the right-hand side is about the number of pauses where so here we are assuming that we have some noise in detected shadow location, and then in that case we analyze increasing the number of pauses, whether the increasing number of pauses help. And it actually does. And as we increase the number of pauses, the estimation of the light position becomes more stable. So the recommendation is that, as we always expect some noise in shadow detection, the more pauses help. I mean, more observations of different pauses of the calibration target, that actually help. Next, I explain our real-world experiment. We performed, under 4 different settings. And so E1 and E2 are nearby point light sources setting, where light source is close enough to the target. And E3, E4 are regarded as distant light source setting. So one uses sunlight, which is far enough. And the other is a flashlight located sufficiently far away from the target object. So for nearby point light sources, we want to estimate the light source position. And for distant light, we want to know the direction. And here are some results. For this setting, the light source position estimation error was like 6.4 millimeters. And for this setting, it was 2.5 millimeters. And for direction, sunlight source estimation direction error was 1.1 degree. And for this setting, 0.5 degree. And here is some reprojection of the estimated light position in the image coordinate. And the blue is ground truth and red is our method, which shows, well, from my viewpoint, it's sufficiently close. Okay, so we also evaluated the pinhead position estimation. And here are mean error of pinhead positions. So they are like less than 2 millimeters in all the setting. Actually, the pinhead size that we have used is diameter of 3 millimeters. So this mean error is sufficiently small. And we did some comparison with the previous effective method. And it actually, our method works pretty well, as good as the previous work. Okay, so the conclusion is that point lights can be calibrated, just like in a camera case, using a structure from motion. And our calibration target is pretty simple and easy to make. We can make it really cheap. And I hope, if it is useful for any of you. So the code is available on somewhere, accessible from QR code. That's pretty much it. Thank you.
Thank you very much, Dr. Yasu. So we have several questions. Actually, this work is very inspiring, and because generally you switch from structure from motions camera pose estimation idea into the light source calibration, and share quite a lot structure from motion, quite a lot concept used for structure from motion. Right now, you can apply to the light results calibration. Some questions from the audience and myself is: do you have the evaluation about the pin number? How many pins you need to? Is it something like using a single one and you apply you switch quite a lot of different orientations, but the checkerboard can still give you a good result?
We actually did, but I forgot the result. But if my memory is correct, the more the better. But at the same time, I kind of remember that it didn't help much. But you can refer to our paper. We definitely have that discussion.
Okay. And in structure from motion, normally when people have multiple using factorization based on structure from motion, after tracking for many frames, and when they later do SVD decomposition, and they have different solutions that makes that finally resulting in different scale. And in your calibration, do you have the scale issue?
We actually, let me recall that. No, we actually don't have the scale issue because we know the scale from the calibration target.
Yeah.
We have the arco marker and we don't have that scale issue thanks to the calibration target. So it's a easier problem compared to the general structure from motion because we know the reference object here.
So if we remove the AR code here, and do you think in this case will the calibration still work? Because right now you are mainly estimating the direction, and maybe for position estimation that may have a scale issue. But what about for direction? If you are just interested in what is the sunlight direction, in this case, do you still need the checkerboard?
We use the checkerboard for two purposes. One is to know the pose of the calibration target, and the second is to know the scale. Mm-hmm. And we definitely need to know the pose, even if we forget about the scale. And in order to, so as long as we have an access to the pose of the calibration target, we can remove this arco marker in order to achieve the the calibration of light directions.
Okay. One question from the audience on what are the main results? What are the main sources of the error? And is it from the detection or optimization?
It's actually detection. So detection of shadow is not that easy. So that's our experience. And quite often, we have some environment lights, and in that case, shadow becomes really, blurry, and it's not easy to, accurately determine the center of the shadow. So that's a tricky part.
Okay. A follow-up question from myself is: when you try to do the optimization, for structure from motion, and when people do this optimization, they try to do SVD decomposition and then select the eigenvectors corresponding to the smallest selected 3 eigenvectors and remove everything else and make it as a 0. And do you do similar optimization?
We actually didn't do that. Is that, assuming some orthographic projection? If you describe the SVD and the finding null space, and then disregard the other part.
Okay, that is very inspiring. And you mentioned I remember you showed the result for different capture of the place. Do you have some idea, suggestion that how many numbers of the capture should be okay to get you a good calibration?
I'm really bad at remembering numbers, but that should be on the paper as well.
Okay.
But nowadays you can record videos, right? So you can just move the target in front of the video camera, maybe less than 1 minute. Then you definitely accumulate a sufficient number of frames.
Okay. Yeah, I think that is pretty much most of the questions, and there might be some other questions on YouTube channel. And right now it's still about 100 people watching out the video, and we really want to thank you for your great talk. That is very inspiring. Actually, this idea I would say can be used for calibration. Maybe we can simulate this idea for many other tasks as well. And I would really think this is a very interesting and inspiring work. Okay, I would like to thank you again, Dr. Yasu.
Yeah, thank you very much.
Thank you very much. Yeah. Okay, now it's time for the last speaker, Dr. Jing Yu, and he's already here. I would like to introduce Dr. Jing Yu, and he is an executive dean in the School of Information Science and Technology at Shanghai Tech University. He received his BS from Caltech and a PhD in MIT. So he's also affiliated to University of Delaware in USA, and his research interests in different topics: computer graphics, computer vision, and especially computational photography. And he has received, from his work, he has received an NSF Career Award, Air Force Young Investigator Award, and he has been general chairs, program chairs, and area chair for many international conferences such as CVPR, ICCV, ECCV, ICCP, and NeurIPS. And he's also associate editor of PAMI and IEEE Transactions on Image Processing and the CVIU. He will be, he is as program chair of ICPR and will be the program chair for CVPR 2021. Dr. Yu has been well known on the contribution of light field and its applications to 3D reconstruction. Now let's welcome Dr. Yu for his talk. We cannot hear you, Professor Yu, right now, it seems like. Is it my issue? Wenshan, can you hear?
No, I cannot hear the sound either.
Dr. Yu, can you hear us? I think he's restarting again.
Okay.
we still cannot hear you. Is it my issue? I still cannot hear.
I cannot hear either, but I saw the icon is changing. Maybe.
Yeah, I can see. I try to message him, but oh, right now he's back, I think.
Hello, can you hear me now?
Now, yes. Finally, yes.
Oh, I got it. I think it's the problem with the firewall from the university. So
okay.
Can you see my screen? Actually,
yeah.
Actually, 5G right now, 4G right now.
Okay.
So, all right.
Okay, right now it works fine.
Okay.
Yeah.
All right. So okay. So I guess I can. You can see the screen now, right?
Right. Yeah.
Okay. Right. Okay. Thanks very much for the introduction, and sorry for the inconvenience, for the trouble. So the title of my talk is building a 3D human from head to toe. So I admit actually my talk probably is the marginally related to SLAM. I do have a little bit of SLAM component, but majority of my talk is on using recent deep learning techniques for 3D reconstruction, particularly on reconstructing a human. So let's start looking at a video. I hope you know the internet is fast enough. You can still see a little bit of the video. You know, this is showing a 3D human model we reconstructed, and we can position the person actually, on the table in VR and AR experience. So I think we're at a stage that we can actually very close to build a very realistic 3D human by using computer vision techniques. So how do we actually do that? Well, actually, the time can be backtraced to 10 years ago when I was still a professor at the University of Delaware. And at that time, I got a call from the office actually asking if I can use computer vision to reconstructing the surgical procedure. Well, so the idea is actually in surgical training, actually, it requires a lot of efforts from residents, resident doctors to actually view the actual training process, the actual surgery process, in order to learn how to operate. So it's a very expensive experience, and that's why the doctors ask if we can physically record the experience, this surgical operation, but in 3D. So remember that was back in 2010. And at that time, there's we all know the camera resolution was still very low. There was still not very good 3D reconstruction techniques. So what we end up doing is actually to use a depth sensor, because we figured there's almost no way you can actually do real-time reconstruction, using regular RGB cameras or even stereo cameras. That's why we started using Kinect sensors. Basically, this shows you the 3 views captured by the Kinect sensors, and they are all very low resolution. But if you fuse them together, actually, you get a sort of an idea on how the doctor operates. Of course, you can't really operate on real patients. So in this case, I think he was operating on a gallbladder, from a goat, actually. So from a farmer's market. So it was a very exciting experience, but the challenge there is actually the resolution of the depth camera is still very, very low at that time. And we were still not able to, build a very realistic 3D reconstruction. So push, to today, actually, if we still look at the active sensors, for example, the depth sensors, they have actually, evolved a lot. The most notable example is probably your phone. On your phone these days, actually, there are always a depth sensor. For example, the iPhone has a front-facing depth sensor, and for many Android phones, there's a back-facing depth sensor. They use different technologies, ranging from structured lights to indirect time of flight. To the latest iPad, actually, they use the direct time of flight, which is more accurate and resolves ambiguity, but still at a very low resolution. So today, with these depth sensors, you can actually generate a reasonable 3D maps. This is trying to show you, the 3D maps you can actually capture with a relatively high resolution TOF, actually. But the challenges are multifold. First of all, you need a very expensive TOF system, in order to capture this very high quality 3D reconstruction. But more problematic is actually nearly all TOF sensors are depth sensors are equipped with the low resolution RGB cameras. And you cannot even texture map, for example, this model. If you texture map it, you see all kind of visual artifacts. So this is showing you one route of building a 3D human. The other route, actually, as I promised, the title of my talk is from head to toe. So I'm going to talk about toe first. Then by the end of my talk, I will talk about head. So in 2014, that was about like 5-6 years ago. So Google had this Google Glass project. So I tried to use this Google Glass project to actually try to capture the 3D geometry of a foot. The reason is actually we want to build which we call bracelets for the foot. So it's actually trying to to conduct a physical therapy for the foot. For example, your ankle gets broken, then you need to have this special mold actually to fit your foot, and it needs to be very, very accurate. So I'm going to, instead of showing you the complete video, I'm going to just show you a very short, because the video probably it does not work very well. But I want to show you that actually just moving the cameras around the foot, you can actually just using this structure from motion, for example, from previous talks, to calibrate the cameras, then you do 3D reconstruction. You can either use open source code map, or you can use commercial software such as Capture Reality or Photoscan. So there are many existing softwares you can do that. So one funny thing you observe actually in this video is actually, which I always say, for a passive computer vision to work, in the past, you always require people wearing patterned flower-ish socks, because you have to have features, you have to establish feature correspondences in order for you to calibrate these, cameras. This is the same as echoed by the previous speakers, right? You have to have a patterns in order to conduct a passive reconstruction. This actually turns out to be actually a devastating thing for real applications, because you cannot always ask a patient or a client to wear patterned clothes or patterned socks in this case. So we started this project. We thought it's a very cool idea. In the end, the doctor is, the therapist declined to use them, because the reason is it's just unreasonable for a doctor to ask the patients to wear pattern socks, So this comes to a very interesting observation. So you have two ends on building 3D human. One is using active sensing, right? So you can actually use depth sensors, but unfortunately that's low resolution, noisy, and also you cannot texture map it. So you have a 3D model without texture. You can also do passive, which will give you texture, because you have capture a sequence of images, but you rely on features, to establish correspondences for camera calibrations. So it's a two end. And today I'm going to talk about how to bridge the two ends using deep learning. Okay, so the story fast forwards to 2 years ago. So 2 years ago, two very famous Chinese cell phone manufacturers, Oppo and Vivo, they actually approached us because they saw my demo on capture 3D human, capture the toes, capture the foot. It says, could you actually do this on our phone? Could you actually, I hope you can still see the video. Could you actually, move your camera around a person and actually generate a 3D portrait of this person? So, and they also told me that, okay, our phones these days are equipped with actually depth sensors. There's a back-facing depth sensor on the Oppo and the Vivo phones. So it was a like a low resolution TOF, but it's still a depth sensor. So they were very, enthusiastic about this idea of when you move around a person, you can capture a person. But they didn't, and then I said, yes, sure, I can try to work on this because I have many solutions we can potentially integrate. But the problem instantly became out of hands because, like I said, the one of the biggest challenge is how do you actually calibrate these cameras? How do you actually register these cameras? You may say, okay, that's straightforward. Let's just run SLAM, right? Okay, so well, it's actually not that easy. So conceptually, in order to produce these kind of like 3D portraits, human portraits, you use a camera to capture a person. You move your camera around the 3D in 3D space. Then you do pose estimation of the cameras. Presumably, the intrinsics can be pre-calibrated. That's not an issue. But you do need to estimate the pose. And then you do 3D estimation or reconstruction. Conceptually, that's also easy because you have the RGBD sensors on the back, so you can use the pose to do point cloud fusion, right? And then finally, you can use for example, images to texture map the point cloud. It turns out none of this, none of the three techniques actually work, as I'll show you later. So there are always a lot of fix, to handle that. So let's talk about the 3D pose estimation first, which is most related to this workshop. Well, so we tried to use the best SFM software to do that. And so I'm showing you some of the examples. One is the photo scan, the AGSoft. So you capture the person using AGSoft, using the camera phones, and then you run a commercial SFM. Then on the left, it shows you the results. Remember, this is the commercial software. If you use a reality capture, you got approximately the same result.
Doctor, we lost your sound. We somehow lost the sound, seems like. Doctor, we still cannot hear you. Seems we still cannot hear. I can see you are trying to speak, but I don't know why we can't hear. Still not. I can see your microphone is you're trying to speak, but we still cannot hear. Still not.
Hi.
I suggest I thought on the WeChat and share the screen there.
Sure. Yeah. Yeah.
Let's see how I can disable my.
Okay. Okay. Then let's see whether it is the sound is okay. Can you speak and then we can test here.
I can hear, but it looks like a lot of echo.
Yeah. It seems. Doctor, what about your mute? Your mute, yeah.
I did the mute.
Yeah.
Okay. Can you talk right now?
Yes, but it's just a lot of echo. I'm trying to see how I disable my sound device.
So Vincent just
Okay, does it work now?
it works for me. Let's see, Vincent, can you hear?
Yes, I can hear.
Okay, you can hear Dr. Yu's talk, right?
All right.
Mhm.
Yeah, I think it's the firewall that's blocking everything. It's just ridiculous. Sorry about that. Okay. Can you hear this? Can you see the screen now?
You can see the screen.
Okay, great. Okay, so I think it's working partially, I guess. Sorry about that. Okay. So okay. So all right. So this is also showing you, traditional SFM. First is Xiaoming learning-based SFM. Once again, this is slightly, in this case, it's actually slightly better than the previous one because the percentage actually wears the patterned clothing. So it adds a lot more features, but still not very robust. So in order to handle that, we figured actually it's really essential to develop a new feature correspondence matching scheme. So this one should also take into account, two very important factors. Instead of doing like a regular feature matching, feature detection, feature matching, I think it's essential to actually classify the features. For example, map the features into a feature space on the manifold. So we developed the two learning a learning approach with the two modules. One is the appearance module, trying to cluster and map the feature space on the manifold, and then use a GCN to actually classify them. The second is once we obtain the initial estimation of the correspondence, they're not supposed to be very random, right? Because random in this means that actually many of these points are outliers. So we use a motion module actually trying to classify these motions from global versus local motions. Then use both modules actually get into this learning-based framework to establish much more robust correspondence. And it turns out to be working pretty well. So let me show you actually using this technique. Actually, you can actually indeed using the previous one, you can actually produce a 3D, for example, a 3D avatar using this techniques. Okay, so we then show this this result to open Vivo, and they're saying, okay, this is pretty nice, but there's always a but. But there are some issues. First of all, they complain the face is not a realistic enough. And the second is they also complain, the body, you only capture half body, you capture full body. And we all know actually if we capture full body, it's even more challenging to establish correspondences. And the geometry will be very cool. So I'm going to talk about how to handle both techniques, both issues, use learning again. So the first, like I said, they're complaining the results are okay, but no visual details, no body geometry. In short, it's not really. So how can you do good enough? Well, let's look at the photometric stereo, which was from from the previous slide. So if you use the photometric stereo, you can actually generate a very high quality 3D human. This is showing you by only capture 5 images, you can
Dr.
actually
Yu,
produce this.
can I stop a second? Are you showing different slides right now? It seems like from us, the slide is freezing on the SFM versus the ours. That slide.
Does it change it now?
No, it's still the SFM. Just the slide you begin to show, and compare with SFM with us, with ours.
Try to reshare. Are you seeing the correspondence matching slide?
Just 1 second. It's still trying to start its screen sharing.
Also, the sound quality seems not very good.
Oh yeah, because I'm using my phone and holding the phone to the speaker of my computer right now.
Okay.
So
Is the screen changed or?
no, we still cannot see the screen. So I'm thinking another solution, that is you can send me your slide. I can play the slide.
Okay.
And for this
let
one.
me try it again to see this how it works. Does it work now?
Still not.
So you cannot see my screen.
Yeah. At the very beginning, we can see very smoothly, and later at some point it stopped.
Let's see. If I can do this. Does it work now?
No, we still haven't seen your screen.
Okay, I guess I can send to you. Let me. Can I send to you through WeChat or?
Can you send through email, because I don't have the WeChat login on my computer.
Okay, I think the file is very big. What I can do.
Oh, I can quickly log in.
Okay. Sorry about that.
No problem. Don't worry. We don't have speakers afterwards, so we don't have too much time constraints. So you can send me the slides through WeChat.
Yes, currently it's a file.
Have you sent to me?
No, it's too big. It says there's a limit on the file size.
Okay.
So okay, let me see if I can do something else. trying to put it on the Google Drive so you can actually download.
Okay. Yeah, it seems like in Eastern world, just now Yasu has some issue. So yeah. Okay. Oh, right now we can see that. It seems yes. It seems yes.
Okay. Let me send you the link anyway, so just in case. Oh, but now it doesn't work. Yeah, maybe let's try this, I guess. So it's partially working now, right?
It's partially working. So Winshan is the sound. I can see the video. I can see the video right now. I just want to double check with Winshan whether the sound is very poor that you guys cannot hear.
I can hear, but not very clear. But it should be okay.
Is it better?
It's better.
Yeah, it's better.
Okay. I'll put it very close to.
It's much better right now. Yes.
Okay. All right. So this is showing you the video of using, this learning phase, the correspondence matching, then do the 3D reconstruction. But as I mentioned, actually the open people, they both complained about the poor quality of the face. They say the face, there's no detail on the face. There's also no body geometry, and also overall they don't think it's good enough. So they asked me, if we can capture better 3D faces, right? So one way to capture the 3D face is to use a photometric stereo. So can you see this video?
Yes.
Okay, so this is trying to show you that if you do use a photometric stereo, you can actually capture very, very high resolution faces. This is showing you one example. You can actually capture so many fine details, such as the beard, the teeth, all the fine details. So the problem with this approach, though, is that you can't really use it on a cell phone because you have to use a very complex setup to capture these very fine geometry. So can you actually do a sort of a quick solution to this? So at the ICCV last year, we presented our paper trying to use a learning-based techniques to handle that. So let me very quickly, go over this approach. Basically, our goal is trying to use a single image and trying to generate a very high resolution, 3D detailed facial geometry. So how do they actually do that? Well, it turns out that there are two very key components to handle that. The first key component is actually to get a better proxy face. A proxy face basically tells you, okay, well, this person what the person will look like. The second is a detailed layer. So you can add on geometric details onto the face. Okay? You can still see clearly, right?
Yeah.
Okay, good. Okay, if you have a problem, please let me know.
So just the one small thing is, are you holding? It seems like compared with the normal WeChat, your sound is still smaller than normally WeChat sound. Are you using the earphone or somehow not?
I use hands-free actually.
Okay. We can hear. Just is smaller than normal. Because when I use yeah.
Well, unfortunately, I don't have the headset with me, so I guess I will try to speak as loud as I can.
Okay, sure.
Okay.
Yeah.
Right.
Yeah.
So let's talk about the using learning-based proxy generation. So there are a lot of work on generating geometry proxies, but very few of them actually consider a very important factor, that is the emotion. So we first presented an emotion-based proxy generation. So why is emotion very important? This shows you one example, So this shows you two faces, one on the left, one on the right. So the two faces, they actually have very, very similar landmarks. They look very similar to landmarks. However, from a human's perspective, you can easily tell the left face is sort of sad, the right face is happy. But the landmarks are identical, so almost identical. So this shows you actually expression ambiguity is very dramatic. If you just use landmarks, you won't be able to generate very persuasive proxies. So we first presented a expression-driven proxy-based generation scheme, and the approach is actually use data sets captured in the wild, as well as the data sets captured by ourselves, the photometric-based data set. Then we add semantic features to emphasize emotion and appearance features at the same time. Specifically, we actually train a emotion net. We want to first learn what emotion the features represent. Then we want to use the emotion to learn how to actually generate the proxy face. So this is showing you several examples. So this is on the left shows you the Clint Eastwood. Clint Eastwood always appears very angry. So, but if you use a traditional express net, for example, the face looks pretty neutral, not angry. If you use other techniques, for example, 3D DFA, still maybe the facial shape looks closer to actually Clint Eastwood, but still not very angry-looking, appearance. But using ours, you can actually tell, using this expression-driven proxy generation, you can indeed tell from the proxy the person looks rather angry. So this is trying to show the first step using a learning-based proxy generation, but the uniqueness is to account for emotion. The second is to add the facial detail. So how do you add facial detail? Well, basically we present a deep facial detail net, DFDN. And the main idea is trying to use capture the data, the real ground truth data, to actually supervise the network in order to generate facial details from images. So we conducted two kind of training. One is called the supervised training, the other is unsupervised. The supervised training basically uses our own captured 3D facial data set, as I've shown you before, it's photometric capture, and this provides you many ground truth details. We also augment the data set using the USC ICT 3D data set that's also captured using photometric stereo, generate a very high accuracy facial geometry. But even with all these data sets, we only have a small number of ground truth data sets. So we further augment the data set within the wild images. But for the supervised training, the main idea is actually you can actually partition the images into patches, and you want to learn from patches, the details within the patches. I'm skipping the details. If you're interested, you can check the paper. But the more interesting thing is a large number of in the wild images. These in the wild images, unfortunately, do not have a 3D facial details. They do not even have 3D. So how can you actually verify our estimation is correct? How do you train the network? So the approach is actually trying to first estimate the albedo, the surface reflectance of the geometry. Then what you do is actually you use the estimated geometry, estimated shape to re-render the image and match the appearance of the re-rendered results and the ground truth results. Okay, and this basically the late Robin Williams, and of course we don't have a 3D model of him, but using our geometry proxy and detail synthesis technique, we can actually produce very high quality 3D faces, from a single image. Okay, and here's another one, an old lady. And here's my favorite, from capturing, a photograph of President Trump and Jack Ma, and using our proxy and the detail, you can actually capture the very fine details about those characters. Actually, in this case, emotion plays a very important role. For example, President Trump appears, neutral, probably not too happy, but Jack Ma appears a little more happy. So, you can actually see these emotions are reflected by exactly the shape, of the geometry proxy as well as the fine details produced by our results. All right, so, okay, let me stop for a second. So I've talked about, how can you generate very high quality faces, using this learning-based techniques. So next is how do you generate, a very high quality 3D human body, human shapes. So this is the video I'm going to show you, hopefully you will see, is actually a joint project with the Juilliard School in New York City. So we actually try to produce a person, three performers, one singer, one drummer, and one dancer, trying to use our capture system. If you take a close look of the results, you can actually see there are many artifacts. For example, you can see, the clothing actually stick to the body, and because of occlusions, and you see the violin, occluding the arms, will produce all kinds of visual artifacts. So this is showing you actually using the even passive or active 3D scanning, still produces a very strong visual artifacts. And if you think about the reason behind, what the difference is between the face and the body, the problem with the face is actually, you don't have detail. But the problem with the human body is actually occlusions. Because like the human body actually exhibits a very elastic, a very complex topology. And these topologies actually are very different, very difficult to capture. Whether you're using a depth sensor or a multi-view capture system, no matter which way you capture, you generate a very heavy occlusion. So how can you actually tackle these occlusions while producing satisfactory results? So and this year's CVPR, we actually presented something called the neural-human rendering. So the main idea is as follows. So instead of fixing the geometry, what we do, we actually is to use images when you capture this, human portrait using, many images. You use this image to actually try to fix the appearance. So you do not fix the geometry, but instead you fix the appearance, so that the person will look very realistic when you actually, turn around the person to see this 3D portrait. So let me dig into a little bit more details on how you can actually capture that. But before that, let me show you. Hopefully, you can still see the video. This is trying to show you, using this neural-human rendering, you can actually produce much higher quality 3D human body, even though they present, very complex topological, changes. Okay, so how do you actually do that? Well, actually, the way you do that is actually which we call the neural-human renderer. So the idea is actually you not only have the point clouds because you capture the point cloud, for example, using the RGBD sensors or using this multi-view camera system, and you also have a sequence of these movements. The person will move in space. So you can actually try to learn how the appearance is associated with the geometry, with the point cloud. And in order to do that, you actually can develop this pipeline. So from very low quality 3D point cloud, what you do is actually you can use something called the neural rendering to produce a high quality image at a new viewpoint. So it's not an old viewpoint in the capture system, but you produce or synthesize new viewpoints that look very good. But this can be very useful because once you produce a very good looking image, and for example, a mask, you can actually use a mask to reproduce very high quality, geometry. So the way it works is as follows. It follows we use a point net plus plus, trying to learn the features, at every 3D point associated with the appearance. Then once we learn the features, then we project the point onto the target viewpoint. But the key is once you project onto the target viewpoint, you concatenate the results. You feed the result into a UNet. The UNet will also learn from many images, trying to fix the appearance of your re-rendered images. That will produce a very high quality image. So the idea is very simple but very effective. Okay? So once you generate many new viewpoints, you can actually use these new viewpoints to refine the geometry. Because, for example, the simplest thing you can do is you can learn the masks, the Moulon masks. Then you can use the masks, many masks, to run structure, not structure from motion, but structure from shape from silhouette. So you can do kind of a visual whole type of approach. You can find the intersections of these masks, trying to refine the geometry. So this is showing you the original geometry, and using the SFS, trying to refine the human shape geometry. And finally, you can actually use the SFS geometry with the original geometry, whether this is captured by structural light or captured by a stereo dome system. You can actually catch these holes to generate better results. And you may wonder, why don't we just use SFS geometry? Because generally speaking, SFS geometry is of a poor quality. They don't have details. For example, the facial geometry, the clothing, the wrinkles, the folds on the clothing, they're all gone. So this is showing you, hopefully you can still see the video. This is showing you the result, the neural rendering results versus the regular point cloud rendering. So with regular point cloud rendering, you will see there are many holes on the shape. Okay, so even if you texture map it, for example, if I stop here, you will see actually there are many artifacts near the back, near the arms, near the hands, near even the head. So, but using this neural rendering techniques, you can actually fix the appearance first, because you learn from the point cloud associated with the appearance. Then you generate a better geometry from. So hopefully, I know I'm exceeding time, overwhelmingly exceeding time. So, but I want to introduce one last very interesting work. So we have shown the result of the face and the body geometry to the cell phone manufacturers, and they love the results. But they're still not happy with the results. One reason is that they think human hair looks too fake. So they still want to fix the human hair. But fixing human hair is even more challenging, because human hair actually looks translucent, transparent. It has an opacity rather than it's just opaque. So can you actually use a similar technique to fix opacity of, for example, human hair? So we basically extended the work, and we presented a new technique called neural opacity point cloud. So on the right, I show you the regular mesh. You see the hair is a horizontal mesh, basically, because the hair has fine fibers, hair is dark, reconstruction produces many holes, all kinds of artifacts. So, but using our technique, you can actually build a 3D appearance of hair with translucency. Okay, so how do you actually do that? Well, the way you do that is almost identical to the way you do human body rendering. So you learn a point feature from the hair. Okay. Then you feed it into this network to learn the feature map of the hair. And once you do that, it's very critical that you separate the RGB channel, which was, for example, in human body reconstruction or human body neural rendering, and the alpha channel, the opacity channel. The opacity channel behaves very differently from the original RGB channel. So you learn a separate opacity channel from the human hair images and appearance. And then you actually, I'm going to skip the details, try to learn all these features. And you also concatenated use the UNet to fix the appearance. Okay, right. So this is showing you the training, process, which is very much like a differential rendering. So the rendering framework, it takes the same as the original one. Basically, once you train the RGB encoder, you encode the RGB encoder network, you can actually directly output to the RGB channel. But instead of directly outputting the alpha channel using this RGB network, you actually train, like I said, train a separate alpha channel. So this is trying to show you, if you train a separate alpha channel versus without training alpha channel. So without the training, separately training and producing alpha channel, you see actually the hair looks very, very blurred. They appear excessive blur. Alpha opacity does not look realistic. But with the separately training the alpha channel, and you can actually see, many fine details will appear. So you can actually preserve the fine details of hair models using this alpha channel. Once again, this is trained on 3D point cloud rather than a single image. So you produce a three-dimensional appearance of opacity. So let me show you, we just skip all the training details. So basically, in order to capture the data set, we actually do constructed a rotation table, and many cameras are facing the model. And then we have a calibration pattern. Then we capture many views of the hair. And once we do that, we generate a 3D point cloud, which, like I said, has many holes, not perfect. Okay? And then we also generate a mask for automatic alpha extraction. So you will get the ground truth alpha mask for every viewpoint. That's used for training actually the opacity of hair. And finally, you can actually concatenate all these results with a 3D model. You train the 3D, you train both the appearance RGB and alpha on the point cloud, and then finally you produce the results. So here I'm trying to show you the results. So this is trying to show you the traditional. For example, you just use the image-based visual or image-based opacity, or you just interpolate the views, and this will produce a very strong artifact. It does not have very smooth alpha, and the appearance jumps. This is the traditional. I hope you can see the video.
Yeah, we can.
Okay. All right. Okay. And this is trying to show you if we use the RGBA, we basically bundle RGB and alpha all together to train a network. The results are slightly better than opacity hole, but the results will exhibit excessive blur, as I mentioned, because you're not supposed to train the alpha channel along with the RGB channel. So you will see actually the flickering and the blur of the hair. Okay. And finally, this is our result. This is our result. Basically trains alpha and opacity, alpha and the color in different ranges. And this is once again, this shows you the traditional method of rendering the wolf. This is using RGBA rendering, and you can see, the fur looks very, very blurred. And finally, our results. This is our result. You can actually see, for example, the tail of the wolf, the hair of the wolf, they look very real. So finally, to the person, so now that they say, okay, can you actually fix your human hair? You have the face, you have the geometry, can you fix human hair? So the human hair, like in this case, if you use a point cloud rendering, you see all these artifacts. If you train RGB all together, you produce, for example, very blurred hair appearance. And if you use our method, you will produce, very high quality alpha maps across the views. This shows you one more results. By the way, this work was published at ICCP this year, and on the special issue of TPAC. And as you can see, using our technique, you can actually generate a quite realistic opacity appearance of hair on human. All right. So to conclude, basically, I have presented to you, a method of techniques. My apologies, I marginally touched the SLAM module but the SLAM module is indeed very important because using learning-based SLAM module, all these techniques requires using this technique to conduct the camera pose estimations. But I hope I have convinced you, in order to reconstruct a very complex objects, in this case, human beings, you have to consider learning-based techniques. For example, we use used learning-based techniques for both feature matching and 3D reconstruction. And in particular, we use this neural renderer to fix the 3D geometry. A very important take-home message, hopefully you get, is actually to that if you have a very good image, but if your geometry is very poor, that's okay, because you can potentially train networks to fix the appearance when you do view interpolation. That's probably the most important thing on that. And I think we're at a stage very close to constructing or building a very, very realistic human digital avatar. So I think we're very close to doing that. Finally, this work, the majority of this work is done by my students, Pierre, Chen, Chen Wang, Xingsuo, Zhou Liao, and Shuna. And this is a group photo. Our group at Shanghai Tech, is still actually recruiting faculty, both faculty members and postdocs, and if you're interested, please do come contact us. All the codes actually I mentioned in this talk, including the neural human rendering and this neural opacity hope, the translucency, are available online. So you can actually check our course, check our project webpage and just to download the code. And that concludes my talk. Thanks very much.
Okay, thank you very much, Dr. Yu, for your great talk. Finally, it worked. It works fine, and I can hear almost all the details of your talk.
Thank you.
Yeah, we have some questions and from audience and myself. First is do you have the timing performance about the reconstruction? Is it?
You mean the So this you raise a really good question. So for the Oppo and the Vivo applications, so initially they actually asked us if we can conduct everything on the cell phone within 1 minute. So this is obviously a mission impossible. So in our previous case, for example, in this office, you can see this slide. So in this case, this result is actually indeed reconstructed under 1 minute on a cell phone. But this result does not use a learning-based fixing. So having said that, for the facial fixing, it's actually relatively easy because once you train the network, you can actually infer the facial details, under 10 seconds. So that's easy. For the body part, actually, reconstructing, just using our learning-based pose estimation reconstruction, that's actually fast. But if you want to fix the human body, as I mentioned, you will have to pre-train, a sequence of models. So the training process takes very long, hours, if not a day. But the inference, can be very fast, under 10 seconds. So basically, if you pre-train the human model, this character, then you can actually infer or fixing the geometry very quickly. Yeah,
sure.
But the training part takes a lot of time.
Yeah. Anyway, training can be conducted offline as long as the inference is quick enough, and I believe the users are very interested in this work.
Yes, thank you. Yeah.
And another question is for reconstruction. I believe when you are showing, you have fixed the background, and that is make the segmentation easier. So when you try to calculate, even for visual hall, that is you need to have a good segmentation. And what about in the real world application? And does it work as good as what you are showing here?
That's a great question. So I think there are two scenarios. So in this 3D portrait scenario, actually we're using the RGBD sensor. Although even the depth sensor is very low resolution, so we use the depth sensor to help segment the results. So that's actually very straightforward. Then you have a background, okay? So in a different setting, in a dome setting, actually, so the challenge is actually this is relatively easy because you have the D sensor. So in this case, you actually only have RGB sensor. You have a dome system to capture the human body, and it's actually quite a lot of challenge to actually do robust segmentation. Even though you're using green screen, you see actually there are lights and the pillars, in the background. So, but but the nice part of this, I did not have time to go into the details about this neural rendering, is actually you can actually produce the RGB image and also the mask using this network. So once you actually produce, the mask for a small number of RGB images within this data set, you can actually use this neural renderer to produce automatically produce full masks, for the rest of views, for many other views. And we use that automatically generate a mask to generate shape from silhouette or shape from shape.
Okay, sure. So another question is, from the rendering and the images, seems like you have already a realistic image, so that you can do the rendering, you can get the pose correct. And do you have a number somehow how many images from different perspectives could give the best result, or something like for something like what is the trade-off between the accuracy and the number of images and from different perspectives for this kind of result?
Yeah, that's a really good question. So in the Oppo and the Vivo case, in the mobile portrait scanning case, actually, we used around 100 images. Because basically we move the camera around the person, so to capture about 100 images. And for the dome setting, actually, we use fewer images, because as you can imagine, cameras are very expensive. Mm-hmm. So in this dome setting, we use about 80 views. And in some cases, for example, we only use 56 views. So that's why, if you use a sparse set of views, actually, you will lead to, for example, overfitting, because like the images became blurred when you introduce new views. So to compensate that, that's why, in this multi-view capture system, we actually add the temporal division. So we not only train on a fixed time instance, but train on multiple time instances to actually learn the appearance. But in the Oppo and the Vivo case, in the mobile scanning case, because we capture around 100 images, that seems to be sufficient to render, this realistic 3D person. I also want to mention there's one more subtle difference. So in this dome case, we use fewer cameras, but we use a temporal sequence of views, and this produces a very high quality 3D geometry. But in the portrait case, that even though the geometry isn't great, but the final result looks much better, because you're viewing this person on a fixed trajectory. For example, you're just rotating the person. You don't actually move up and down. So this actually also compensates a lot of visual art.
Yeah, that totally makes sense for me. Yeah. Actually, when you show alpha using the alpha channel for learning, that is very interesting for me. And actually, alpha channel, I don't see much work using alpha channel to help. I basically see quite a lot of work on using RGB, but I didn't see many people using the alpha channel to help in the learning process. And for here, and when you use alpha, for this, you are from the fusion side, and do you first fuse the images together? For example, RGB and alpha, 4 channels together, and inside put into the network. Or you first learn a encoder decoder for the RGB, and learn a separate encoder or decoder for the alpha channel, and then fuse them. Is something like
correct?
Yeah.
Correct. We adopted the latter part. Yeah, you're right. So in the inference stage, we actually separated the RGB and the alpha inference, and we believe this is actually very critical. If you infer them all at once, you actually see this, as I'm showing you. This is showing the close-up. You see the excessive blurs. You see many blurs, And but if you separately handle them, you see actually all these blurred details, will be revealed, because we will preserve finer detail. And so this is our observation. We figure that we have to separate. So
Okay. So that means we need to separate. Okay, we don't learn together. That is okay.
Correct.
Okay.
Correct.
And maybe we have time for one more last question. And from your perspective, actually, in yesterday's talk, there is one speaker, Daniel Cremers, mentioned probably right now for SLAM and for structure from motion and traditional algorithm and geometry-based structure from motion and SLAM algorithm still achieve the state-of-the-art algorithms, especially in the camera pose estimation. But he mentioned for depth estimation, that could be something like the current learning based could be the best and achieve the state-of-the-art result. And from you just comment and you mentioned we really need to use end-to-end learning process. And do you have some intuition here or insight here? Whether we want to use something like a partial for deep learning, or we really make that everything into end-to-end is the best.
I see. That's an excellent question. I think my comments do not contradict Danielle's. Actually, I think what I have shown is actually so if you use deep learning for fixing the appearance, no matter the geometry is captured by traditional methods or by learning-based depth inference, the fixing part, will always work. So this is basically the take-home message. So with poor geometry, whether it's generated by SFM, by 3D scanning, if you use images to improve the appearance or re-render, actually that will actually benefits the final appearance rendering. So this is the one. And for the for example, SFM per se, we figured, at least in our experience, we figured actually learning-based pose estimation actually in several cases do outperform commercial softwares. So especially when the features are sparse, and we observe, and also when appearance vary across the views, for example, shading differences, etc. It turns out the learning-based techniques actually do outperform the state of the art. I think maybe because the procedure actually tries to learn the topological relationships between features, and also their appearances in the appearance space. This basically makes this feature matching and the subsequently pose estimation more robust.
Okay, that totally makes sense. Yes. Okay, that is probably the question right now, and we really thank you very much. And after you
Sorry for the trouble, for the but I'm glad finally worked out.
That finally works out, and I know you especially get up very early in the morning for this talk, and we really appreciate for your effort to make this talk finally work.
My pleasure. Okay.
Okay, cool. Yeah, thank you very much, Dr. Yu. I would like to thank you. There even there was some troubles, and on YouTube channel I can see from time to time there are still 80 to 120 people around here. So okay. Yeah. And now I can see your face.
Okay, so I forgot to turn on my camera. My apologies. Okay, yeah, okay, right.
Okay, cool.
All right.
Yeah.
Okay.
Okay. Thank you very much. Yeah. And for bye. And for the entire talk, right now we finished our workshop, and thank you very much for Winshan's group for his great support. And Winshan, later I think you will have the videos processed for our audience, right?
Mm-hmm. Yeah, we will process the video later and make them all published on our website.
Okay, thank you very much, Winshan, and really appreciate you and your group are still here. And
yeah, you did a really great job. Yeah, I enjoyed the whole workshop a lot.
Yeah, me too. And finally, there are some troubles at the end, but finally we work out.
Yeah. Also, I appreciate Yafei, Chen, and all other members from our group.
Yeah. They really work hard, help to transfer the question from YouTube to the Google Doc. Okay, cool. Thank you very much, Winshan, and it's really nice working with you and your group.
So
Okay.